Okay, so hello everyone. We are starting with the next session for our day. So this session, which is the first for today, is about brain-inspired neuromorphic computing. So the first speaker is Mr. Miguel Soriano, who will talk about photonic reservoir computing using time multiplex systems with classical and quantum resources.
All right. Thanks a lot. Thanks a lot to the organizers for the invitation and all of you that made it so early in the morning. So indeed, I'm Miguel Soriano, and I'm coming from IFISC. This is in the Balearic Islands in Spain. And the topic of the presentation, not a surprise in the context of this workshop. It is about photonics for machine learning. This is a field that is now making a lot of progress, and there are already very nice review articles that cover the recent advances, and here I highlight some of them on Nature Photonics, on light science and applications. These are some recent review papers. I also wanted to advertise a bit a special issue that we published recently in collaboration with Daniel Brunner and Sanhui Fan in Nanophotonics that covers articles with recent advances in the field. In general, what we are interested in is some application like here image or voice recognition that you want to solve. And these applications run better on with an algorithm such as neural networks, artificial neural networks, or convolutional neural networks. And these algorithms, conceptual algorithms, actually run more efficiently over a dedicated hardware. And this is why we are here. And photonics is actually a very successful substrate for these kind of implementations of artificial neural networks for different reasons. And just a recap of artificial neural networks. I guess you are, most of you are familiar with artificial neural networks where we want to process some information, and this is done by dividing some nodes in layers, layer-wise, and you want to have this information processed, and then information flows from the input to the output and gets nonlinearly transformed in every layer. Eventually, with some training, you get the application going. I wanted to make a difference, highlight the difference between a feed-forward neural network, where the information just flows from the input to the output, versus a recurrent network. In a recurrent network, you also have layers from input to the output, but in the intermediate layers, like here, a hidden layer, in the recurrent case, you allow for some loops in the layer. This creates an eternal state that allows to process information of the context of previous information. It has kind of an internal state that provides memory. This is the difference between feed-forward networks and recurrent networks. This has some implications, in particular that feed-forward networks, you can approximate any continuous function. This is the approximation theorem, provided that you have more than one hidden layer in between the input and the output, and these hidden layers have nonlinear activations. In contrast, recurrent neural networks, thanks to this internal state, actually can approximate a dynamical system. The difference can be illustrated with this example here. If you want to do video activity recognitions, for instance, in this case, to identify from the frames that a person is running instead of walking, by looking at a single frame, in this case, if you know that this Usain Bolt usually runs, then you can understand it's running, but if you don't have this information, it would be sometimes difficult to understand from a single frame if a person is running or walking. Instead, if you see you can see it as a sequence, then you understand better that this person is running. This is what you can do with recurrent neural networks, for instance. I continue now with a historical perspective regarding optical neural networks, or the use of photonics in the context of artificial neural networks. Actually, the first optical neural networks were explored already in the 80s, so 40 years ago now. But the interest in artificial intelligence declined, one of these winters of artificial intelligence, and also the interest on artificial neural networks also declined. We have seen a renewed interest on this kind of technologies since 2010. And there has been several approaches to optical neural networks using different multiplexing techniques. What I mean is that in the general context, you have an application that you want to run. The best algorithm for that could be an artificial neural network with some neurons and synapses. And you have in optics, you have the freedom to choose where you encode information. For instance, you can encode it in space, you can encode it in time, and you can encode it in wavelength, also in optical systems. This is what I mean by multiplexing. The operations that you can easily do in optics are, for instance, in contrast to other technologies, you can do Fourier transforms quite easily, multiply and accumulate. You can have hardware accelerators that work very well in optical systems. You can do convolutions. So these are operations that in optical systems, thanks to parallelism, you can do very well. Here I take the words from from an article here below from Dave Moss and collaborator, a recent article, that probably the ideal solution, the final solution, would be a combination of techniques. There is no one solution that is better than others. If we can combine all these multiplexing techniques, then the better. I also took this historical perspective from the article on the evolution of the different lines on space multiplexing, wavelength multiplexing, and time multiplexing. In here, I will focus on the initial works, some pioneering works on time multiplexing that started also in the early 2010, and I will continue with that. So the context is to use photonic systems for artificial neural networks and exploiting time multiplexing as a way to encode information. Now I will specialize from general recurrent neural network to a particular case of reservoir computing. Reservoir computing is a different name to say a recurrent neural network with random connections, so these belong to the same family. And in this case, if one thinks from a functionality point of view, the minimal ingredients for such a reservoir computing or recurrent neural network is that it has some nonlinear transformation. It provides a mapping of the input to high-dimensional space, and also that it has some memory, this internal state of a recurrent system. In a traditional case, a hidden layer of a recurrent neural network or reservoir computer has some nodes that are interconnected. In the case of reservoir computing, these connections have random weights. And the approach that we developed already 10 years ago, it was that one can encode actually the same kind of functionality using a single hardware device. This would be a nonlinear node here, subject to a delay feedback loop. In this case, the information does not live in different spatial nodes, but rather it lives in time in different temporal locations. So the information gets modulated, the information just comes as a modulation to a single nonlinear device, and we read the output of this device at different times, and these different times provide different information. In particular, I'm going to discuss the case of using as the nonlinearity a semiconductor laser, and this I will make an overview of the results that we obtained with this system. In case of using a semiconductor laser as the device, it allows all the properties, good properties of photonic system, like fast operation. For instance, we can achieve processing rates of gigabyte per second. And the first demonstration involved the recognition of spoken digits. So here, there were some digits from 0 to 9. This is a typical benchmark task. And with having as a nonlinear node a laser subject to feedback, we could recognize at the same time the speaker and the digits at these speeds. And also typical of reservoir computing and recurrent neural networks in general is the prediction, typical benchmark is the prediction of time series. There is some information that comes in time, and you want to predict, for instance, the future, how this will evolve in the future. So for this case of a prediction of a chaotic time series, one can also do it with a photonic system. And in this case, the prediction it was about, at the time, of 10 million data points per second. We are busy now trying to, or the recent advances that we have made in the progress is to try to make it faster. So this was more or less an introduction of the context of the talk, and here I give an outline of the scientific content of the talk from now on. I will focus on this information processing with photonic systems and time multiplexing, starting from the classical case of using a semiconductor laser, how to run it faster, how to combine it with integrated photonics, and I will say a few words about how to train these hardware systems. And I will end up the presentation with a jump to a quantum reservoir computing. This is something new that we are working on, and I will show you a proposal in a photonic substrate so far on numerical simulations. So for the first part, these are experiments that take a semiconductor laser as the nonlinearity. So this is how the experiment looks like in the lab. We work with optical fibers, components coupled with optical fibers. So let me explain you a bit how the system looks like. We have a semiconductor laser that we drive, and we drive with an external signal. The external signal comes from an injection laser. Here, I don't know if you can see it, but yeah, here from the top. This acts as a carrier, and on top of this carrier, we modulate some arbitrary signals with an arbitrary wave generator at high speed. This information gets injected and nonlinear transformed by the reservoir. Since we are operating it in a reservoir computing approach, in a recurrent neural network way, we have a feedback loop that gives us the internal memory. And so far, what we do is we detect the output of the laser, and then we post-process the information for the machine learning purposes. Just to give you some numbers now of the recent experiments, we upgraded the lab, and we can modulate the input at 92 gigasamples per second and 40 gigahertz of analog bandwidth. And the detection, the same. We have set up the detection for an analog bandwidth of 40 gigahertz. So regarding our previous experiments, now we have our focus has been to upgrade the speed. We have upgraded the speed of the input modulation and the output readout. The missing ingredients to how to speed up the laser, the semiconductor laser, and this is the point now of this slide. Usually, semiconductor lasers are operating such that the maximum frequency in a normal state is given by the relaxation oscillation frequency. And this frequency is in the order of 1 to 10 gigahertz in normal conditions. So more or less, this would limit the speed of operation when operating in a reservoir computing fashion. But actually, these are semiconductor lasers are very nonlinear devices, and there are some mechanisms to speed them up. One of the mechanisms to increase the bandwidth, the modulation speed of these lasers, is optical injection, for instance. And given that we are already injecting information optically, we play with the degree of freedom of the different frequency, the different wavelength between the injection laser and the reservoir laser. This is plotted in this here. So we have this is the optical spectrum of one of the reservoir lasers and the optical spectrum of the injection laser. And there is an offset or the tuning between them. If you tune them properly, you can still make them interact, but at the same time, the response laser increases its bandwidth. And this is known as an injection locking mechanism, and it depends on the strength of the injection, how much, this would be this axis here, how much light from the injection laser you get, and the tuning between the injection and the reservoir laser. So this is a mechanism to increase the bandwidth. I'm not going to enter into more details. So here, already one of the demonstrations that this is possible to do with injection to get an increased bandwidth. So here, a reminder of the setup with injection and the reservoir laser, and also a reminder of how time multiplex system work. So yesterday we saw also on the talk of Cathy, for instance, that time multiplex reservoir computing involves modulating a laser in time and then reading the light that comes out of the laser at different times. So this is what we call, in this context of reservoir computing, virtual nodes. So we built a virtual network out of the time multiplex response of the laser. Here we were focusing on how to get faster and faster what we call virtual neurons, so that we can read the laser at a faster and faster rates, and how we can sample the output of the laser faster and faster. These are intensity detectives from the output of the laser for different detunings, and you can see that depending on the detuning, so here there are 3 lines, and this responds to the output of the laser for different conditions of the detuning. This is the offset, frequency offset between the injection laser and reservoir laser. And we want to be in a condition where we got enough signal-to-noise ratio and also fast modulation. You see at the output here, you cannot tell much, but you can see that there is some oscillatory behavior of the laser. This is a nonlinear transformation of the input, so this already, if we look at this, we can already think that this can work for reservoir computing. If in an enlargement of this part over over half a nanosecond, these dots are actually the samples that we use later for the reservoir computing purposes. So we sample the output of the laser at these different times, and with this we build the output layer in a machine learning fashion. So it's possible with optical injection to encode this information at high rates. We have validated this kind of experiment in a time series prediction task. This is, again, benchmark task, so it is for academic purposes. The information that we process is here on the bottom. It's a chaotic time series. This comes from Bakiglass. It was also presented by Kathy yesterday. And the task is to predict the future of this chaotic time series. It's a hard task. It's a nonlinear task. And if it works, it validates the photonic system for reservoir computing, and then you can use it for other purposes. One technical thing is that how you encode information. I talked about virtual nodes. These are the points spaced in time that we use for information processing. Here, for this task in particular, I will be considering taking 200 nodes out of the output of the laser, of the temporal response, at 11.7 picoseconds. That takes a processing rate of 0.4 gigahertz. So this is the current speed of the system when using time multiplexing. We exploit a large bandwidth, and then with the time multiplexing, we read it in time. So this is the final speed of processing. And here I highlight the response for one of the tunings. This is the error in the task as a function of the tuning. So the tuning plays a role. There are some range of the tunings where the system operates well. And one interesting observation is coming back to the time multiplexed approach. So why does it work? And here we can see, maybe already get a visual illustration of why it works. And this plot on top, it has several lines, and this is the evolution of looking at a different virtual node as considered as an independent object. So in reality, the signal out of the laser comes as a sequence, but you can pick the sequence, you can follow the evolution of one virtual node separately. And this, if you do this, you can recognize that every now virtual node behaves slightly different, and with this high-dimensional projection of the input, then it is when you can process information. So this is the illustration of why the time multiplexing approach works. I've been talking about how to exploit semiconductor laser for this time multiplex reservoir computing. This gives us a sequence of data that comes in time, because we have encoded information in time. At the output, what we have been doing for experiments usually is to measure this, detect the signal, and post-process it in a computer. The post-processing is relatively simple. It involves multiplying by a weight, a normal of neural network. So you need to perform an operation here, like multiply the state of the system with some weight. In photonics, this can be understood as a modulation, applying a weight. And in the case of time multiplexed approach, actually we need to sum and multiply things that come at different times because of the time multiplexing and virtual nodes. So basically, what we designed now to have a complete device for time multiplex reservoir computing is a photonic integrated circuit that in itself compensates for the delays that the signal had. So for instance here, it's a circuit proposal that we recently built and are testing in the lab. In this example is one of with 16 delay lines that would allow to use a system with 16 virtual nodes. The one that we're testing in the lab actually has 9 lines for some technical reasons. The idea here, in this case with an integrated readout, is that the output of the laser comes, we modulate, we apply, by modulation we apply weights, and later we need to compensate for the time delays. So with different delay lines of different length, we sum them up, we combine them, and eventually at some steps in time, we get the right information. So the output of the system, the output of the photonic reservoir, would be the weighted sum at some times where all the delays have, of the information that was time multiplexed, it gets combined again, and the output is produced. We need to do this with photonic integration because we need to compensate for these 11 picosecond delays that we had in our virtual nodes. So we need to recompensate for every delay line of accumulated 11.7 picoseconds, for instance, in this case. In this direction of going to a complete device for reservoir computing, there is another step that so far we have only validated with numerical simulations. We are not testing in the lab. It is about how to generate the input in the time multiplex fashion, and this is done via what we call a mask. This is a repetitive signal that over which we encode the information. And since this is a repetitive pattern, one can also produce such a repetitive pattern using an integrated system. For instance, with a laser with feedback, you can produce periodic patterns. We have validated this approach in numerical simulations. This is a work of my colleague in Balearic Islands, Apostolos Arkiris, and it's something that we would like to try also with photonic integrated circuits. So now I'm almost finished with this part of the classical photonic reservoir computing using semiconductor lasers. And I wanted to say a few words about learning in physical systems, very, very short, because there will be other talks on this later today. But when you have a physical system, you would like it to learn, that is train. You can also call it training, depending on the language that you use. Often, you need to look at it from the hardware and software co-design point of view. And in the case of reservoir computing, time-multiplex reservoir computing, there are some weights that we can modulate. So far, in reservoir computing, we say that everything is random at the input. What we only care about is the output weights. This can be trained easily with a linear regression. So this has been solved already, thanks to the reservoir computing approach. If one wants to go to a fully trained recurrent neural network, one also needs to optimize the weights and the input. This is not so easy. For instance, in software recurrent neural networks, one would need to use backpropagation through time. This is an algorithm that helps you to optimize weights in a neural network. In the physical system, it would be the same. You need to optimize the weights that you apply here in a modulation. Again, reservoir computing is random. If you want to go better than random, there are some options, and here I list the two that came to my mind. You can do first idea is to have a very good model of your system, of your physical system, have a good model, physical model of it, that you can run on a computer, such that you can run the algorithms of backpropagation, gradient descent, and so on. So this would imply training them on the model and transfer the parameters to the experimental system. If you want to do that and be successful in the transference to the physical system, in the experiment, you will need to include in the model the characteristics of the experiment, such as component tolerance, signal-to-noise ratio, bandwidth, etc. This works, and I will show you one example, but in more advanced cases, one would also like to have training directly on experimental system. And this, actually, it was already, some ideas regarding these concepts of training directly on experimental systems were proposed already in the 80s, when the first optical neural networks were developed. And with optical materials, it's possible, but I'm not going to enter into that so much. So just to say a few words about how learning can work, I will give you an example on a time-multiplexed optoelectronic system. In this case, uses a Mach-Zehnder modulator here. And it was about going from this random mapping from reservoir computing to a full optimization thanks to backpropagation through time. First, when we did that, we had a good model of the system that matched the experiment. And the first observation is that the input weights that we trained were optimized both for the system, for the properties of the physical system, and for the properties of the task. For instance, if we looked at the bandwidth of the input weights that were applied at the input, immediately they is adapted to the analog bandwidth of the system. Also, instead of being random, the input mass also adapted to the properties of the task. In the case of task, this was for the digit recognition task. It started to find I mean, it's difficult to always explain what artificial intelligence finds or machine learning finds, but here already you start to see some shapes that maybe are useful to recognize visual features. So, as a summary of this part, briefly, so we found that this kind of more advanced learning improves the results at the cost of an increase in complexity. To give you some numbers, what we achieved experimentally for a handwritten digit recognition task, this is the MNIST that we have seen also in other talks. These are the digits, handwritten digits. In a reservoir computing approach, we went up to a 7% error, which is okay, taking into account the properties of the system. And on top of that, with backpropagation through time, training in addition to the output weights, also the input weights, we went down with the error with a 1% in the experiment, which is quite compatible even what you can do today. And the important point here is that the training time in the inference in the inference part of the system there is no difference. There is a difference on the training time. It is more involved to train the system with backpropagation. In reservoir computing, training would take minutes. In a similar machine, bar propagation through time could take hours. So this is the order of magnitude of the complexity of the training, involved in the training. So with this part, I close the first part of the talk. And let me say a few words about quantum reservoir computing and a proposal for photonics. So since we didn't have so many presentations, or at least we didn't have any presentation on quantum reservoir computing in detail yet in this workshop, let me say a few words of what we understand by quantum reservoir computing. It is, again, about processing time series. This is why what reservoir computing is good for, processing some information that comes in time. This would be the same. If you are dealing with a quantum physical substrate, you need to encode somehow the information. And out of the quantum physical substrate, so the evolution of the system, quantum system, you need to perform a quantum measurement if you want to extract information from it. In this case, for instance, one could take as observable some expected values of this quantum system. And with those expected values, one can build an output layer similar to what is done in classical reservoir computing. This is no difference. So we identify here in this sketch already that we have an input. This would be equivalent to the input layer. We have a reservoir layer. In this case, it can be quantum. And an output layer that can be classical or quantum as well. There are some scientific challenges to solve and understand if the quantum system can provide the requirements of reservoir computing, which are memory, nonlinearity, high dimensionality. We also need to take into account if the measurement, since the measurements usually alter the state in a quantum system, if this kills the memory that you need in reservoir computing. This applies specific to reservoir computing because it needs memory, it needs to have the previous input should affect the next, so measurement could be a problem here. There is another aspect of quantum systems that needs to be taken into account. Here we consider we need to make some observations out of this physical system, and we want it to be trainable. So these outputs, we should consider outputs that are reproducible, and quantum has this probabilistic nature. So we need to take multiple measurements or multiple copies of the experiment to get an expected value that we can use for the output layer. So all these things put together led us to propose a platform in photonics that I will explain. And to understand the context of this quantum reservoir computing, when we started working on this, we found that this is a very new field, and we were lacking some structure in it. So we wanted to understand how to talk to other people on the same kind of language. So one way to understand it is to define if the input is classical. We have 3 layers: input, substrate, reservoir, and output. So 3 layers. The input can be either classical or quantum. So we build this table considering if the input is classical or quantum, if the reservoir is classical or quantum, and also the last letter here. So this would be classical, classical. There is another C. Classical would be classical output. So you can have all these different combinations from the 3 possibilities, and up to going from a classic and the other extreme of the table, you have quantum input, quantum reservoir, quantum output. But all these, all the ones that have a Q in it, let's say, can be considered quantum reservoir computing in this initial understanding of it. Since we came from classical reservoir computing, we are familiar with the tasks and the benchmark tasks of classical reservoir computing. We wanted to see if the quantum reservoir could also solve those tasks in a photonic system. There are different substrates that one can have for quantum reservoir computing, and some proposals have been to use nuclear magnetic resonance in molecules, trapped ions, fermions or bosons in lattices, superconducting qubits, quantum circuits, and the particular photonic platform that I'm going to discuss is based on an optical frequency comb, the modes of an optical frequency comb. So here it is the proposal. We developed a theoretical understanding of it, and then we performed numerical simulations on it. We have some ideas on how this could be done in experiments, but the experiments are not yet done. So let me take you through the idea of the platform. We need to encode information, and for us, the information carrier will be optical pulses that come from a femtosecond laser pulses source. And these pulses, when you look at them in frequency, they have different frequency modes. We can encode information in these frequency modes of the frequency comb. So this is similar to what we saw yesterday in the talk of Sesmasar. It's kind of frequency multiplexing, and it is also combined with the ideas of time multiplexing. So here is when we start to see that the different degrees of freedom of optical systems can be combined together. The input information is encoded into the optical pulses by modifying these are squeezed optical pulses, and they are squeezed vacuum states because we are doing quantum reservoir computing. The information, for the moment, we encode it such that the input, this S of k is the input that we want to process, gets this input gets projected into the angle of the squeezing angle of this squeezed vacuum state. So our proposal is to encode the input in this angle. So for every time step of the input, the angle of the squeezed state will rotate. This is illustrated here in the picture. For input k, this is a sequence, k, k plus 1, k plus 2, etc. For input k, it will, the encode will define some angle in this representation of the quadratures of an optical pulse. And then the next input will give you a different angle in this representation of the PU and Q quadratures of an optical pulse. So we encode the input information. The time multiplexing comes in the fact that for each, we encode each input in multiple pulses. We want to do this because we need to get a statistical ensemble or an average of the quantum state to actually use it later at the output. So we already encode the input in multiple pulses to get an ensemble at the output. When we encode each input in a sequence of pulses and then the next input in a different sequence of pulses and so on and so forth. The coupling, we encode information in these frequency modes. We need to have coupling between these frequency modes, and this is provided by a nonlinear crystal that creates a complex network on the coupling between frequency modes. This complex network can be used in the reservoir computing manner. So our reservoir is the network of the frequency modes of the pulse. An additional ingredient of this proposal, this platform proposal, is to have a cavity with a beam splitter. Part of the light is reflected for the output layer. This goes to the detector, and the other part of the light is actually traveling along this cavity, such that we get this memory. This is similar to the classical case where we get memory thanks to a feedback loop. So here in the quantum case also you get the memory thanks to recirculating pulses also inside this cavity. For the quantum measurement, this photo detection using homodyne detection, this is typically done in optical systems for the detection of one of the quadratures, and out of that we build our reservoir. So this, just a small detail on the detection. I think this is important to understand the approach. So we detect for each of the pulses, each pulse contains several frequency modes, and from each of these frequency modes, we detect an expected value. Expected value that if it's a squeezed vacuum, the expected value is 0, but it has some standard deviation, and this standard deviation is proportional to the input that we encoded. So this is a way to recover the input information at the output. We had the coupling between the modes thanks to the crystals in the cavities, and our different, when considering quantum reservoir computing, the object with which we build the output layer is the so-called covariance matrix. This is how it tells you how different modes are correlated. So our object is to measure the frequency modes and see how the modes are correlated given this kind of function. This is this covariance matrix at the output is function of the input, and it also includes, as we will see, memory of the past inputs. So in the reservoir computing, in the quantum reservoir computing, our output layer is the covariance matrix, and the size of this covariance matrix is proportional to the number of frequency modes of the system. Number of frequency modes, I don't know if you can see it, is n, so the size of the covariance matrix is n squared. This is the dimensionality of our system. So there is, in this sense, an advantage to the classical case with the dimensionality going from n to n squared. In this approach, these are so far, these are Gaussian states, so you can only go to the second order. In other quantum systems, like quantum bits, you can have maybe a higher Hilbert space. Here in the middle, I put a picture of where we got the inspiration from for this experimental platform. These are experiments from Valentina Parigi at LKV laboratories in Paris, France. And she's building such complex networks of frequency modes out of pulses. And on top of that, we designed this protocol to use it for reservoir computing. And we are in collaboration with her. So just to give you a brief overview of some results that we can get on this approach. First, we wanted to see if it indeed has memory. So we tested a linear memory capacity. This is typical in reservoir computing. Is it about, it entails reproducing the input at different times, looking only at the output. So the system has memory, so that's a good message. This photonic platform would have memory if implemented in hardware. That's what we expect. And the memory is proportional, also maybe comes kind of natural, with the dimensionality of the reservoir, so the number of frequency modes. This was the ideal case of infinite number of pulses. When dealing with thinking of going this into a practical platform, you need to think of having a finite ensemble. This is where the pulses come from. For each input, we have distributed in several pulses. So how many pulses do we actually need to be close to the ideal case? We have considered that the estimation of the covariance matrix is the ideal plus some noise, and this noise actually is proportional, is inversely proportional to the square root of the number of pulses. So this is the first thing that you get. You only get a few pulses from the ideal memory, so you can remember points in the past. This is the delay. You can remember up to 50 inputs in the past. In the case of an ideal case, you had only 300 pulses to build your ensemble, you would be very, very bad. So no different from other quantum technologies. You need of the order of 10 to the 5, 10 to the 6 pulses to make an ensemble that is meaningful for this, in this case. We also wanted to validate the quantum reservoir computing for time series prediction. This, again, this benchmark task where you try to predict the feature of the next steps or the next events in a time series. In the ideal case, it works quite well with low error. And in the case of having this limited amount of pulses to build ensemble, you get a slightly reduced performance, but it's still possible to do it if you are in this order of 10 to the 5, 10 to the 6 pulses for the ensemble. In case of going away from the ideal case of infinite pulses and staying with a finite number of pulses, we found that there is kind of a strategy to deal with that, which is to control the reflectivity of the beam splitter in the cavity. This is a problem of signal-to-noise ratio in detection. Or most of the limitations that come with a finite number of pulses comes from the signal-to-noise ratio in detection. So you want to have you have less pulses, you want to have more signal for detection, as long as you still keep some pulses going over the cavity. So there is a balance with the number of pulses that you can have in your ensemble and the light that stays in the cavity for the loops. We have also results, and the time series prediction also a way to see that this photonic platform has both nonlinearity and high dimensionality. Even if it's Gaussian states, the nonlinearity comes from the encoding of the input to the angle of squeezing. This is where the nonlinearity comes from. The results on this the results related to this work are available on arXiv, and we recently, last week, got accepted this paper on physical review applied, so if you are interested, you can find it there. As a final outlook of the different parts of the presentation, I showed how there is a cross-fertilization between complex photonic systems like semiconductor lasers with feedback and information processing, reservoir computing, and I went there are some points that I would like to highlight. So there are, as we saw in other talks as well, there are opportunities for integrated photonic circuits in this context of the time-multiplexed, I'm referring to the time-multiplexed approach. The development of new learning concepts, we still need better hardware-aware training. That maybe can be done directly on the hardware. And also I touched on quantum reservoir computing. We are still working in collaboration with this group in Paris for a practical implementation of it. As a general overview of these approaches based on time multiplexing, it allows for rapid prototyping in the sense that with a single hardware device, just by adapting the time in which you encode information, you can make a larger or smaller network quite easily. You don't need to refabricate the device in this sense. And also it adapts to the task requirements. So some tasks, as we saw also in the talk of Kati Lutke, some tasks require different parameters. And if you have you have fabricated a device, this is maybe more difficult to change some of the time scales. In the case of the time multiplex approach, at least to understand what are the requirements, it's easier to change the time scales of the system as you have a single nonlinear device. So with this, I would like to thank my collaborators on the semiconductor laser case and also on the quantum reservoir computing. And I would like to thank you for your attention.
Very nice talk. Do we have any questions from the audience? So, okay, where's the microphone?
Thanks, Miguel. A really nice talk, a really interesting one. A quick question from my side. We saw that if we have a classical problem and you have a quantum substrate, then you give an expansion in the number of nodes that you can produce through the quantum substrate. On the other hand, in order to get your result, you have to do statistical measurements at the end, which is not the typical case for classical reservoir computing. How this trade-off for real applications? Have you considered what is the benefit of increased performance compared to the drawback of reduced acquisition time of the data?
Yes, I guess in general, what we have seen, I mean, if we want to use a photonic system, we care about the speed. So if the information is already classical, in most of the benchmarks, there is not so much advantage going to the quantum system because of this. We use this classical task to validate the quantum substrate. And once this quantum substrate is validated, I think the most interesting tasks, and this is where people see that there is some potential, is when the information is already quantum. This is not so different to the case of photonic reservoir computing when we process optical telecommunication signals, because all the information is already in the optical domain, so an optical reservoir computing makes sense. So here in the quantum domain, it's similar. It can be in the optical quantum approach or in other quantum substrates. If the information is already quantum, you cannot really process it with a classical system unless you do some detection or something like that. In the case of a quantum reservoir, you avoid this step, so you could process the quantum information directly. This could be in sensing or something like that. Yeah.
Okay, thank you very much.
Yeah.
Okay, do we have any other question? Okay.
Thank you for the nice talk also. I had a question for these measurements. When you need this standard deviation, you need to repeat those measurements. So you feed in a lot of couples of one pulse with one data and then the next pulses with a lot of them, or do you feed the whole time series in a lot of times?
So the protocol, as we have envisioned in this case, it is that one input that comes from a sequence is encoded in many pulses. So all these first sequence of pulses encodes the same information, and then when we switch to the next sequence, the next point in the sequence, then we encode it again in m pulses. So it is a sequence of pulses for one input, and a continuation, a sequence of pulses for the next input, and so on. And this size defines the ensemble. So this is an idea to try to do it everything online, let's say.
Okay, let's have just one more question.
Thanks, Miguel. Just some questions in the details of the setup. So you need the multiplexer there in order to measure the different modes in your photodiode, because you have frequency modes, as you said. Or you see the sum of all these in your photodetector.
So, I mean, you're asking for an experiment that doesn't exist yet,
but even in the simulation.
But in the case of the complex network already, so it is true that here it is about measuring different frequency modes. What you can do is at the measurement you can change what they call is they have a measurement basis, and depending on the measurement basis, then you can characterize all these frequency modes one by one, maybe, and then build a network out of it, and then eventually extract information. So this, and you can build so there are methods to build these covariance matrices. That is what we are interested on after doing this detection. Yeah, it's not easy. Yeah.
Okay, thanks.
Yeah.
Okay, let's thank the speaker again for his very nice talk. So the next speaker is Mr. Lorenzo Pavesi. And his talk is about the equalization of PAM4 IMDD signal by a small silicon photonics time-delayed neural network.
Let's see if it's here. Otherwise, I have to. No, it's. Let me check. No, it's not here. No. Just a moment.
So this is not my talk. No, but if you want, if you
But
prefer,
if you want to
I
talk
can
about
try.
that, you can.
Yeah, I can try.
You can do it. I'm sure about that. Okay.
So thank you very much for the invitation, for the opportunity to be here, to tell you about a device that is actually an implemented version of what Miguel was suggesting as a potential integrated circuit. So here we have this integrated circuit, and what I would like to show you is that this integrated circuit is actually doing something that is, according to us, valuable. Before starting describing this small integrated circuit, I would like to introduce my lab. This is the Nanoscience Laboratory in Trento, and what we actually are doing are working on different topics like quantum photonics, so we are also implementing, and we have also an integrated circuit scheme that is doing what, in a way, what Miguel was suggesting, so using quantum photonics for machine learning. So the paper will appear at the end of this year. Then we are working on non-Hermitian photonics as well as on neuromorphic photonics. So if you are interested, so here are a few references on one side, the highlights of what we did last year, and then this paper I wrote a couple of years ago about my path through silicon photonics in these last 30 years. So when people is considering neuromorphic computing, so the typical way to propose and to pass the message about what neuromorphic computing is to show an integrated circuit and on top of that a brain. Actually, this is our vision. So we have a project where we are trying to merge, on one side, photonic integrated circuit, on the other side, a biological circuit, meaning living neurons, and put those together on top of an hybrid artificial network where the neurons as well as the photonic neurons are computing, or if you want, are thinking together. And the actual experimental platform that we are developing in order to make this hybrid artificial circuitry is to work with living neurons which have been genetically modified by inserting on the neuronal membrane a light-sensitive protein. Therefore, so this is a technique that is called optogenetics, so therefore by using light, you can switch on or switch off the neuronal activity. So this is the experimental platform, and here is an example of how we do control by using light, focus, and pattern light, the activity of an actual neuronal culture. So on the left here, what you see is that the optical images of one of these neuronal culture where you can identify the neurons, so the body of the neurons, and then all the processes that makes this neuronal circuit. And then what you see here is that we are using patterned light in order to excite a single neuron, in order to excite 2 neurons, 3 neurons, and so that form our circuit. So here is, you see that we indeed are able to focus the light exactly on the body of the neurons. And then here is the response of the culture. And what you see here is nothing else than the map of the neuronal activity that reflect the fact whether the neurons is working or not following the light illumination. And what you see here is the fact that when you excite 4 neurons, then what you are inducing is a message that is traveling through all the circuits that those 4 neurons have formed. But this is within a microscope. And therefore, what we did was to develop a circuit, a photonic circuits that enable us now to excite the neuronal culture through the photonic integrated circuit. And here you see the circuits on the right. So you have the optical fibers that are used to carry on the light signal into the circuit, and then the small green square is the actual circuits. Then we grow neurons on top of this circuit. Here is an example. So you see all the lines, the dark lines are the integrated waveguide. So the platform is a silicon nitride platform because we need to have visible light. And then on top of this, you see the white signs that are nothing else than the actual neurons, the actual neuronal cultures. And then you shine light, so you see the small blue spots, that is the light that is used in order to excite optogenetically the neurons, and then the red spot are the calcium indicator that show that indeed the neurons are answering the excitation. But this is not going to be the main subject of my talk, because in the talk what I want to show you is the actual photonic integrated circuit that we are developing in order to enable optical computation. And one of our expertise is to use silicon microresonators. And if you are interested, so this is a review paper that you wrote. So we tried several different neuronal circuit. Here is an example of one of these reservoir computing system based on silicon microring and time multiplexing. So this was working and performing quite well. Here we have another work where we study specifically what is the nonlinear task that one microring resonator can perform, and the kind of memory, nonlinear memory, short-term memory, long-term memory that we have, and also what we did in collaboration with the group of Claudio Birassos and Apostolos Aegiris in Balearic Islands. So what we also did was to implement a scheme that is very similar to what yesterday Kathy was suggesting, meaning that using an external optical feedback in order to increase the memories of the system. So here you have a few of those. Then we also work in another scheme, no longer reservoir computing. This is a feed-forward network where each single node here is achieved, nonlinear node is achieved by using a micro ring resonator, and so we studied. So this is able to solve a task, even though in this specific case you have a severe problem of thermal crosstalk, like the discussion, theoretical discussion people did yesterday. As well as we implemented, so this is a new result we have, so we also implement a scheme of a photonic streaming learning machine by using arrays of microresonators, that here you see the arrays of microresonator, and by using localized grating scatters, so we are able to map the signal intensity of light in each one of these microresonator, and this is the input for our linear regression through which we implement this photonic streaming learning machine. So this network is quite well performing, so it's able to solve tasks like back node recognition or the iris flowers or whatever you are interested in. However, the topic of today's talk is to discuss with you a very small, a very simple silicon photonics time delay neural networks, very similar to the suggestion that Miguel did in his talk. And I want to show you that by using these very simple networks, so what we can do is we can really recover chromatic dispersion in an optical fibers. And we do that with a significant saving in terms of power, in terms of cost, and in terms of sizes. And this is something that is working. And the motivation we have is to try to block the penetration of coherent detection in the short reach. Nowadays, in the short reach, people, because of cost, because of power consumption, is trying to use direct detection. So very simple intensity intensity modulation, very simple transceivers. However, because of the problem of signal distortion, so the other kind of transceivers are penetrating the market, and those are based on coherent detection. So coherent detection is fantastic techniques, however, has a big limitation is the fact that in order to elaborate the recorded data, so you need to use digital signal processing, meaning that you need to have on board of your transceiver a DSP chip. And this DSP chip, so digital signal processor, has two main problems. So the first one is that it's expensive, it's cost, and the second one is that it's power hungry, so it's consuming significant part of power. And therefore, there is a big motivation to try to improve the performance of direct modulation schemes by which you can overcome this cost and this power consumption limit of coherent detection. And so our motivation is to try to put simple transceivers even where more elaborate and more expensive transceivers are needed. And so one of the big limitations of this simple transceiver is about the fact that when you propagate a signal in an optical fiber, so the chromatic dispersion causes intersymbol interference, and therefore your pulse broadens. And the broadening of pulse means that you are losing the information that the data stream are carrying. And this pulse broadening is associated with the chromatic dispersion characteristic of your fiber, as well as with the length of the fiber that you are using. So the longer is the reach, the more severe is the problem. And therefore, you can use a simple transceiver for short reach application, 1 kilometer, 5 kilometers at high bit rate, but not for longer. And therefore, there is the need of coherent, because in coherent, you are not affected by that because you recover chromatic dispersion or nonlinear dispersion by electrical treating of your data. And so what we want to do is that we want to use intensity modulation, so simple scheme, even for long reach or high data rate, or complicated, so pulse amplitude modulation, complicated modulation schemes. And what I want to show you is that indeed this is possible. And this we can do by using a very simple neural networks. And this is the scheme of the network we are using. So you see it's extremely simple. You have an input where your data are inserted into the neural network. Then you have a splitter. So you split your signal along 4 lanes. And in each one of these lanes, you add a delay. And why we are interested in the delay? We are interested in delay because we want to process the bit in the present with a delayed version of the input. So what we want to do is that we want to process in our neural network what is the bit in the present with a version of what was the bit in the past, in order to be able to recover this pulse distortion that is caused by the chromatic dispersion. And therefore, what we did was to tune the length of the delay lines in such a way to be able to work at the data rate that we are interested in. For example, in this circuit, we want to work at 10 gigabit per second bit rate, and therefore what we are doing is that we are designing the length of the delay line as a multiple of 50 picosecond. And therefore what we can do is that we can compare the bit in the present with 1 bit in the past and 2 bits in the past. And what we try to do is that now we try to learn the way to recover the actual information that we had at the input, even though the information has been distorted by the chromatic dispersion. And in order to learn, what we do is that we use phase shifters. So by simply changing the phase of the light that is traveling on those different lanes, we try to make the interference between all those delayed versions of the input, and we try to manage to tune the interference in such a way to recover the information that we were interested in. And therefore, during the learning phase, what we do is that we change the current that is flowing in these phase shifters in order to control the phase of the light. In this implementation, so we only use 4 different lanes, and we do not play with the amplitude of the field. And so in this formula here, the amplitude of the field is only dictated by the waveguide losses. Clearly, the longer the delay is, the higher is going to be the propagation losses in the fiber. In a second implementation, I will show you in a while, so we are increasing the number of lanes, as well as we are placing Mach-Zehnder interferometers along each one of these lanes, so that now we can also tune the amplitude of the field. But let's see what's actually this simple device is doing. Remember that at the very end, what we are doing is that we are detecting an optical signal, and therefore the output is equal to the square of the sum of the weighted delayed version of the input. And this is what we are tuning in order to recover the signal. So the chip is actually very tiny. So this chip here in this specific implementation was fabricated by IMEC on our design. So here you see the dimensions. So you see the spirals that are making all those delays. Here is the experimental setup. It's very simple. So we have a transmitter. Then we have a fiber span of different length. Then we have our neural network that we're by using a current generator, so we can tune the phase of the signal. And then we have a receiver. So the data processing as well is simple. So here you see the input data. So the data are coded as a non-return to zero signal, 0, 1, at a bit rate of 10 gigabit per second. So this is the recorded signal after it has propagated through 100 kilometer long single mode fiber. Clearly we are working in third telecom window, nothing special. And what you see the distortion of your transmitted signal. And now if you make an histogram of the expected one and the histogram of the expected zeros, what you see is that those two distribution overlaps. And it's indeed this overlap that close the high in transmission. And therefore, so the training is performed in order to reduce the overlap between those two distributions. So what we are doing essentially in the training is to get the Q of those two distributions and try to change the weight in order to separate those two distributions. Meaning that what we are trying to do is to reopen the high. So here is an example of a trained network after propagation through 125 kilometer fiber. So this is the input. The two distributions are well separated. The high is well open. So here is the transmitted without the neural network. You see that now the high close. You have an overlap between the two distributions. Then you train your network, and the output is the following one. So the high reopened, and then the two distributions are pushed far apart. So if you prefer, so you can also compute the bit error rate as a function of the power at the receiver. So the black line here are the black line here are nothing else than the fiber to fiber. So are nothing else than the input, and you see that the bit error rate decrease as the power at the receiver increase. Then you have the bit error rate for the not equalized signal, meaning through the fibers. So in this case, the fiber length is 75 kilometers. And then the blue lines here is what you get when you use the trained neural network. So you can equalize and you can recover quite well the chromatic dispersion. Here you have an example after propagation in 125 kilometer long fibers. So you see that if you do not use the neural network, you are not able to decrease the bit error rate for any power rate receiver that you are considering below the prefect threshold. While if you are using your neural network, so you can significantly decrease the bit error rates, and indeed you can also pass the prefect threshold. So here you see the applied after training. So the applied phase shift that along each single lane that results in a reduction of the bit error rate below the prefect threshold for different fiber lengths. You see that the longer are the length, the more relevant is the contribution of the longer delayed pulses. So then we complicated a little bit the scheme by increasing the number of lanes. And what we did also was to add Mach-Zehnder interferometer along each one of these single lane in order to be able not only to train the phase, but also to train the amplitude. And so in this way, what we are doing here in the output, so we are making a coherent sum of a delayed version of the input, weighted both in amplitude as well as in phase. So we have now more possibilities to recover the distorted signal. In this case, we keep the overall delay 200 picoseconds as in the previous example. However, we increase the granularity, meaning that along each one of these different waveguides, so we are inserting a unit of delay that is not longer 50 picoseconds, but is 25 picoseconds. The more delays, the more in the past the signal is used. So this is the actual testing setup. Now, a difference between what we did before, we are moving the neural network before the optical link. So in this way, so what we are doing is that we are pre-distorting the signal so that the output, the signal is recovered. And then the experimental setup is a standard one. So here are the results. So this is the result for different bit rates. So the black dots are 10 gigabit per second. The black triangle are 20 gigabit per second. So the blue line here now are the transmitter, the bit error rate at the receiver without the neural network. And what you see is that as a function of the power at the receiver, that if you are sending a signal at 10 gigabit per second along a span of 125 kilometers, you are not able to pass the prefect threshold. If you are sending the signal at 20 gigabit per second for a span of 75 kilometers, you are even not able to match the prefect threshold. However, when you use a trained network, so what you observe is that you recover the transmission, and now you are able to pass the prefect threshold even at 10 gigabit per second, 125 kilometers, as well as at 20 gigabit per second and 75 kilometers. Here you have another information that is quite interesting, is the fact that now you can compute with a very simple formula by considering the dispersion that you have to compensate. You can compute the number of different lanes that you need in order to recover the signal. And here what you have is the bandwidth, so the data rate that you are using. You have the granularity of your delay, as well as the length of the span. And here is an experimental results where we show what is the bit error rate after 100 kilometers for 10 gigabit per second, non-return to zero modulation format. So the bit error rate as a function of the number of channels that we are using in reconstructing the signal. Clearly, by having a Mach-Zehnder, we can switch off the channel. And therefore, so we can make multiple interference between 1, 2, 3, 4, 5, 7, 8 lanes. And what you see here is that, and what you see here is the fact that as you increase the number of lanes, the number of channels that you are using in the network, you have that your loss function is decreasing. And since the loss function is decreasing, meaning that you are separating more and more the histogram between the ones and the zeros, so what you see is that also your bit error rate is significantly decreasing. And therefore, you have a further parameter that you can use in order to optimize the performance of the network. So the more lanes you are using, the longer span you can recover, or the faster bit rate you can approach. We have also used different training algorithms. So the results up to now were based on a particle swarm algorithm, so a genetic algorithm, or you can also use a backpropagation algorithm like the Adam-1. So the advantages of the backpropagation algorithm is the speed. However, you are not sure that you are indeed getting the overall minima in your loss value. On the other hand, the particle swarm algorithm is slower, but the result that you are getting is much better. And what you see here are the typical training time as a function of the fiber length at 10 gigabit per second, 8 lanes. And you see that we do train our network in 150 seconds for, by using the backpropagation algorithm, while it takes roughly 350 seconds for the particle swarm algorithm. Then what we did was to benchmark the results with respect to a commercial dispersion compensation module. So we wanted to see whether we are comparable or not. And so the system we were using is a Teraxion system that is a tunable dispersion compensation module. So it costs 5,000 euros, and typically you can compensate dispersion between 900 or minus 900 picosecond per nanometer, roughly speaking 80 kilometers at 10 gigabit per second. And so this is how small or how big, depending on the point of view, so the system is. And what I want also to underline is the power consumption. So this device here is consuming something in the order of 70 watt in order to work. Here is a comparison between the two, and the dots are the result with the dispersion compensation unit, the blue dots, while the red dot is the dispersion that you have if you use only a fiber. So clearly, for 0 kilometer fiber, you have 0 dispersion caused by the fiber because the fiber is not there. And then you see the effect at 25 kilometer, 50, 7,500, and 150 kilometer. The yellow dot here is the kind of dispersion that you compensate by using the integrated photonic circuit, so the small neural network I show you. And so what is shown here is the fact that indeed, by using our neural network, so we are as good as this commercial system in order to recover the dispersion up to a length where the commercial system is no longer working while our neural network is still effective. Here is another way to say the same. So this is the bit error rate as a function of the power at the receiver for the 8-channel perceptron at 10 gigabit per second. And what you see is that the two systems are working quite similar for 25 kilometer, 50 kilometer, 75 kilometer. You see that the curves overlap quite well. So meaning that by using the commercial system, we can compensate the chromatic dispersion. But we can do as well by using our neural network. And then what you see is that when the length overpasses the potentiality, the possibilities of the commercial system, so the commercial system, the blue, start to fail, while the red, that is the neural network that we are using, is still able to compensate for chromatic dispersion. However, so a significant difference is the size. Our neural network is extremely small. The power consumption. So here the commercial system is consuming 20 watts. Our neural network is consuming only 100 milliwatt. And this is simply the power that you need in order to actuate the different phase shifter in the circuit. Therefore, so this result here shows that the neural network, so the integrated system, is overpassing the performance of this commercial system at very much less cost if industrialized. However, the neural network is not only able to compensate for not return to zero signal, but is also able to compensate for more complicated modulation format. Here is essentially the same scheme as I showed you before, so the problem of the distortion caused by propagation in optical fibers. So here is the modulation format that we are using. This is pulse amplitude modulation 4, meaning that for each baud, for each symbol, you have 2 bits, 0, 1, 1, 0, 0, 0, 1, 1. And in this way, so you can increase the bit rate by using the same baud rate. So you increase the quantity of information that you can transmit at the expenses of a lower or a deteriorated signal-to-noise ratio, because now, instead of having only 2 levels, you have to use 4 different levels. And therefore, this is a task for the neural network that is more demanding than the one I've shown you before. And as before, what we are doing is we are minimizing the loss function, meaning that we are starting with the different histogram of the different modulation levels, and what we are trying to do is that we are trying to recover distinction between those 4 histograms, so between those 4 levels. And this is the goal of the training. Here is the results. So this is a 10 gigabaud or 20 gigabit per second. So the input, 4 different levels, clearly separated signal. Then after propagating through 100 kilometer optical fiber at 20 gigabit per second, you see the overlap. You have completely lost the information that you were transmitting. And here is after the training of the network, you see that now the histogram are well separated, so you can recover the information you were sending. Here are the A diagram. We have some noisy problem in the setup still to be solved, but this is the input from the AWG, so this is the output after 0 kilometer of fiber. This is the output after 25 kilometer of fibers. You see that the A is still open, so this is the improvement caused by the neural network for 25 kilometer fiber, PAN4, 20 gigabit per second. Here, the output at 50 kilometers, so now the eye starts to close. If you do not use the neural network, you can reopen the eye if you use the neural network. 75 kilometers without the neural network fiber So the eye is completely closed. You have lost your information. Too many errors. If you use the trained neural network, 100 milliwatt power consumption, you are still able to open the eye and get reliable information. So the situation is even worse for 100 kilometer, no more eye without the neural network. With the neural network, so you are reopening the eye and you are recovering the information. So let me conclude. So I've shown you a simple neural network that is able to compensate chromatic dispersion at high bit rate, at least at the higher bit rate that we can use in our setup, and for long distances. I mean, so we show that 75 kilometer prefect, 100 kilometer PAM4 at 20 gigabit per second. So the simple neural network win with respect to either the benchmark or more complicated coherent transceiver, both in power consumption. Coherent transceiver, you need a DSP here, you do not need. And the reach, standard transceiver, intensity modulation transceiver, have a limit at 8 kilometer. Here we can overcome 100, 125 kilometer. In the cost, so the cost of the cost of the commercial system is 5,000 euro. Here, so you can, so this is a very simple integrated photonic circuit that when fabricated in volume is a few euros. And so we gain in power, reach, and cost. Now we are trying to see whether by using this kind of neural network, so we are also able to compensate for nonlinear dispersion. And if you are interested to get the answers, so come next year to the workshop where I will show you the results. Thank you for your attention.
Thank you for a very nice talk. Do we have any questions from the audience? Okay, there are many questions. So let's have two of them because we are short on time.
Thanks a lot, Lorenzo, for this very nice work and the talk. My question has to do with tolerance that you have on the perfect length that you can achieve on the spirals. So you need a multiple of half the bit period. And probably there will be some deviation due to fabrication imperfections there. So some spiral will give you 51 picosecond, another one 102 or 98. Have you investigated the tolerance to these deviations? And also the tolerance of the whole system to slightly changing bit rate, so around 20 gigs or around 10 gigs.
Thank you for the question. So the answer to the first one is that so the system is very robust because, as you know, in optical communication, the way you use in order to measure the bit error rate is to sample your signal, right? And so what we did is that essentially what we get was more, maybe here is shown. Here. Okay, so what we do, so we have in our sampling oscilloscopes, we have ample room where to place the actual time where we do the sampling of the signal. And therefore, so the deviation in the length will cause a small jittering in this threshold here, but it's really not relevant. Really not relevant because everything here is linear at this stage. The second question I forgot.
Yeah, the length is also the same.
The bit rate, no problem at all. Okay. So it's more a problem of synchronization between the input and the output than what is happening to the network.
Okay, let's have just one more question because we are short on time.
Yeah, thanks, Lorenzo. Very interesting work. So one thing I was wondering for the sort of 8-line example. So you move the compensation before the transmission. So I was just wondering, I mean, sometimes doing dispersion pre-compensation then gives you extra nonlinearities and so on in the transmission. So it might be related to what you just mentioned on discussing it next year, but I was actually wondering whether then you can maybe not actually compensate for them, but really use them in the computation. I mean, whether you have any feeling whether that is actually helping you with fixing things.
So the reason why we do place the neural network before the fiber link instead of after is essentially because everything here is very sensitive to polarization, but the fiber not. I mean, so you can have PLD, and so we do not want to have issue about polarization. And therefore, so we say near the transceiver because there the polarization is already fixed and controlled. And this stabilizes the response of the system. Then the other question, could we use this for computation? Yes. So we have a paper a couple of years ago where we are using this very simple setup here to do computation like XOR, like digital computation. So yes.
Okay, thanks again for the very nice talk.
Thank you.
The next speaker is Sarah Massad, and she will talk about the great photonic reservoir computing for telecommunication applications.
Right. Hi, everyone. My name is Sarah. I'm a PhD student at Ghent University and IMEC. Today, I'll be stepping in for my supervisor, Peter Biensman, to present our group's work on integrated photonic reservoir computing for telecommunication applications. The work I'll be presenting here today pertains to efforts that I've done, but also efforts that my colleagues, current and former, have also done. For the outline of the presentation, I'll first give a very quick, very brief introduction about reservoir computing, and then I'll do I'll speak about some of the experimental results that we've recently incurred, and then I'll also speak about some of our simulation results. So, very quick, very brief introduction. What is reservoir computing? The basic principle is basically we need some kind of nodes that perform any function, linear or nonlinear, preferably nonlinear, but we can go away with linear functions, as I'll show later. And then what we do is we randomly connect these different nodes with each other. By random connections, I mean we don't really care about the weights of these connections. We don't engineer them. And then we don't train the network, but instead we tap into the different nodes of the network and we train the readout. Now, this is particularly interesting if we want to do some kind of physical implementation, because in hardware, it's very hard to actually control your system once it's manufactured or fabricated. And so what we take this idea and we move it into passive silicon reservoirs. So we create an integrated circuit on passive silicon photonics. And what we do is we also make sure that our nodes aren't very complicated or sophisticated. And in that, we can have them be simple splitters and combiners, or MMIs, basically. And then we combine or we connect these nodes with one another using waveguides that we specify the length of, but we don't care very much if the length slightly deviates, which causes some kind of changes in amplitude and phase. Now, the good thing about this reservoir is that it's fully linear, and that simplifies significantly its manufacturing, but also the fact that we're not limited by timescales of the nonlinearity. It also generalizes nicely to digital and analog tasks. We've shown somewhat like 10 years ago that this can also do both linear and nonlinear tasks using a simple trick that I'll introduce in a second. So this is another schematic of the reservoir. It's basically a space multiplexed reservoir, so it's not time-based. You have it spread out in nodes in space. And the first node here is elaborated a bit more. So it's an MMI with 3 inputs and 3 outputs. And basically, you have the chance to inject an external input into the reservoir and also read at each node out of the reservoir. And basically, this is what I'll show here. So you send a pulse input, and then you can see or visualize this pulse at different nodes. And then, obviously, what you need to do is once you have this readout, you need to weight each of these outputs, and then you can sum them and receive them by the receiver. Now, what we do as a trick here to induce nonlinearity in our system is we actually leverage the receiver as a nonlinearity. So there are several options for receivers that can be inherently nonlinear. And what we do is we treat this reservoir as a pre-distortion system of some sense, and we use the receiver nonlinearity to kind of have this entire system behave or work for us for both linear and nonlinear tasks. Now, the bulk of this presentation will be about telecommunication tasks, so I'll have a very quick introduction about what kind of problems we're actually talking about. Now, a fiber channel typically exhibits both linear and nonlinear issues, be it dispersion or Kerr nonlinearity. The challenge arises when you have these issues that are distinct in nature but happen simultaneously and affect each other, but they're also propagated along the entire propagation length. So if you're only operating in the linear regime of the fiber, this becomes a linear problem, which is easy to solve. However, once you start inducing nonlinearities, then the model becomes a lot more complex, and you need a bit more involved modeling in order for you to model the fiber, but also to compensate for the distortions that arise. And here I just show a very quick signal illustration. What I want to show here also is what this signal actually means. If you're not very familiar with it, this is a 64 QAM, or quadrature amplitude modulated signal. It's an advanced format compared to ones and zeros, or on-off keying, in the sense that you have real and imaginary modulation, basically. So you encode information both in amplitude and in phase. Now, as the signal propagates along the fiber, you can start to see that significant distortions happen. And distortions in this case look like different symbols that originally were distinct in nature overlapping with one another. So a very brief high-level introduction for basically what kind of problems we're actually talking about in this presentation. Now, for the first experimental results I'll be relaying today, we're talking about linear and nonlinear compensation at multiple wavelengths. So here we send data at different WDM channels, and we use the same reservoir to compensate for all of these distorted signals. These are experimental results that we've recently received. But before I go into that, I just want to clarify a difference in two different architectures, let's say, or sorry, readout schemes. So initially, what you would like to have in your integrated circuit is the ability to have the reservoir and all of your weights and your combiner on the same chip. Unfortunately, for us, this is a bit more challenging because the weighting elements are not very mature, and well, the combiner tree also introduces significant losses. So we have an alternative scheme that we're going to be using for this part of the experiment, where for every node, we detect the output at that particular node, and then we do the weighting and the summation electronically. So this is what we call the electric readout, and this is what will be relevant for this part of the presentation. So the setup we have here is we have a CW laser, we modulate it with ones and zeros, on-off keying, and we amplify the signal before the fiber. The reason we amplify it is we want to explore the behavior of a reservoir or the ability to do compensation, both in linear and nonlinear regimes. And to get into the nonlinear regime, we need very high power, so we need to amplify our signal significantly. Now, after the fiber, we also need another amplifier because our chip currently, or this implementation, is very lossy, so we need to make sure that we have enough power at the receiver to detect the signal. And so, again, we use multiple amplifiers just for that particular reason. So this is a 4x4 node reservoir. We have a 25-kilometer fiber and 28 gigabits per second. The idea, again, is that we want to be able to train for multiple wavelengths. So basically, since our reservoir behaves as a giant interferometer, we know that at the free spectral range, we're able to have the same behavior for the different wavelengths, but we also want to kind of expand the behavior around those target wavelengths. So this is one of the results of the paper. Basically, what we show on the top is that if you don't take into consideration all of these different wavelengths and you just train for one, you get very good bit error rate performance for just that particular wavelength, but you don't get, I don't think my mouse is showing. There we go. So you get very good performance just for that particular wavelength, but this does not extend to the rest of the wavelengths. However, if you change your training mechanism and you start to incorporate data from all of these wavelengths when you train, you can enhance your performance for all of the different wavelengths. Now, again, this is with one set of weights, same reservoir that can compensate for multiple channels. One caveat here is that there is no cross-phase modulation, so we don't transmit all of these wavelengths in the fiber at once. We actually sweep the wavelength at the input and then basically visualize it. And this will be relevant for the next part here, where we investigate nonlinear equalization. So here, what I mean by nonlinear is self-phase modulation. There's no cross-phase modulation. And what happens here is we can see that well, typically in these experiments, what we compare our performance to is a tap delay line in the electronic domain. So this is something that's very similar to what Lorenzo introduced before, but implemented electronically, basically, where you would detect the data, and then you delay it electronically, and you basically do dispersion compensation. So we compare our performance with an electronic tap delay line, and we can see that when the input to the fiber is low in power, this is when we're operating in the linear regime, we get very similar performance both in photonics and electronics, basically saying that in a linear regime, you get the same gains, basically. But when you go to the nonlinear regime, because we're able to leverage the behavior of our reservoir to do nonlinear compensation, then we get a significant difference between the reservoir and the tap delay line. In here, we also investigate what happens for an 18 dBm input power when the number of taps of the tap delay line increase significantly, just to show that this problem is inherently nonlinear, and increasing the linear size of the tap delay line does not contribute to significant improvements. These are results for the worst performing wavelength of all of the wavelengths that we've tested at. Right. So on to the next experiment that we've done. This is something that's a bit different in the sense that here we actually do this optical readout. So remember in the first part I was mentioning that we need to detect the output at different nodes. Currently we have smaller chips and maybe a bit more struggling chips that can implement this optical readout. So basically we have weights that are implemented on chip and then a smaller reservoir. This looks something like this. So this is the reservoir and all of this is the weights. So basically there are 8 nodes and then we have 8 complex weights or 16 different drivers basically and a combiner tree. Just for dimensions, this is 2.5 millimeters, and this is 15 millimeters. So the size scales significantly when you start adding weights onto your chip. Now, what we do with these experiments is we want to pass just a little word about the weights again. So these weights are BTO weights, and we're just experimenting with them right now. This is largely a work in progress. It doesn't really have any significant results relayed just yet. But we were struggling a bit with these weights because their extinction ratio is not very good. So the maximum to minimum for this, for example, weight is 3.5 dB. But then if we characterize multiple of these weights on different chips, we also notice that they have very inconsistent behavior, and they range between something like 3 to 15 or 20 dB extinction ratio. Not very reliable, not very consistent, but we are trying to do what we can with this system. So basically what we have here is a system where we do on-chip equalization, so everything is done optically on-chip. We have a transmitter on this side, and then we do polarization controlling again, because like Lorenzo mentioned, they're very polarization sensitive. We amplify this signal, and then we send it to a 25 kilometers fiber spool, and then we do the reservoir computing. So here, again, we have our RC chip, but we control the weight of this chip through an algorithm that we use, which is a evolutionary algorithm, basically. And then we monitor the power here, and we receive the signal, basically. The best results that were reported with this experiment, again, this is an exploratory experiment largely, was around 5% bit error rate, which was 1/3 of what we started with. Still needs a lot of work to reduce it much lower, but again, the size of the network was very small. It was 8 nodes, and the weights were very strongly limited, let's say. This work was done in collaboration with Elgar from IBM and Alessandro from ULB during their post-digital secondments at our university. Right. Again, very quick, I'll pass on something that we're also working on, which is basically coherent chip measurements. Now, I've reported previously, again, the same slide, where we have two different kinds of readouts, which is the optical and the electric. One of the things that I haven't mentioned, but we've recently started working on, is what if we replace the photodiodes with coherent detection? So we basically go over all of the nodes of the reservoir, and we coherently measure this, which basically allows us to recreate the optical signal, but electronically. And then this allows us to do things like coherent transmission, so 4-QAM, 16-QAM, and do this kind of training offline, basically. So these are incomplete measurements. I mean, we've done the measurements, but they haven't been processed just yet, but this is a direction that we're heading towards the next few months, basically. So we're trying to do coherent signal equalization, single polarization, both in the linear and nonlinear regimes. Okay. Now, we're done with the experimental part, so anything I relay after this point is simulation-based. So in the simulations, I'm going to be majorly talking about things that are done with Kramers-Kronig receivers. And Kramers-Kronig receivers are self-coherent receivers, so they're basically they allow us to detect coherently transmitted signals, but instead of using a fully coherent receiver as the one shown here, we can actually use a single photodiode. And this ability comes from transmitting an unmodulated carrier with your signal. So you have an unmodulated carrier, and then you have your transmitted modulated signal, and you propagate both of these together in your fiber. Now, your unmodulated carrier needs to be significantly higher in power compared to your modulated signal, and this actually affects your ability to correctly reconstruct your signal, as this animation has shown. This is a bit challenging because it means that once you pump a lot of power in your fiber, you actually enter the nonlinear regime. And so this is where we apply our reservoir computing, both for linear and nonlinear compensations, in the sense that we now don't need to amplify our signal to unrealistically high power and then pump it through the fiber. This naturally comes by the fact that you have a self-coherent transmission. One of the things that I just want to also very quickly pass over is a very simplistic pipeline of what the KK processing looks like. So we have a detection in the beginning, and then we have a logarithm and an exponential here. And the reason I want to highlight these things is because these two operations require digital upsampling. So it means that if you detect your signal at 2 samples per symbol, which is what's required for Nyquist, you actually need to upsample to 4, 6, or 8, well, actually 6 or higher for near ideal performance. And this adds some significant weight to your processing, basically, because it means that you need to do it now at a larger number of samples per symbol. This will become important a bit later in the presentation. Now, what we are studying here is our ability to do different kinds of compensation. So we're going to study the channel equalization ability, and also a bit later, the transceiver equalization ability. In the first architecture, what we're looking at is nonlinearity compensation. So this is for Kerr effects. And what we do here is we have a transmitter, we pass our signal through the fiber, and then we amplify it again, and we pass it in loops around this, basically. So this incurs significant nonlinearities every time that the signal finishes a fiber span, it's amplified again and sent to the span again. And so this accumulates multiple nonlinearities. Because we're looking into doing nonlinear compensation here, we do ideal chromatic dispersion compensation, which means that we remove perfectly all of the linearly contributed errors. And then we send the signal to the reservoir, and this is where we have our Kramers-Kronig receiver. Now, as I mentioned earlier, the Kramers-Kronig receiver can be operated in certain regimes where it's not ideal, where it's not fully linear. And we do use this ability because we need a receiver that's slightly nonlinear in order for us to do some kind of nonlinear compensation. So here, what we relay basically is the result of going over multiple spans. So on the x-axis, you have more Kerr nonlinearities. On the y-axis, obviously, as you go lower, this is better performance because this is bit error rate. And what we do here is we benchmark our performance against errors generated using an ideal transceiver and fully compensated for dispersion. So what this means is we're actually isolating all of the errors that come from Kerr nonlinearities. And we do this by removing any other sources of error. So any transceiver errors that can arise, we remove those shows by having ideal components, and then we have ideal dispersion compensation. We go a step further, and we do linear compensation, basically, just to verify that there are no residual linear errors that are left after this. And then we compare our result, which is using our reservoir with a slightly nonlinear KK receiver, and we backpropagate to adjust the weights. And so here we can prove that we do Kerr nonlinearity compensation, basically. In the next one, we are looking at doing linear dispersion compensation. So we're basically isolating different sources of error again, and just looking at our ability to do these different errors separately. Obviously, this also means that we can do them together, but we also wanted to alleviate any kind of ambiguity on whether we were adding gains in a specific region or another, so we kind of treated each error separately. In this, this is a standard transmission, basically, but there's no dispersion compensation here. This is handled at the reservoir. And what we show here is basically the added value of doing dispersion compensation optically versus electronically when you have a distorting receiver. So like I mentioned before, the KK receiver requires digital upsampling in order for it to have ideal performance. And you can see here the performance of the receiver as you increase your samples per symbol. It gets to an ideal performance around 8, but 6 is also quite good, and obviously 2 is quite bad. So what we show here is basically the added value of doing your linear compensation before a nonlinear distorting receiver. And you can see here that when the receiver is ideal, you get similar performance. Before that, you have some kind of gains because you're addressing the problem before a distorting receiver. One of the things that we also were looking into is whether we can aggregate multiple problems together. This is an example of that, where we look at the zones where the receiver is significantly distorting, and then we do backpropagation, and we kind of train our system to address this also with the overall issues. And so you can see here that well, at the zone where the receiver is strongly distorting, we have significant improvements, but then it's actually, the level of error is very low and it's not very trainable, so also not very easy to describe the improvements here in terms of bit error rate. Right, and the orange and the green are basically reservoirs. They're exactly the same reservoir, exactly the same size, but a different kind of training that now takes into consideration the receiver issues. On the last subtopic I'll be discussing today, this is simulations that we've recently done in terms of transceiver equalization with KK receivers and with DSP integration. So we basically focus at a different kind of problem. Here we look at the transceiver itself, so not the fiber channel, but the transceiver. And again, we're operating in a regime where the KK receiver itself can be distorting or nonlinear. And in that sense, we have reduced carrier-to-signal power ratio, and we have reduced upsampling. Both of these things mean that we save resources for the receiver, but at the expense of having distortions. So if this is what we want to send, which is a 64 QAM signal, and our QAM modulator can be slightly nonlinear, so you can have something that looks like this. If you have a noisy amplifier, this is also the effective noise, but also you start seeing that you have a line width of your laser, which also causes this rotation. And then in the end, if your receiver is nonlinear, then this is what a back-to-back connection would actually look like. Some of these things are obviously exaggerated, including the receiver behavior, but just to sort of showcase what kind of problems we're actually dealing with. And what we try to do in a system like this is basically inject a reservoir to do back-to-back, well, kind of in a back-to-back system, we inject a reservoir, and what we target is transceiver issues. And then once we have a reservoir trained, we take it into a system with a fiber, and we say, we want the reservoir to continue targeting the transceiver issues and to defer any channel-related issues to the DSP afterwards. And so we basically integrate our reservoir in a larger system where you have some DSP which targets the channel equalization issues and the reservoir which targets the transceiver issues. And we managed to achieve 3 to 4 times reduction in bit error rate, and this is largely because whatever linear dispersion that has happened in the fiber that was distorted due to the distorting receiver is not compensated properly with DSP. But once you have a reservoir that can help address these transceiver issues, you get better performing DSP, basically. Also, a small note here that we don't do the the laser line with compensation in the reservoir. Even though this is a transceiver issue, we do it with DSP, basically. Right. In conclusion, I just want to very quickly highlight other recent work from our group that was not mentioned in this presentation since it was targeted solely for telecommunication. Some of our recent work includes particle classification with spiking neural networks. We have a recent collaboration with a different group. We're using a Luihi chip. And then we have quantum reservoir computing, feed-forward architectures in photonic integrated circuits, and optically implemented coherentizing machines. The bottom two are still largely new, but the top two have actual progress, and I think we've had recent papers in this year. In conclusion and in summary, we've shown that we have successfully implemented experimental multi-wavelength linear and nonlinear equalization. We also have our initial attempts at doing all optical readout with online training for channel equalization. This is the natural next step to a paper that is currently on archive, where we do XOR and other header recognition tasks, basically using online training. But now we're taking it to the next step where we do channel equalization. And then the last two are simulation-based, where we do channel equalization with KK receivers, and we do transceiver equalization with DSP integration. Thank you very much.
Very nice talk. Let's have 2 questions because we're short on time. Okay.
So thank you very much, very interesting. I do wonder, is there any sense to use the reservoir computing integrated in the chip in this scheme? Since you are doing so much computation in the electronic domain, why don't you do everything in the electronic domain, or vice versa? So the need to put your integrated circuit in the chip imply that you have to add a further noise source that is an EDFA, because you have to recover by the propagation losses or the insertion losses of your receiver. So this is increased the noise level on your system. But since you are doing so much computation in the digital regime, why don't you do everything in the digital regime?
So I think the way I'm going to answer this question is sort of separate the 2 parts, because in the first part, where we do the experimental, for example, results, we don't do any kind of digital signal processing there. So there we do linear and nonlinear equalization both optically. The reason we have amplifiers there is, well, largely because we want to showcase that we have nonlinear dispersion compensation, or Kerr nonlinearities dispersion, compensation. And in that, we do necessarily need to sort of invoke unnecessary high power, but just for basically proof of concept results. Regarding the losses on the chip itself, this is an early implementation that we have, which is much lossier than the new versions that are coming right now because of certain grating couplers and certain bend radiuses on our chip. But I think we do gain something like 20 dB or so just by changing basically the design slightly. So there's definitely a lot of room for improvement. A lot of the weights as well that we're currently using are lossy, the combiner tree, but this is not necessarily something that can, that is inherently wrong with the idea. It's just the design and sort of implementation or fabrication was slightly lossier than we expected. In terms of why do we do certain things optically and things digitally, I think this is in reference to the KK receiver part, which requires some kind of digital processing as well. This is correct, actually. There are some gains, or there are things that need to still be done in DSP. And I personally think that the way to go about this is to start migrating some of the things that happen in DSP optically, and this way we can actually save, because you can have everything done digitally, but then if you can process things at the speed of light, and if at some point our losses are significantly lower, then it doesn't make sense to continue doing these things digitally when you can actually process them optically at almost no cost. So I don't think that DSP can necessarily be fully replaced just yet, but I think that it can nicely be integrated with the optical solutions that we currently have to sort of migrate some of the required tasks into the optical domain.
Okay, do you have one more question in the audience? No? Okay, so let's proceed with the coffee break. And we will be back in 10 minutes, I guess, to continue with the 5 minutes? 15 minutes. Yeah, that's better. That sounds better.
was trying to find a YouTube, you know, like bing, 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 bing sound. And then
that's right. So, I think it's about time to start.
Okay.
So the next session is about photonic approaches for artificial intelligence. And the first speaker is Volker Solzer. He's going to speak about photonic electronic chips for machine intelligence. So the floor is yours.
Well, thank you so much for the invitation. It's a pleasure being here. Good morning, everyone. So Volker Solzer coming from here from Washington, D.C. right now. This is actually my last day of being in Washington. It's actually very exciting. Good memories. Thank you so much, GW, George Washington University, for a lot of things. As of this Monday, I will be starting at the University of Florida. I thought, since this is a new move, I just thought I'd show like a couple of brief things about like Florida. There's a lot of interesting things gearing up as well, in particular in chips, before we then continue with our exciting discussion about photonic machine intelligence systems. So Florida is actually very well positioned for chips as we know already, and a lot of good companies, good investments, and the university incidentally is right here. And this is like where Gainesville is. So if anyone would like to stop by, you're very welcome. We've got a brand new building. The founder of NVIDIA, you know, speaking of GPUs and accelerators, Chris Malachowski donated quite a bit of money and then the university, of course, pitched in. This is like, I think, a 200 or 250,000 square foot building, and almost one floor is for what I will be directing, which is the Florida Semiconductor Institute. This is not just photonics, this is chips, a lot of things basically on top, so very exciting part. Maybe eventually we can host a workshop there, let's see. So, why not indeed? Lots of things gearing up in Florida, and like our leaders here getting very excited about this too. Chips, ASICs, or application-specific integrated circuits, or ASPICs, as we like to add now, the P for photonics, really based from devices, chips, and ASICs, really enable a lot of disruptive technologies. We see a few words, of course, here. This is a bit of a sort of summary from my team, my group, working on essentially sort of photonic black box accelerators. I will talk about this today. Something I do not talk about today is some sort of like hashing and encryption chips that we build as well. Some reconfigurational approximate computers, some coherent IC machines. Then this work up here more on the photonic convolutional neural networks. However, not just doing it brute force as a speaker yesterday. We actually use the Fourier transformation of an optical lens on a chip for higher synergies. And then, of course, like in photonic tensor core processor. So optical computing and signal processing, including ML, DL, and so on, is really about a link budget analysis. That's really what it is. It's a link budget plus some bit of some maybe nonlinearities, electro-optic or so. So what does it take to, let's say, get to maybe a 10 femtojoule per bit link, if that's maybe a goal? So a couple of years ago, I wrote this paper about essentially looking at the energy efficiency versus speed bandwidth. If you multiply the two, and there's of course our good old conversion errors here down from Mac to Windows, or Windows to Mac, but joule per bit times bit per second basically gives you watt. The third dimension in this plot basically shows how much power you're burning per device. So if you're essentially here right now, let's say let's say hundreds of femtojoule per bit, and you're driving them, let's say, of 10G, you're basically burning 1 milliwatt per device. So, Wim, to your point, essentially, yep, if you have maybe tens of watt on a computer, you can basically integrate 1,000 devices. That's it. If you maybe have hundreds of watt in a beefy accelerator, you can into 10,000 devices. That's it. Not very large scale yet, right? So that's why we need to do something. And so the idea is basically we have a paradigm shift to go from milliwatt based per device to microwatt. So what you need to do is obviously bring the energy per bit down on device level if you want to operate here, and there's a highlighted here, essentially in this, like, let's say roughly 10 or tens of gigabits per second scheme. That then will enable you to get to maybe 10 million or plus components basically on the system. We know this for quite some time. This is borrowed from David Miller here. He's also part of our Explore Center that Ben here talked yesterday about. Most energy is used for communication, not for logic, something we know for a long, long time. And again, AI compute in photonics is nothing else but moving data and having moving data doing like basic performing compute. Yeah? So we are essentially in the communication world here. If you do an interconnect SWOT, so this is a strength, weakness, opportunities, and threats, kind of just like high level here, merit electronics versus optics photonics, you see, okay, from a footprint density point of view, electronics obviously is high, photonics is low. But if you look at the footprint per function, then I would say both are on the order of roughly medium. If you look at the maturity, aka cost, well, electronics was kind of cheap in the past, but now it gets more costly because since the, I don't know what it was, maybe 22 or like nanometer node, it gets more costly actually to scale. And in optics, I would say it's currently still high, but it is with integration, again, it will come down to medium. So essentially, the playing field will eventually be more leveled. And it's limited in electronics really by RC and heat, particularly in 3D HI. HI stands for heterogeneous integration, so that's what we call it, 3D HI these days. It's really limited by heat and capacitance. In optics, DACs, ADCs, and nonlinearity. Highlights in terms of tech, well, it's obviously scalable. The electronics and massive parallelism and also WDM and photonics is definitely interesting. So the desired performance from an interconnect point of view is bandwidth density energy product. Yeah, you see the metric gigabits per millimeter per joule per bit. Okay, so part one. I have three parts today. So part one is about devices, electronic modulators. We need a better modulator. This is a short wish list. Yes, we can increase it more as we discussed yesterday. Certainly, I'd like to focus on the compactness and the efficiency because unlike optical transceivers, if you don't make it very compact, you will not integrate thousands of devices. So it needs to be compact, full stop, and it needs to be efficient, full stop. Fast, sure, and other, integratability and so on, sure. But that's really like key. Of course, modulators are used everywhere, literally right now. If you're streaming this here on YouTube, then you use one of these services. You use some of these modulators literally this very second. You can use it for other RF processing at the edge, data center traffic, again, machine learning right here, maybe other modulating data signals for LiDAR and so on and so forth. So how do we design a better modulator? This is essentially yesterday the same thing of, how can we get a better phase shifter? In my world, I also like to use the modulator. Of course, they come in two flavors, right? They come in EOM and EAM in phase shifting and basically in electro-absorption-based styles. You need to basically have a better material. And if you compare, for instance, lithium niobate against silicon against some material that we are excited about, which is indium tin oxide, you basically see there's a big factor in terms of delta N. What you can have. So you literally need a better material for this. ITO is interesting. You can get a unity strong index change. If you look at this here, this is like the real part, imaginary part. What's also exciting is you actually can tune this quite a lot. This is the carrier concentration. This up here is a Drude model. And the plasma frequency, remember, there's this NC, the carrier concentration. Yeah? So if you basically apply like a gate, for example, you can literally, like a transistor, switch between these various states. Now on the right here, Kramers conic tells you get both delta N and delta kappa, right? So you can make a basic phase shifter, or you can make an electro-absorption modulator based on what kind of carrier concentration you have. Yeah? This is the delta N over delta kappa region. You can be there or there. Now we spent several years on processing this, and did all the mapping and all this metrology and so on. This is like one paper summarizing this. Then we built one device here. This was an electro-absorption modulator on purpose, even squeezing the mode using plasmonics, and intentionally operating at the ENZ point, or epsilon near 0 point, or this very high delta kappa regime. And the performance is essentially, you got an extinction ratio of 1 dB for every micrometer. The loss is roughly similar. You got a 1-to-1 or 2-to-1 ratio with a 4 few volt of bias. But then in this device, we never used actually the delta N. We just said we'd apply against delta N. So can we use both effects synergistically in a kind of like a Kramers chronic style? And you can simply add a little switching island to this. So as opposed to simply absorbing light, you can also deflect it away from this. Yeah? And then with this, we made this device. Actually, it was very low loss. It was a photonic mode, nothing plasmonic. And you get a pretty decent switching, almost like 1 dB per volt roughly. It's broadband, spectrally, no resonator anywhere. It was a kind of interesting device. Then we're switching gears now to phase shifter-based devices. So now we're using intentionally delta N by operating the device here in this lower carrier concentration regime. And this is just like a summary of all this work over the last years. And V pi L, the voltage to get a pi phase shift times the length, is like a figure of merit for these. Of course, there are other merits as well, losses and coupling and so on, but this one is just a particular merit. And if you look at this performance-wise against all the other VERS like 3.5, silicon, lithium niobate, and so on, we are now using the metric volt, V pi volt micrometer, and we are pushing this now then into the tens of volt micrometer regime. In fact, here's a device. I had to gray out a little bit, it's not published, and I had some restrictions, but let me show this one plot on top right on this device. Actually, it is less than, it's basically 0.1 volt peak to peak. It's a directional coupler-like device, but it's not a directional coupler. It actually uses an exceptional switching point between a gain and a loss-based system. It currently operates at 40 gigahertz speed, and if you do the VPI-L, it's 16 volt micrometer. I believe that could be or is the world record right now. Speaking of speed, the device is not limited by a transit carrier time to form the accumulation layer. You see that would be really, really fast, even with a reasonably lousy mobility or medium mobility. It's really RC limited, and if you do a very rough calculation here, you should find basically hundreds plus gigabits per or gigahertz as possible. In fact, you can do a little bit more analysis on this. Maybe if you watch this on YouTube, you can basically simply stop and pause and go through the math and figure out that everything checks out. But there are two ways to operate the device. You can basically end coupling or side coupling it. And then if you run all the numbers, and then you can basically use, this is our typically processed resistivity of these ITO films. You basically get either 62 or, gosh, some few hundred gigahertz based processors. So plenty of speed at the bottom for these devices. But what gets matrix multiplications or neural networks, where we need thousands of these, tens of thousands, millions probably. So to scale, on the right is basically some of these modulators here, so everything is much better if it's smaller. Again, to scale, silicon, lithium niobate, basically for one, lithium or one silicon modulator is roughly you get maybe a tenth or maybe a third of one of the lithium niobates one, and for ITO we can get hundreds up to thousands basically for the same footprint. So very exciting. We also work on detectors, by the way. I just show one example here. We're coming out soon with a very high gain bandwidth product detector integrated in silicon photonics. This is just an earlier work using some emerging materials. Good part. Okay, so let's switch to part 2 then. So again, for part 1, devices are extremely important to do a very efficient link budget analysis. Machine intelligence for ASPICs. Okay, we're all excited about this number. For example, this is from McKinsey, big business, hundreds of billions of dollars in this market. But it comes at a cost, right? You get more performance in terms of, let's say, accuracy, for example, but you're also burning more operations per second. So what can we do? So here's a list of 8 solutions that we believe could be important to focus on. So integration, Mac basically on-the-fly Mac operations, and so on. Let me just walk you through this. So the first thing is, this comes actually from DARPA, is essentially your performance here in green at the bottom really improves if you essentially start integrating electronics and systems better, tighter. Yeah? This is the integration level, if you so will. Here you're going into the 3rd dimensions, and here you're allowing for multiple types of chips. This is essentially think about Lego. Yeah? In the past, we only had one chip, which was gray. And now in the future, we will have multiple little Lego blocks of different colors, and you add them all together to get a very strong performance. What, of course, this community we are excited about is that in the optical domain, we can perform multiply and accumulate very synergistically on electro-optic devices and possibly even passive devices. So again, the analog optical Mac is you have a signal, you have a reconfigurable little device of sorts, the signal goes through, and you simply perform the multiplication. So it's a free multiplication. Yeah? Summation, of course, then the photodetector incoherently. You can also do it coherently if you fan in 2 waveguides, but then of course you have to be phase coherent, obviously, which, as we discussed yesterday, can be rather challenging if you want to do it at every node. But the good news is you have options. You can do it maybe with high-speed MZIs, with ring resonators, with what we call now these PRAMs, photonic random access memories. And I'll give you a quick example of the latest work we had there. So again, if you do the same analysis for hardware, like a SWOT AI analysis, you can find that you can basically electronics and photonics are kind of synergistically to each other. Yeah? Where one is good, other one is challenged. And on the right side, we're adding some of our sort of a contribution to this field now. We're starting to add nonlinearity using electro-optic systems. I would say the memory is, at first order, at least academically solved. You can use these phase change-based materials electrically controlled in these systems now. You can switch them, integrate them. But if you have this heterogeneous system now, you have domain crossings, EO and digital to analog. And that is actually the main challenge right now for the full system. A few years ago, we came up with this photonic tensor core concept. Essentially, it's a matrix vector multiplier that uses WDM to parallelize the system. and then here you like perform the multiplication in an electro-optic system, and then you can add the data in a photodetector, for example, incoherently. So unlike what you may have seen from some of the other work out there, we believe in using actually an amplitude-based system, because other than controlling phase, which is doable, but again detectable is very difficult. Here, doing it in amplitude it's more straightforward. It gives you more stability. WDM is obviously also used for parallelization. Then we look at two different systems, maybe cloud system and edge system, where various electro-optic components can be used. Performance-wise, we are seeing basically several tops per watt with a potential of 100 plus tops per watt at roughly 10 G. Okay, bit resolution is not the highest, so that's something for training one needs to think about. But what we are having as a vision, and I'll show you for examples, is integrating essentially all the functions on one chip. We did 4 generations of scaling of this chip, of this prototype, or this photonic tensor core system. 1x3, here's a 3x3 tensor core, including these detectors. We then integrated in some of the systems these random access memories, and the latest version includes actually a laser that's completely integrated onto the chip as well. And here's just initial bonded device. Of course, you have to make sure you test these chips very carefully. So you map essentially the transfer function of your photodetectors, your weights to the from your devices to the photodetectors and your algorithm very carefully. You can do this weighting and basically find regions of linear performance, such as this box shown over here. Then you can use them and you can do some fun things with it. You can do, of course, image filtering. Here's, for instance, an edge detection. Yes, this work was done during COVID, so you actually see here, George needed a mask. We gave him a mask, using AR and VR and so on. Yeah, image classification, same thing. We all know this. And 90%. So this is a new work now that, let me see, is this video playing by any chance? Oh yeah, here we go. So where we're basically starting to integrate these memories now into larger chips, and we also will start integrating the EIC into these. So essentially we have this looking at this photonic EIC co-packaged system, and in this particular case we're interested in memristive approach for more like heavy edge application, basically, let's say automotive, for example. So here we go. That's underneath the hood. It's essentially in photonic random access memory. We call them PRAMs, electrically controlled. I think Nathan will probably later talk about optically controlled one. We talked to industry, and they were very cautious about doing anything optically controlled. So it needs to really electrically controlled to be, at least from their side, to be integrated. This particular material is GSSE, is an alloy of GST. You notice, so this is again like a linear weight, and the loss in the lower state here is extremely low. So basically, it's so low we cannot even measure with a photodetector. It's like a fraction of a dB. Right now we're working on 4 and 5 bit, but it could also be increased later. Right now we're looking into approaching 10 to the 6 cycles. It's not good enough for industry, to be honest, but it's actually pretty decent. And you can also use a single heater of these little heaters to have multi-bit precision. And yeah, those papers is coming out very shortly in this journal here. If you actually compare SRAM against PIC from a memory read, you actually find roughly a 100x improvement. The SRAM is basically up here, 100 femtojoule per access at basically 3 gig. And if you go through the analysis here, again, there's like link budget for PRAM. Let's say you could run it theoretically at 30 gig easily. That's a 10x here, and then you actually even, including overhead and high bit resolution, you basically burn like 10 femtojoule per access. So you have this roughly this factor of 100x improvement. Next solution that you can have, you see, if you're a board designer, you don't want to worry about photonics. Photonics should fade to the background. You want to have your board, plug your chip in, and be done with it. Yeah? So which of these is photonics? Don't know, don't care. You know, what happens in Vegas stays in Vegas, right? So that's kind of like the idea. So here, for instance, it's like a chip, multiple chips. That maybe this is photonics. Again, don't know, don't care. What we're basically doing in the system now, we're integrating all the components into this photonic tensor core processor, including the laser. The laser is front end here. Right now, that is done in like using this PWB, photonic wire bond, I think was introduced yesterday as well, briefly, and where you use a little wire to connect the laser to the system. Coupling, of course, efficiency need to be still improved. Here's actually like a process flow a little bit. You put the laser there, like you etch and section in, you connect it, and you can actually protect it. The good news is it's actually pretty stable. You can take the chip, drop it on the floor, and it still works, basically. It's actually pretty nice. The next solution is we want to start training not offline in a GPU or CPU. We want to train on the system. So the key point is if you can do that, you can actually train at full bit precision. And that's actually a very important point. Yeah? And you can also do this now with these gigahertz fast systems at very high rates, at least for cloud-based applications. For edge, of course, these PRAMs are much slower. They're like more in the like megahertz range, even slower. Next solution is you need to really start packaging. So in the past, so here's some prototype systems we're building now. I'll give you some details maybe later. But that's really just prototyping. That's really not for real-based systems. But current systems, even in the field, look like this, even in the military, surprisingly. So what we need to do, we need to really put everything like what Wim was talking yesterday about an interposer and put electronics and photonics tighter together, like in this 2.5D style, or we shall do it actually in 3D-HI. Yeah? And these are like two programs, Hellcat and this DARPA SRC JUMP 2.0 program. These are both 3- and 5-year-long programs. Good directions in exploring them. In fact, the last one here, like the DARPA JUMP 2.0 one, called it Chimes, really tries to blur the boundary between what is a chip and what's a package. Those lines should just blur really like very synergistically. And you see a few targets here, basically 1 billion FETs per millimeter squared that we're trying to focus here, roughly 10 terabits per second I/O, 10 or 100 TOPS per watt on these accelerators, and so on. This is actually from our center here. Ben is actually part of it as well. But what's exciting about this is if you actually look at this, so this is all electronics, photonics, co-integrated, right? But if you look at this, these are all things about photonics. So industry really starts to listen to photonics now. This is really exciting, actually. Yeah? And at least, or inversely put, we can contribute to even classical systems as well from our side. I just thought I'd just show you a few examples from the lab about prototyping systems. So generation 1 essentially is just a chip. So you got a chip back, you tape out a chip, you got a chip back, you test it, you have an automated systems, you have electronic, optical I/O, you just get some features about the system, great. But it's not a system yet, it's just a chip, right? But that's basically something you can do. Of course, everything's automated and you can run this and so on and so forth, high speed. The next generation was generation 2. Now, this was exciting for us optical people because this is basically you have now a full computer that you can put on your desk or on your chair or anywhere, right? Of course, it looks very messy. It looks very graduate student style, but at least that was generation 2. All the DACs, ADCs, lasers, photonics, everything is basically on the system, what you see here, but it looks pretty messy still. So here are some details about this. We used the fiber attach initially, but then we said, look, this is not really scalable at all. It's not really stable. We need to do something better. Generation 3 now is we have the photonic, the laser, everything on the chip, and we just have basically high-speed SMAs going to the RF sock. This is the one we just discussed here in a break. This RF sock, programming this actually costs us like months to actually program this. So that's actually, we need to really develop more SDKs, software design kits, to really bring this down. Generation 4 will really be a system where the photonic chip is just part of the accelerator, done. Yeah? So putting it all together, essentially, this is like the roadmap, from chip testing to building systems, putting it all on the chip, and then ultimately, of course, packaging it further. Okay, let me switch gears from the tensor core processor, something actually gets me really excited, which is actually doing convolution operations directly on the chip using Fourier transformation. So machine learning basically requires essentially 80 to 90% of convolution operations. We just happen to use matrix multiplications for it, but we really want convolutions. Yeah? You see, like the FC layer, the fully connect, like the reload, like nonlinearity, it's just a tiny part, effectively. So the gorilla in the room is really basically the convolution unit. Unfortunately, convolutions scale with n to the 4th power. Let's say you have n squared data, it scales with n to the 4th power. If you could go in and out of Fourier transformation, it costs you n squared log n squared. But that's very costly, particularly for large matrices in electronic domains. So that's something where photonics can play a role, because you can basically, the convolution theorem says if you happen to be in the Fourier domain, you can get a convolution as a dot product multiplication. That's much cheaper. Yeah? And again, the lens performs a Fourier transformation, so you can literally use this actually. So here's a chip that you see in this program that we're doing. We had actually a version where we used a free space system, and we didn't use SLMs because SLMs are way too slow. With this, you can never actually get any good performance, but you can actually use DMDs, digital mirror displays. They clock at 10 kilohertz at 2,000 1,000 by 1,000 pixels, so like a million pixel basically, and then you can clock at 10 kilohertz. And then you can also do a fan out. You can process basically like up to 50 different kernels at the same time, so it's actually not too bad. You can do a lot of image processing in parallel. It's like similar to light on, but a little more parallelized, I guess, and a little faster probably. Okay, but the good thing is with this system, if you do like 1,000 by 1,000 matrices, you can actually increase your speed over a GPU by roughly a factor of 8, which is actually exciting. Okay, so then we built this whole system here basically on the chip. And if you compare now the modulation speed for upping these pixels versus the matrix magic size resolution, performance scales orthogonal to these, of course, then here's basically our generation 1 of this, and then this chip that I'm showing you in a second is basically up here. So it only has like basically tens of pixels, but it can clock at basically like at a gigahertz. But it has a long performance improvements over this. This is how the chips look like. Basically, you bring in the light, you modulate the signal onto it. Of course, there are ADCs first. Then here's the lens on the chip. It's a 1D lens. Then you go into the Fourier domain. You can do the filtering, again using MRMs in this case, inverse Fourier transformation detection. This is how the chip looks like. You can do all the calibrations. There's a phase calibration in this point too, which is described down here. We can talk about it later, how that exactly works if you're interested. You can do machine learning on these then. You get a decent performance, MNIST, CFAR, and we ran a whole bunch of others as well. Then we basically starting to build a full system. You need the SRAMs, the DRAMs. We have basically in this case 8 of these tiles. Each of them has 8 groups, 32 MRIs each, and so on and so forth. You can run through some performance projections now. For example, depending on technology, if you have one of these joint transmit collators, 8 or 16 with heterogeneous integrated or monolithic integrated, you get basically for VGG, AlexNet, ResNet, and so on, roughly a performance here in the tens of tops per watt. But this is on average, right? So peak performance is, of course, different. And the A100 88-bit has a peak tops per watt of 2, and these systems have basically tens to up to over 300 tops per watt. So this gives me a lot of hope, actually, that there's a lot of room for scaling in these systems. You can even do more, like basically frames per second, energy delay product analysis, and you find it roughly over state of the art. You find roughly a factor of tens, hundreds, up to maybe 10 to the 3. This is published in this HPSA paper here. Like this is really like the machine learning community. And then you can also basically analyze power, and you find, oh my God, majority of power. I mean, look at this. It's ADCs and DACs, right? You need to cut those down. What you can do, there are a few tricks you can do. You can do front-end buffers. You basically copy your front-end signals, or you basically run the ADCs slower, so you accumulate in temporal domain longer, and thereby you basically save ADC power. It's also kind of interesting. So lots of room for scaling. And then we also designed a digital analog converter in the optical domain, which is pretty interesting, where you basically convert an electrical digital signal to an optical analog signal. This helps you, of course, for high PAM, PAM 8, PAM 16, or higher bit resolutions. And if you look at actually the gigasamples per joule, it's actually pretty decent. And the footprint is not much more than actually electronic chips, so at 8-bit. Okay, so this, looking at the time here, kind of running a bit out. I just thought maybe give you a few more thoughts about applications. If you look at the capability and functions, there's signal rate and then the kernel filter rate. So far, a lot of these papers you've seen out there have only shown very slow kernels. Yeah, all these PRAMs, for example, these random access memories, they're always very slow on the kilohertz or so like range. If you can do this faster, you can basically take some data that's maybe slow, and you can filter this very, very efficiently, and you can do more filtering on this. And what we are now showing in these gigahertz fast systems, you can basically change the filter and process high signals and change the filter quickly. But the applications in which you want to intentionally train them, but you really want to do this like machine learning acceleration, but the other applications, maybe like also Ben talked yesterday, this life learning and experiencing. So as we just experience something in our life, we still learn something, even though I maybe never wanted to become never wanted to learn how to fly an airplane, but if my dad had an airplane and I always as a kid flew with him, then maybe I just learned how to fly an airplane, right? So like something like this. So that is basically fast learning and slow learning, basically good aspects about learning. Okay, so performance-wise, again, for the PTCs, if you look at the giga operations per second per watt, performance scales orthogonal. Here, basically TOPS per watt. Of course, GPUs, FPGAs, and ASICs, of course, perform better. And if you run through some number for cloud and edge systems, essentially you get, again, roughly, like with the current system that we have, roughly like 10 TOPS per watt, which is actually pretty interesting. But again, you're processing 16,000 max, right? So you need that many devices here. Applications, you can do RF fingerprinting. This is something from the Pearl Personal Group here. I think great example, predictive control, deep lidar, anomaly detection. That's something we also work with the intelligence agencies, data routing, a lot of applications for this. So takeaways, so there's system integration density. You need to, integration increases performance. You need to, this basically means you need to put the PIC, the CMOS, laser, and package all in the same system. So right now we started working with global foundries to basically do that in the monolithic style. Again, you can leverage the strength of photonics, and then there is natural process, well, you know, process data in the natural domain. And I would also say for our community, let's actually be also accept support from the chip industry. So I ran out of time. I had maybe a slide about chip market. Long story short, it's big. It's a few $100 billion, and few companies that are basically starting this field now. This is the center we're doing with Ben, essentially together on this brain-inspired work. And just like maybe one slide on this, we are starting to do these like self-learning devices now, where the device essentially can sort of reconfigure itself and thereby possibly even connections to others, maybe using routers or so. So the idea here basically would be, if you look at the cost of learning versus task complexity, if you have one task, okay, and the system is great, like you train it right now, but if you have multiple tasks, the system completely fails. So, or simply put, like a DARPA's lifelong learning program, you know, you train your system, but if you have a second task of the system, it doesn't work. Yeah, so basically, like, don't forget how to walk after you learn how to drive a car, right? So, like, you know how to walk, and eventually, like, when you're 18, you learn how to drive a car, but if you then forget how to work, it would be bad, right? And then very last, maybe, if I just have maybe 1 minute, I thought I'd just give it a little 30 seconds, okay. Since we're in Greece and we are philosophers here, I thought I'd give you maybe my thought on consciousness. Okay, so state of consciousness, I believe, is connected to the attention span of an entity. So imagine it's a trigger event, and then to forecast the options that you have based on this trigger event, should I go left or right, yeah, depends on your state of, like, your attention span. So if you have a longer attention span, which is further reaching into the future, then the task to compute your options, you can be very conscious. If not, you just need to react. It's like a hormonal-driven system. So that's basically where animals are, mostly at least. And that's where our humans are. Interestingly, there are certain human tasks, for instance, like a UPS driver delivering your boxes. Yeah, if that's basically a non-polynomial time-complete problem, if you have 60 items to deliver, it takes 10 years for a computer to process. So human cannot process this either. So there we just say, I think that's the best way to go. And yeah, and then we can discuss essentially like modules on how to map these sort of conscious processing into systems, essentially. Interesting, if you look at the level of automation versus the task uniqueness, then you find some sort of inverse function like this. So if the task is very simple, you can use autopilots, but if the task is very complex, you cannot do this. So you need to do very deliberate action and decision. So of course the question is, how does will and intent come in? And of course you can ask our philosophers to do that. They had some answers to that. For us humans, it would be more something, this is Maslow, I'm not sure whether like this crowd knows this. So why do humans do things? Well, there are all these different levels, and if you go to the very highest level, there might be other items as well to consider. And it's interesting if you put this all into perspective, right? So in the past, we had these physical foundations about chemistry and peptides were formed. Then feedback was added. I'm not sure whether you noticed that, but for instance, a flower was just invented 80 million years ago. It's this very, very new idea of hormones and pheromones and so on. This is basically a way of reinforcement learning in my mind. Now we are living in the age of analyzing everything. So we do cognition and data processing, and maybe that's where we're going. So here I'm offering you a very philosophical idea of maybe the meaning of life for humanity is to accelerate the development of higher level consciousness. Who knows? Some achievements you can pause later on. So modulators, 50G systems, tensor core processors with 110 to 100 TOPS per watt. And like we work on this photo Fourier convolutional ASIC. and also like towards self-configuring devices and systems. So, well, with this, again, thank you, GW, thank you, you, and Florida, here we come. You're always welcome. Thank you.
Thanks, Volker, for this high bandwidth talk. So, if there is a single question, probably we can discuss with Volker during lunch.
Yeah, thank you for the talk. I'm interested in your move to putting lasers on the chip. Mm-hmm. It seems like there are definitely some advantages, but could you comment on the relative intensity noise? Because that is really what limits the bit precision of the optical input channel, especially if you're driving it at 10 gigahertz.
I was kind of like a bit choppy, but I heard you were asking about the integration of the laser, and then about was it the bandwidth?
No, so the relative intensity of noise of the laser and the bandwidth that you're modulating at determines the effective number of bits of your analog channel.
Right.
So,
yeah, I saw your paper that you had exactly about this, like system analysis as well. Yes. So in this particular case, you can let me see. So obviously, like the whole analysis goes like this: like how much power does the laser produce in the first place? What's your coupling losses, and how much nonlinearity or power? How much nonlinearity or how much power can your chip, your waveguide, tolerate before nonlinearities kick in? Right.
Well, actually, so that's shot noise limited, but relative intensity noise limits the frequency at which you can modulate the optical signal. So how long are you integrating over? So if your laser noise is high and you modulate it quickly, then your resolution is low. So what is the relative intensity noise of the
right now
lasers?
we're targeting 6 to 8 bit, but I mean, there's certainly ways to sort of stabilize the laser further with feedback controls. That's something we're currently not doing right now, but I guess it also depends what the because even like a downstream detector needs to needs to resolve it as well. So at least right now we're seeing decent results at 6, 8 possible. Beyond this, I think one needs to definitely look into better stabilize more lasers.
Thanks.
Yeah.
Okay, I think we have to move to the next talk.
Thank you.
Thank you, Volker, again. So the next speaker is Miltiadis Moralis Pegios. He's going to talk about high-speed silicon photonic neuromorphic computing enhanced by hardware-aware deep learning methods.
So, thank you for the invitation and for the nice introduction. I will talk about, I'm Miltiadis Moralis Pegios, and I will talk about our work on high-speed silicon photonic neuromorphic computing. I think after having this talk by Volker and all of the discussion today, I think we all agree that the next wave of computing hardware will be based on neuromorphic architectures, moving on from more specialized computing hardware to this new approach. And several projections that were made by several groups, including ours, during the last years have highlighted the potential of neuromorphic photonics to reach the energy and footprint efficiency targets that right now burden their digital counterparts. And just to put things into a bit of perspective, what we mean by neuromorphic photonics is basically what Sorger described as the matrix vector multiplication. So we have the biological neuron that is mathematically represented by an artificial neural network. Here we have a simple model of a neuron. And we are using photonic components to convey both the information and the mathematical operation in the photonic domain. In this talk, I will focus only on the, let's say, the matrix vector multiplication part, that we call it the linear neuron. One of the main reasons is it's basically the matrix vectors multiplications of a neural network scale much faster than the nonlinear part, while the computational capacity of most neural networks is closely correlated to the number of max it performs. So what we did as a first-level analysis is try to describe a single matrix vector multiplication, trying to understand what are the basic parameters that influence the energy efficiency of a photonic accelerator, and in order to guide us, let's say, in what should be the optimization targets for next-generation neuromorphic computing accelerators. And doing this first-level analysis, we can see that the two main parameters that we need to focus on, that are perhaps intuitive to almost all of us here, is that we need to increase the scale of the network. And this can be effectively translated in a distribution of the optical power and the electrical power that gets consumed at the photonic accelerator ingress and egress. While increasing the baud rate will not only give us the special benefits of photonic computing, that is the bandwidth, but will also increase the matrix utilization, bringing the energy efficiency to lower values. And as perhaps discussed today, there are different ways we can try to scale photonic accelerators. Let's say the first approach is to try to scale them in the space dimension. This is correlated to making bigger chips, and comes with a number of drawbacks, such as the maximum thermal torque, thermal capacity of the chip. But for our perspective, most photonic accelerators right now are insertion loss dominated. So the scaling is very difficult to do and is associated with the current status of the technology. On the other hand, most architectures right now have to pay a penalty with scaling that is correlated to how well we can represent the weight matrix in the photonic domain when we increase the scale. Another way to try is using wavelength division multiplexing as another axis of freedom. However, at this point, most resonant devices require active control that is relatively power-hungry and basically nulls the same argument of high efficiency neuromorphic computing, while the broadband devices that are needed for such systems are not readily available for all silicon photonic foundries. Another approach that is on the first level intuitive is to time multiplex the calculations, basically to unroll in time the operations that the neural network is performing, the photonic neural network. But we think at this point someone should be a little bit cautious, in the sense that right now the scale of photonic neural networks, when compared to the scale of the implementations we have even for simple matrix vector multiplications, they have a discrepancy. And if someone thinks about that, this is a simple example on how many times basically we update the weight matrix during a single calculation of a larger matrix that is broken down in different chunks. This basically gives us a latency penalty that is translated to an energy efficiency penalty when the weight update relationship to the compute rate is very imbalanced. And in the same sense, this at some points makes the notion of, let's say, in-memory computing with very small matrices brings the same inefficiency, because even though the weights are non-volatile, if we have to update the weight matrix a lot of times, paying all the time the energy cost, then it's not easy to find an exact trade-off where it makes sense to go for that approach. So in this sense, what we think is needed is a loss-optimized architecture that, at this point, that can support at the same time high weight update. Now, on the high compute rate barriers, I mean, from a communication perspective, the photonic neuron is much similar to a photonic communication link. And even if we try to, let's say, model it as we did here, we can see that it shares the basic building blocks of a single photonic link and shares, in some aspects, the same limitations. And here we have exemplary some of the signal degradation mechanisms as we traverse the photonic neuron that are related both to the electronic equipment, such as the digital to analog converter and analog to digital converters, and in our case, where we target high compute rate implementations in the tens of gigahertz, most photonic components right now they have, compared to the 10 gigahertz, they have a low bandwidth behavior that will introduce intersymbol interference and further degrade the signal quality. In this sense, one can generalize that in order to increase the compute rate, you have to increase the available bandwidth, but the moment you are increasing the available bandwidth, you are increasing the noise bandwidth, and all these noises scale with the noise bandwidth. So we must find a way to compensate for the analog hardware noise in order to achieve high compute rate photonic neural networks. And let's say these two basic requirements have shaped our approach in photonic neuromorphic computing. On the one hand, we try to come up with a new architecture for matrix vector multiplication. It's the crossbar architecture I will speak later on. And on the other hand, in order to compensate for the analog hardware noise, we try to incorporate methods from the deep learning landscape inside the photonic neural networks. Okay. So, revisiting, let's say, the most prominent approach people have highlighted during the past years for doing coherent neuromorphic photonic processors, it's it uses the SVD decomposition scheme. So we basically need to implement two unitary matrices and a diagonal matrix. And this, of course, comes with a lot of advantages, as we're using a single building block, no crossing, relatively broadband. However, we believe that when scaling to larger circuitries, the MZI loss is cascading. And at the same time, as highlighted here, the differential path loss decreases the quality of the representation of the weight matrix and at the same time increase the calibration complexity, requiring complex tricks and ways to accurately calibrate the photonic matrix. The main takeaway here is we believe that the scaling and performance of such an architecture is heavily dependent on the MZI technology level and, of course, I think discussed by Will very precisely yesterday on the technology choice of the phase shifter. So in order to quantify, let's say, this relationship of the scaling and the insertion loss of the node that we use in such a weight matrix, such a neuromorphic implementation, we plot here the theoretical fidelity upper limit for a Clemens mesh, implementing a unitary transformation, with the x-axis here representing the node loss and the c-axis representing the achieved fidelity. And with the different straight lines, you can see the theoretical projections for different scales for this node loss, while the scatter points highlight the experimental reported values from different groups making this kind of chips during the last years. And I think the key takeaway point from our perspective is that as the node loss or the node attenuation factor increases here, it is very difficult on both the theoretical and the practical level to achieve the high matrix representation. And this has motivated us to introduce a few years ago another architecture is based on an IQ-like algebraic cell. In this case, we are using the properties. We are basically imprinting the information on the electric field in order to allow for a weighted summation at the output of this simple IQ modulator. And without going in further details here, the key takeaway point here is that in order to allow for negative values to be able to be imprinted at the output of this circuit, we introduce a bias term through an extra coherent phase branch that is highlighted there, that allows us to include both positive and negative values in our basic logic building block. Now, scaling the linear neuron can be done both horizontally, concluding to an n by 1 linear neuron, and both horizontally and vertically. That concludes basically the crossbar architecture you can see here. We think it comes with a number of advantages. The first one is that each weight, let's say each constituent of the weight matrix has a single path that allows for one-to-one mapping. The way the cascadability is enforced is on a per column basis. This effectively reduces the calibration complexity from an n square problem in the, let's say, the typical Clemens mesh to an n complexity. While at this architecture, the differential path loss is only evident at a per column basis, allowing fidelity restoration through the use of simple attenuated mechanisms at the column outputs. Here you can see some theoretical projections showcasing that even for high node loss, from a theory perspective view, the crossbar architecture can retain high fidelity. That, as we said, is a metric we use to quantify the quality of the matrix representation. And given that the circuit, each node, as I said before, it has a single path to the output, the circuit loss scales linearly with the node loss, allowing in this way to implement high dimensionality layouts without getting prohibitive values of insertion loss, as would be the case for Clemens implementation. That is intuitive, imagining that you can cascade, you can't really cascade high loss phase shifters in the Clemens mesh. After a certain scale, the loss will explode pretty fast. And finally, using this scheme, that's basically not using the U2 algebra, but is it supports the implementation of any matrix we want without the requirement of using two unitary matrices and the diagonal matrix, making easier the translation from the photonic neural network domain to the photonic chip. And with that in mind, we fabricated and designed, in collaboration with IMEC, a 4x4 prototype of our crossbar architecture. You can see a microscope photo of it here. This single prototype utilizes electroabsorption modulators that are very high bandwidth components for both input and weight imprinting, while it is boarded on a specially designed PCB board, not shown here, to facilitate seamless access to its electrical controls. The first thing we do is try to see if the insertion loss of the photonic chip matched our theoretical predictions based on the foundry values that we got from IMEC, and it seemed to have only a small deviation, highlighting that using this kind of technology, we can scale to relatively low scales, but with a very high node loss that at this point reached around 5 dB. Now, I will talk a little bit about how we calibrated the device. As mentioned, given the nature of the layout, each column has an independent, the columns are independent, and it's only 4 constituent optical paths that get summated in this case at the output. And you can see the mathematical relations here that describes the attenuation originating from each electroabsorption modulator in each node, and the insertion loss of the different optical paths. And so, as a first step, what we did is we got from IMEC a standalone electroabsorption modulator with the same properties, and we measured its optical and electrical response. And we tried to model the whole column. In this case, it was the first column, using these values. And what we can see here in the top right graph is that, of course, we expected this behavior, that given the fabrication variations, it is not, there is an introduced error when you assume that all the electroabsorption modulators and the optical paths that introduce different coupling ratios and stuff like that have the same properties. So in order to circumvent this, we basically used the least mean square method and the training data set to be able to approximate the coefficients of the insertion loss and the extinction ratio equation for each node. And in this way, we were able to reduce the programming error in absolute terms from around 4% to less than 1%. The next step was to implement 10,000 arbitrary linear transformations on the photonic matrix. You can see on the left part of the graph a histogram of 200 of these values for each different column output. One can easily, let's say, discern that the fourth column has a big differential loss in comparison with the other. This was due to a fabrication error at the grating coupler of the fourth column. And as discussed before, what we did then, use attenuators at the columns outputs in order to restore the fidelity, basically realign the output power for each column. And in combination with the calibration procedure that discussed before, we were able to reach a fidelity that is in line with our theoretical projection and almost 100%. And taking a step back to the previous graph, we can see that, let's say, our architecture fulfilled its purpose, in a sense. That was to break the symmetry between the achieved fidelity and the imposed node loss, showcasing that we can make photonic accelerators that can support a high loss, and this, unfortunately, is related to high bandwidth nodes and achieve very high fidelity that can be transformed in the photonic neural network domain in high accuracy in the representation of the weight matrix. Okay, now moving on to the deep learning methods. I think there is a talk from our collaborator, Anastasios Stefas, that will get in a little bit of more detail, but I will explain a little bit our approach and our experimental validation. So for the hardware-aware deep learning, we followed a twofold approach. The one deals with retraining of the neural network, trying to bring in the neural network training, the idiosyncrasy of the analog photonic hardware. And the other approach begins from the realization that retraining neural networks and as a per-cases basis, it's okay, but when we think about if we want to use photonic accelerators for the tasks that are very expensive to train, is not really the way to go. So perhaps we can find some other ways to adapt around the specific capabilities of the photonic network. So in this case, just in order to a brief overview, we have again the photonic action. The ideal output would be the weighted summation. Here we model some of the noise degradation mechanism as Gaussian noise. This assumption is relatively valid for most of them, for typical situations on a photonic link, including the quantization noise, the rim noise, thermal noise, and shot noise. And this basically distorts the weighted summation. And again, when considering high compute rates, the frequency response of the photonic accelerator will probably have a low pass response as compared to the required bandwidth for accurate representation. So we model it as a low pass filter. In this case, that distorts the weighted summation output. So in order to showcase some of these functionalities, the first one was bandwidth-aware training, where we try to incorporate the bandwidth of the photonic system in the neural network training. We used this chip. This is basically a 4x1 crossbar that was fabricated in collaboration with the University of Southampton. In this case, we used traveling wave Mach-Zehnder modulators for input imprinting and heaters for weight imprinting. The procedure here was to excite a pilot signal that would allow us to approximate the transfer function of the whole photonic neural network. And then we went back to the neural network design and incorporating a specially designed module that basically performs FFT and reverse FFT and allows incorporation of this specific frequency response into the neural network training. And you can see in the graph at the top bottom right, the results for the blue one is the baseline training and the red one is the bandwidth-aware training. And we showed, and of course the scatter points are the experimentally derived performance, and we can see that we have, for example, for 32 gigamax, an improvement in accuracy of around 70%, showcasing that we basically can extend the performance of our photonic components when introducing bandwidth-aware training. The second approach was try to take this Gaussian noise quality that was mentioned before, that basically sums in a single coefficient the noise contributions of the photonic network, and again go back to the neural network and introduce a module that specifically is trained for a given number of Gaussian noise based on the experimental measurement. And you can see the results here for 5 and 10 gigabaud. Again, the blue lines are the baseline approach, and the red line is the the noise-aware training system. And while we plotted the x-axis to ease, let's say, the presentation of the simulation results, the inference normalized to 0 to 1, the noise inference that we inject into the system, while the scatter plots are the experimental values. What we can see here is, of course, we can intuitively see that there's a performance improvement when using the noise-aware training. And there are two ways, basically, to interpret this result. One is that if we have a fixed noise level, we can get an accuracy improvement. The other way someone can look at that, given that basically the x-axis is correlated with the input power to the photodiode. As for this specific photonic link, it has, let's say, not a linear, but it has a monotonous relationship. So we can, for a given accuracy value, transform let's say, this gain from the noise-aware training in an optical power budget gain for the photonic accelerator. Okay. Going back to the deep learning regime, the other approach which used begins from the realization that is well known, that is very high to achieve high bit resolution in photonic neural networks when you are targeting tens of gigahertz of operating speed. That is conjoined with the other reality that is very high cost to retrain neural networks, especially when we are speaking not for a toy example that we illustrate, but for a real application. And what we propose here is we begin again with a realization from the digital world that, let's say, the noise robustness across a neural network is not uniform across its layers. This is basically the black curve of the graph at the top, bottom left. So we can see that for implementing different neural networks and putting a threshold on the accuracy, there are different bit resolution requirements. That's the first observation. And the next observation is that the required equivalent in, let's say, matrix operations or millions of max, it differs across the neural network. So there is an opportunity here to vary the operational rate of our photonic accelerator based on the requirements in bit resolution, and in this way reduce the execution time. So our second step was basically to try to correlate. Okay, this is more, let's say, for ideal systems. We'll get to the modeling of our real system in the next slide. But the idea here is to find a way to correlate the compute rate with the achieved bit precision of the photonic neural network versus different other parameters here. For example, we plot versus the insertion loss of the total accelerator. And then here we have an example in the software domain when we showcase that this exactly approach that varies the compute rate across the layers of the neural network can reduce significantly the execution time up to 85% when compared to, let's say, to a baseline scenario when we use the same bit resolution capabilities across the whole neural network. And in order to experimentally validate this approach, we used a previous chip that we have developed with IMEC, that's basically a 2x1 neuron, and build a classifier of the iris dataset using this relatively simple neural network. And as discussed before, there are two steps. The first step is the analysis of the noise robustness of the layers of the neural network, and the second step is the correlation of the operational compute rate and the achieved bit resolution of the accelerator. And so what we did experimentally is run these two different layers using different compute rates from 2 to 16 and 50 gigahertz. And what we can see from the experimental results are that we have a relatively good match between the experimental behavior and our model. While in this case, varying the precision across the layers can lead to a reduction of the execution time around 55%. Okay, just a quick mention here. This, let's say, was built on the backbone of this tiled matrix multiplication that we discussed before, that we are basically unrolling the operations of the matrix vector multiplicator in time. And that is something we can do relatively fast by leveraging the 50G bandwidth of both the input and the weight modulators. And finally, we'll speak a little bit about one of the applications that we think it's interesting for such kind of photonic neuromorphic processors. So in this case, the application is a denial of service attack identification. So we're basically having an attacker that is using a number of bots to cause a denial of service in a network operator. And let's say what's the baseline approach right now from a network vendor is to use a converged model of an accelerator and a network card that monitors the traffic using AI models and tries to prevent, let's say, take measures before these attacks take place. However, the processing speed is rather limited by the electronic processor speed of the GPU. So what we'd propose here, in collaboration with our partners from NVIDIA, is to have a look-aside photonic accelerator that can operate at the tens of gigahertz, and in this sense be able to monitor the incoming traffic close to its line rate. And so for this specific example, we used telemetry data that was provided, of course, by our partner to train a photonic neural network to identify the reconnaissance attacks that is basically a precursor of the DDoS attack. And you can see here the experimental derived values. Here, of course, we use the Cohen's kappa score. It's an accuracy metric that is used for biased data sets when we don't have, let's say, uniform distribution about the classes we are classifying. And we can see that it has still sufficient values even for 50 gigabots, showcasing that we can use the system for such kind of tasks that we think are very well suited. And with that, I would like to conclude my talk, and of course, I couldn't go without mentioning a number of the team back in Thessaloniki. That includes basically two groups, one that is more focused on photonics, you can see on the first line, and the second group is our AI collaborators that made this work happen. So thank you for your attention.
Thanks a lot. There is one question for the speaker. So I have a question for you. This crossbar architecture, which is very interesting, how much can you scale it? I mean, you have shown 4x4. What is the uppermost, let's say, dimension you can anticipate for this?
So it basically depends on the choice of the phase shifter. In this case, we project that you could scale, given some, let's say, optimal fabrication variations of up to 64 by 64 when using electroabsorption modulators that are relatively high loss. And if we consider that there is no, let's say, progress in the technology in the next year. So.
Thanks a lot. So let's thank the speaker again. And the last but not least, as we usually say, is Nathan Youngblood. He's going to talk about computational photonic crossbar arrays for scalable and efficient matrix operations.
Okay, thank you very much for the invitation to be here. I'll be talking about computational crossbar arrays that are different in design from the talk that we just heard. So let's dive right into it. So just to motivate the talk, I know a lot of people have been presenting on the need for doing machine learning training using AI, or using photonic AI. But I would also like to highlight that for emerging AI services in the cloud, inference is also very important. And inference usually is easier to do with photonics because you require a lot lower precision, and you still have this significant deficiency between the top performing AI models that are growing in the amount of operations that they need per month compared to the efficiency of current electrical hardware. So this is a big demand, a big need in the marketplace that photonics can address. But there's also equally a growing demand for ultra low latency hardware. So here I have a couple of examples. We heard a really nice example of compensation, very nice talks about nonlinear compensation and linear compensation in fiber networks, real-time processing of high-resolution video, fast financial decision-making, predictive latency, or predictive control, predictive targeting of supersonic aircraft. So anytime you have the case where the process value of the data is decreasing with increasing time to get the computational result, that could be an option for photonics, where it can make an immediate impact in the market over what we can do with electronics. For example, if you're paying an extra $70 to run your photonic network to do fast financial decision making, you don't really care if you're trading millions of dollars of data. So there are many optical approaches to these AI challenges. They all share the ability to do low energy linear transformations, have the option of very high bandwidth with wavelength division multiplexing, fast modulation speeds, low loss interconnects, so you're not spending money or energy to transfer data across these photonic waveguides. But scalability is a challenge that's come up a lot in this conference, especially to non-trivial computations. So expanding beyond what we can do and how many parameters we can necessarily fit on our photonic circuit. Tolerance to device variability, and of course power consumption of electro-optic conversions and digital to analog conversions as well. So the unique contribution that my group has, and when I was working as a postdoc in Harish Bhaskaran's group, which is where a lot of this work started, is to combine high bandwidth photonic interconnects with non-volatile materials to really try to do photonic compute in memory in these memory cells. So you can take these waveguides, put materials on them, phase change materials. GST is a common example where you can change between the amorphous and crystalline state and encode information in a continuum of levels between, excuse me, a continuum of levels between low transmission and a high transmission state. So that encodes values between 0 and 1. And if you apply this to the weights of a neural network, you can think about having a two-dimensional crossbar array structure where you input optical signals at these inputs, and then at the speed at which you can modulate and detect, you get the result. So low latency is the proposed target. And if you can stack multiple layers together, then you can think about implementing a deep neural network. So in order to do this, we need cells that do multiply accumulate operations using these materials. And the recipe for all optical multiplication is you first set the weight of these phase change materials, so the transmission state, using an optical pulse. Electrical pulse has also been shown. You can send a second pulse that is lower than the switching threshold of this material, and so that's proportional to number B. And since transmission is simply T times the input optical power, you get C is equal to A times B. And you can combine these to do dot products. So this is an example, early example of work that I did with Carlos, who's now at University of Maryland, where we combine two of these cells in parallel and then use sum on these outputs. Note this factor of 2 there. It'll come up later. So you can also apply this to two-dimensional arrays. So if you have two by 2 edge detection kernels. You can take those, stretch those out into a column, and recast this as a 4x4 photonic matrix. You can encode pixel values in these inputs, sum them up on photodetectors, and then you get the experimental output relative to, as you scan over the pixels of this input image. So this is nice, but the real power comes when you start scaling in frequency dimension too. So not only are you leveraging spatial dimension with this 2-dimensional crossbar array, you have a 3rd dimension, which is frequency space. So you can simultaneously send 2 input vectors simultaneously. And as long as you have filtering at the output and you double the number of modulators at the input, you can get twice the computational throughput in the same computing core. So this is actually a really powerful technique, and we demonstrated that we could do this up to 4 wavelengths channels, so a total of 16 different frequency channels using integrated photonic microcomb supplied by Tobias's group. So the nice thing about using these passive structures instead of resonant structures, there's a trade-off, of course, but one of the nice things is that you have very high bandwidth. So you're not limited by the resonance, the photon lifetime in the cavity, and we showed that basically if you send these through, the inputs are modulated at very high speeds, and you can show that there's no decay basically because of photon lifetime. You can show good precision. So these are the results of dot products, so a single column, for example, from a 9x4 photonic matrix. And then if you extrapolate, this is always dangerous to do, but if you extrapolate and say that you can operate at 12 gigahertz, you have a 32x32 photonic matrix, you have a pretty high density. If we normalize by the amount of area, if you can scale in terms of frequency space and scale in terms of modulation speed, and you're doing all these operations in a single clock cycle, you now have a pretty competitive architecture. So comparing to Google and NVIDIA, you can see that there's a significant change in the amount of compute density if you can operate these at high speeds. Should point out, Jason also showed this, that these materials can be switched electrically as well. So this is an example of an electrically programmable in-memory photonic dot product. The previous example, as Volker had mentioned, was switched using optics, but you can also switch electrically. Easy to show very beautiful pictures of fabricated chips from other foundries and sources, and an entirely different story to actually demonstrate useful computation on these. So we're still working on this, but this is a future direction slide. So I mentioned that there are some challenges switching these electrically. There's a couple of challenges which I'll get into. Uniform switching area. So you can see that this is an example of where we were able to crystallize the center, but not the outside of this pixel. This is a relatively large pixel. This is over 100 by 100 micron in size. There's ways of addressing that. You can kind of tailor the size of your heater or the doping area of your heater to get a kind of a nice uniform profile across the phase change material. So that is relatively easy to address. The more significant challenge is this rapid area switching. So crystallizing these materials is easy. You just heat it up above the crystallization temperature and let it crystallize. Melting them, so amorphizing them, switching them back to the highly transmissive state is challenging because you need to go above the melting temperature, which is a high temperature, and you need to be able to quench these materials below the crystallization temperature relatively quickly. So if you have a slower phase change material, like SBSE or GSS or some of those other materials, then this becomes a bit easier, and but the switching time goes up. So you also have challenges of repeatable deterministic switching, and maybe some sort of combination of the switching time and the heating profile could address some of these things. But when you actually fabricate these devices, if you did a simulation on this, you wouldn't expect this area not to be fully switched, like what's going on there. So one of the things that my group has been working on at University of Pittsburgh is doing both device level simulations and also direct thermal measurements of how hot these materials are actually getting to. So this is an example of some recent works that we have on this topic, and I'll just go into this archive paper because it hasn't been published yet, and so it's maybe more interesting. So in this case, what we're doing is we're actually taking the thermal optic effect of the phase change material to determine the local temperatures. So we looked at this on 2 different heaters, a metal heater, so platinum, on a silicon substrate, and a SOI. So we have a thin layer of silicon that's been N-doped. And by measuring the pixel temperature, or sorry, the pixel reflection, and correlating that to temperature, we can actually get steady state heating efficiency curves. But since we're doing this optically, we can also do dynamic responses. So you can see we have a COMSOL model of this silicon microheater, and the experimental results are a bit noisy, but you can see that there's a clear trend that's followed and a good agreement between the COMSOL simulations and the experimental model. And here is actually a spatial profile, because we can actually raster the stage underneath the laser beam and figure out, where is it heating up locally. And since we have both spatial and time dependence, we can actually create movies, and we can watch heating and cooling in real time and see, oh, something's kind of funny is happening. There's a little bit of asymmetry in this, and there's a little bit more heating in this area. This is an actually fabricated device, and this is the actual temperature that the phase change material is getting to. Overall, there's generally good agreement between the simulation, but when you start looking at the differences, that can give you information when you're designing your devices. Okay. So going back to this crossbar array concept, with this incoherent matrix vector multiplier, you are putting in different wavelengths. You can do wavelength division multiplexing, so you can scale in frequency space. The challenge is this recombination. So you can do fan out. You always have fan out loss regardless of your platform, but fan in loss is something that you can't avoid if you have resonant recombination. So micro rings, for example, and Paul Prucknell's group with their broadcast and weight, or if you're using a coherent MZI mesh, for example. We can turn this kind of concept on its head, and this is very much directly inspired by Ryan Hammerly's seminal paper, where you time multiplex these inputs, and now you're interfering them on this 2D array. So we can take inputs, take 2 matrices, take the column and row matrices of A and B, multiplex them in time, and then at each of these intersections we can take and do homodyne detection and get the dot product between these 2 vectors at this point in space. You're sacrificing readout speed, but you gain in terms of compute efficiency and are able to scale to larger areas. So yes, this is inspired by Ryan's work, and we heard a bit about that yesterday in his great talk. So one of the advantages, and Ryan talked about this a little bit, one of the advantages of doing, I say fixed weight, but weight stationary versus output stationary is the same concept is being described here. If you're trying to do a large-scale matrix like you might want to do for a neural network, you would have to reprogram this array multiple times in order to just get this sub-matrix output. And then you have to do that again and again and again. That runs into issues with endurance of your memory cell, and also switching speed and switching energy, and it becomes quite inefficient. However, you move to a time-multiplexed architecture, you can stretch this out in time, and now the only part that is dependent on the dimensions of your physical hardware, photonic hardware, is the size of your crossbar array, which is this K dimension. And so by integrating over time on an image sensor, for example, and you modulate the inputs, these 2 inputs, A and B, you get this submatrix out. That has several advantages. First of all, it requires multi-megahertz ADCs instead of multi-gigahertz ADCs. So that saves you in terms of energy running these ADCs. But it also saves you in terms of bit resolution. So this is one of the examples of why you can get to few or sub photon per Mac, is because you're integrating over a long period of time. So your effective, your frequency, your readout frequency is much, much lower than it is in this case. So we've done some calculations in this paper to show that the energy is much more efficient. This is not including, caveat this, for all the optical comparisons, this is not including data transfer. So it's not a really truthfully fair comparison against these digital architectures, but this is just a reference guide for the eye, so to speak. But as soon as you exceed the matrix dimension of your physical photonic hardware, your latency goes way up because of programming latency, and your energy efficiency goes way down because it costs time to reconfigure and energy to reconfigure your weights. So we're working on trying to actually implement this time multiplex on-chip idea. This is an example of just a single dot product unit cell to kind of test this idea. So we're doing simple binary input signals where we're changing the phase relative to these two inputs in modulator A and B. If you integrate over time, you get a final result that is like within 3% of the actual result over 64 time steps. So we're integrating over time to get this this homodyne signal, and you get shot noise limited shot noise limited detection at the output too, which is nice. This system is fully coherent, so that gives you the option of moving to the complex plane. So these are examples of measured values of encoding in the complex plane on the unit circle and changing the amplitude and phase. That's how you go around this complex plane. The advantage of doing this with the same amount of noise, the same amount of SNR, you gain significantly in the number of bits that you can encode. So now there's been a lot of talk at this conference about doing computation in the complex plane, and there's a lot of advantage of doing that. You need a coherent system to do that. So to actually read this out in a scalable manner and prove the concept works, we fabricated a 2D array. So this is the same type of crossbar array for the phase change materials, except it's modified where each of these unit cells now has this 2x2 multimode interferometer and then 2 output grading couplers. And you can see here, as we're scanning the wavelength, so we're not actually doing useful computation, but as we're scanning the wavelength, you can see different output waveguide, output grading couplers light up. And so by taking the difference in these two images, so you'd say this is possibly the positive and this is the negative, and you take the difference between these two areas of pixels, you can do computation, and of course you're summing up over time. This is, by the way, for only a few microwatts of optical power, so it can be quite efficient. Yeah, so this is just the same measurement when the grading couplers are in focus and you're not illuminating the optical circuit as well. Okay, so moving on to optimizing AI models. So let's say that we're able to actually make photonic circuits that are scalable to machine learning models of interest. There are a lot of different architectures out there, and if you're going to go and simulate the physics of all of this, it would take a long time and you wouldn't get anywhere. If you try to do things digitally and just assume that these are perfect digital representations of your machine learning layers, your deep learning layers, that doesn't work either because you're not taking into account noise and analog signals and stuff. So we've come up with an intermediate framework where you can include the effects of noise, but use the PyTorch framework, which people are familiar with and is constantly being updated and features are being added to it. So my student Viv Swan has been working on analog VNN. It's just been recently published. And the idea is that we just drop in these effectively digital layers that represent analog effects. So you've got input, you're normalizing your input between 0 and 1, obviously. You have to reduce precision. You add noise based on maybe your driver, your shot noise, your relative intensity noise of your laser, et cetera. And then you get the output that's going into your convolutional layer here is something that's representative of your optical signal. This is all in the digital domain, so this is all just simulation. And then you might have some attenuation after your neural network, renormalize, maybe add some extra noise and reduce precision. Then you have your digital outputs because you have your analog to digital converter. So all these are just drop-in layers. Like you can convert them or switch them around however you like based on your hardware. So we've kind of abstracted out the hardware and just try to focus on the effects on the actual signal. The nice thing about this is it adds maybe 3% overhead to PyTorch now that this has been optimized. So we can model, we showed that we modeled, a 9-layer analog neural network with, millions of parameters. Or I guess this one only had 2 million parameters, but since then we've done ResNet 50 models with 34 layers and stuff, and it works just fine. some interesting things is that you can now optimize hyperparameters. So you can see which activation classes, for example, work well with different amounts of noise. You can also see the effects of noise on the weights versus the signal. And what we found is that it's very important to have accurate weights rather than accurate input signals. And then finally, kind of a last thing is I'd like to highlight this recent review article that we did on survey of non-volatile integrated photonic memories. So there's you know, PCMs, MEMS, charge trapping, et cetera. And this field is rapidly growing. We need something that has high storage density, low switching energy, high switching speed, and high extinction ratio in order to encode lots of bits. And there's been some really nice work coming out of HP labs where they demonstrated an optoelectronic memristor that can basically has two bistable state, but I think that there's a lot of potential for this. It's especially low switching energy and high speed, which is important. Okay, so to conclude my talk, I would like to do this very scientific analysis of history where we take and compare analog with computation, or audio with computation. So evolution of audio now is back to hipster vinyls and vacuum tubes. So this is being Greece. This is a very important contribution to computing. So it used to be analog, and now we're back to analog because we've kind of reached the bounds of what digital can do in some domains. So maybe there's a future for both in the coming years. With that, I'd like to thank my group. Nick did the photonic mapping, or the thermal mapping. Sadra's working on the coherent crossbar array, and Vivswan does all the programming and stuff for analog VNN and the entire lab. So, and with that, are there any questions?
Thanks a lot for this nice presentation. Do we have any questions?
Thanks a lot, Nathan, for this very nice talk. Coming to the frequency multiplexing that you applied on your PCM-based crossbar. Mm-hmm. So more or less, you applied frequency multiplexing in order to bring a new dimension, mm-hmm. since you already utilized the wavelengths for a different purpose. So every wavelength had to carry a certain action. So my question here has to do with the whether we have tried to use these PCM weights within a coherent layout, so as to use just a single wavelength and then utilize them wavelength dimension for increasing the degrees.
Yeah, so Sajed Mosaini at UW has a nice theory paper on that idea. The challenge is that you get strong both phase and amplitude modulation. So if you had something that is purely amplitude modulation, that would be very interesting. Like the ITO memory cells, if we can improve the extinction ratio, that would be quite an interesting way to go. I guess for your case, you get like 6 dB of extinction ratio for the EOM, or electro-absorptive modulators?
Yes, 4 to 6 dB, depending on the voltage.
Okay, yeah, so if you can do purely amplitude modulation, then it can work. For the incoherent, so maybe for coherent, PCMs might be more suited for, like maybe a coherent mesh, MZI mesh or something like that. I'm not exactly sure.
But don't you have also PCM structures where only the phase is changing?
Yeah, yeah. So Carlos had a nice paper that was recently published. It was 11 microns, and you get a pi phase shift with 0.04 dB of loss or something like that per micron, which is pretty good. So that's extremely compact.
Thanks a lot.
Yeah. Cyclability is like the thing that we're working to improve with that.
And a last question, if there is any.
So I was wondering, these phase change memory devices, they rely on essentially melting the material, and if you want to change the state of them. So in say futuristic applications where you want to do online lifelong learning, you want to continually update these weights, do you think it's feasible and to have an energy efficient implementation of that with these non-volatile memories, or this phase change specifically memories, or?
Yeah, so it entirely depends on how much you're updating, right? So depending on the application, if you need to update, every millisecond or something like that, it's probably not efficient. If it's like, you accumulate data throughout the day and then you update, then it would be efficient. So I think there are it needs to be very application specific in that case. And in terms of, outstanding challenges in the phase change community are lowering the melting temperature, improving, phase modulation without absorption, and cyclability. But the material itself has been demonstrated to be quite cyclable in smaller scales. So it's maybe a material science problem.
All right, thanks.
Okay, let's thank all the speakers again of this session. We are having an hour for our lunch, so we'll meet here in an hour from now, okay?
Όχι, αυτό είναι δικό μου. Everything okay? Great. Okay, so I think we are ready then to start. So we have, in this session, it was supposed to have 3 talks, but unfortunately, Bert Hofrein from IBM had to cancel the trip. Actually, I did not get the clearance from IBM to travel here. So it will be, we'll have 2 talks in the session finally. So the first one will be given by my colleague, Professor Anastasios or Tassos Tefas, from Aristotle University of Thessaloniki, on open deep learning tools for neuromorphic computing.
So, thank you. I would like to thank the organizers for inviting me here, also my collaborators from my team, Manos and Nikos, and of course the WinFOS team led by Nikos, also so the talk by Miltos and the rest of the researchers there. So, I will talk about deep learning and tools for neuromorphic computing, and especially what we have done on trying to build tools for photonic activation functions, for photonic implementations, how we have tried to compensate for noise, low precision, and also to imply non-negativity on our training pipelines. So you already heard a lot about how deep learning, which is actually the leading force of AI, changing the era of new applications on robotics and NLP, but also on many other applications. Of course, to do so, we need powerful hardware, but also open libraries. In the community of machine learning, open tools is one of the major driving forces because almost everything is available. Unfortunately, OpenAI in the last months with ChatGPT changed this by providing closed, let's say, architectures. And deep learning becomes larger and more complex, so we need computational power, energy, and we have cost for developing, optimizing, making more ethical, more accurate. And of course, all these renders the applications of deep learning and also the development of new methodologies as things become even more complex. Maybe an elite, let's say, situation where only some specific companies and universities can have access to such large infrastructure. And also there is another problem that in many cases we need collaboration between different communities, like also for me in that case, between photonics community and deep learning community, or between the robotics community and deep learning community, when we need collaboration and a common language and understanding between the groups that are collaborating, and we need open tools that everyone will be able to use and have a common sense on what it means to have, let's say, a photonic neural network, let's say, because this is what we hear all day long and yesterday also. And indeed, there is a steep learning curve for learning how to optimize, train, and design neural networks. So it's not something that it's easy, and you can say to a student that works on photonics, okay, take this neural network and train it and make it work. We read all these papers and everything seems to work. Now we have seen a lot of figures how the accuracy of these networks increases, but also how the number of parameters increases. You can see here, for example, on computer vision tasks, but now have 3 orders of magnitude, even larger networks in the range of billions of parameters for NLP, for example. So how this is related to, for example, photonic neural networks? Are we able, or even thinking, having networks, photonic neural networks that are going to be able to train billions of parameters? And do we actually need all these parameters for the applications? Maybe this is overshooting to have billions of parameters, and we can do our work with only 1,000, or let's say a few hundreds of parameters. Then we become relevant, then we can have applications. And these are also, in many cases, it's true that we over-parameterize our algorithms. But in order to make them work based on the algorithms that we now have available, we need, of course, specialized hardware, accelerators, and beyond GPU and TPUs, of course, now we're talking about neuromorphic photonics and how this can accelerate what we already do in deep learning, and for which applications these neuromorphic photonic hardware becomes even more relevant. And we need that because the footprint of current technologies, it's not something we are happy for. Indeed, the cost of just training the algorithms that are needed for a high-end, let's say, conference paper on deep learning is estimated something for a lab on around 30,000 euros. I have to pay on computational costs in order to optimize the architecture and the algorithms, and you understand that this is indeed something that keeps, let's say, in some cases, the research back. And now with all this buzz on the natural language processing NLPs like GPT-3, GPT-4, and so on, this even becomes more relevant, since in that case, we need multiple GPUs and infrastructure that is not available in many places in the world. Actually, a few companies now are able to train these huge models, to have also access to the hardware, but also access to the data needed for that work. And so we are now talking about neuromorphic photonics, and if indeed we can use light to train machine learning algorithms, and what kind of machine learning algorithms are we only constrained to small networks with one layer or two, with few parameters on the few inputs, dimensionality that is, let's say, tens or a few hundreds, or we can scale up. And we had indeed a lot of talks today and that tried to answer to these questions. We know all that we have specific advantages if we use photonics, and we have high frequency, bandwidth, massive parallelism. So we want to use all these features. Because we know that if we are able to come up with clever solutions, then we will benefit, and the entire topic of deep learning will benefit from that. But there are also limitations, and almost all talks were about how to deal with these limitations, and we, in our work, we tried also to handle some of these limitations, like the difficulty to support conventional deep learning, and starting by the conventional activation functions that we use on the electronic, let's say, domain with GPUs, and that we have noise on whatever we do that it's inherent, and we cannot actually say that, okay, we will leave it out of the equation. The low bitrate resolution, it has been discussed also in some cases, and also in our collaboration, we also considering how we can for example, work with only non-negative weights, so to become even more, to come even closer to what is easier implemented on the photonic domain. So we have tried to deal with all these training challenges, and starting just to explain why these are important. You know, neural networks are few decades already deployed and are available, and the theory is there, but we're not able to train reliable deep learning models. And why is that? In a simple example in this slide, we can see that, for example, if you say that I will use a sigmoid activation function, then sigmoid activation works for a shallow network, so you have 2, 3, 4 layers, it might work. When you go deeper and deeper, suddenly it doesn't work. So you cannot do much to make it work. It took decades, and we were not successful in making sigmoid activation to work in deep networks. Suddenly, ReLU and different activation function even more simpler. So a simpler nonlinearity actually make things easier. So this maybe comes in contrast with the mentality of some of us that will say that, okay, we need more nonlinearity. This bigger nonlinearity, in many cases, since it's not trainable in many cases, cannot solve complex problems. So another idea is maybe if we can go to simpler nonlinearities and how this is feasible in photonics, if it's feasible. But you can see here that indeed choosing the activation function in a clever way might solve the issues that we all have. Why is that? Because the activation function is what is used in backpropagating the errors. When you're trying to train your algorithms, you need to use an activation function that's differentiable, and the derivative is what propagates errors. So if you have an activation function that vanishes, then actually you cannot backpropagate errors, then the network is not trained, and then you see no improvement in what you had in mind that you will be able to solve with deep learning. And you can see here also an example where not only the nature of the activation function, the derivative of the activation function, but the actual initialization of the network plays also a significant role. So it's a non-convex optimization problem, the training of a neural network. And you cannot say that, okay, I can start with whatever weights I want and everything will converge and the network will perform as it is like. So the initialization of the networks is indeed very crucial in many cases. The phenomenon that we are trying to deal with is the exploding gradient. So when we're trying to make things better, the gradients that we're using to update the weights might go to infinity, or also they are might go to 0, to vanish. So we're trying to deal with this by using clipping or trying to place the neurons in a point on the optimization plane where they will not be easily going to 0. The derivatives does not usually vanish. Coming now to what we have in photonics. When we started our collaboration with the WinFos group, so it's a collaboration between the machine learning and the photonics group, we said, okay, what do you have available in photonics? So to see if we can use these activation functions to train our algorithms. So starting with activation functions that either are there or that can be approximated with well-known activation functions like the generalized logistic function, we try to train our models using these functions, and this was not an easy task. It's not something like you plug whatever activation functions you want and everything works. Or in the Mach-Zehnder modulator, the sine square, also it's a difficult activation function to have training with this. And so we have tried to solve the issue of how we can train neural networks, standard neural networks that have these photonic activation functions by using all the tricks we knew in the machine learning domain in order to avoid local minima and make things work better. So to do so, we have used clever initializations and also clever initialization in order to assure that all the signals that comes from the input goes to the output and that all the gradients that are calculated in the output will go through in the backpropagation algorithm through the first layer to the first layers. And in these approaches have given improvements over what was already published at that time. And so this will pave the path that we need a close collaboration with the photonics group to understand what they are able to provide and also, in our case, to explain what we are able to provide also to those researchers that are implementing photonics. And you can see indeed that when you are doing that, you have significant improvements over, for example, classical Xavier or other uniform initializations of the neural networks. So I will skip some slides that have been already discussed by Miltos. We had indeed in our first works significant improvements using these activation functions, and we have tested in different data sets. And then we have tried also to tackle the issue of noise, the photonic noise sources that are already there, and then someone needs to have algorithms that are able to compensate somehow for this kind of noise. So at first, you should, of course, be able to understand what kind of noise and where you have this noise, if it can be approximated or modeled, in our case, by additive wide Gaussian noise. And since the noise is there, how you can estimate the parameters of the noise, and if you have a good model of the noise, can you use it in your training to make things better? So, as already presented, the noise sources were modeled by additive Gaussian noise, and we have estimated the variance of this noise, and we proceed with a co-design approach, so taking these into account whenever you train. Actually, you add this noise. Also, there were similar approaches in the talks previously that we know that this idea to have all the parameters during training known and try to implement them as good as you can in the training procedure helps and improves things. So you can see in that table that indeed when you are performing training with having in mind what kind of noise you expect, then you always improve compared to what you have without taking account the noise of the network. So in order to compensate for all the noise that's available, we try to build the more generic model that we had in mind for the neuron and try to use this estimated variance that comes from the experimental devices to use them in the training procedure. In the activation function, on the weights, on the summation, on wherever was wherever we thought that we have noise. And the pipeline we have designed and proposed in order to solve this issue had this module, this adaptive initialization, that actually what was trying to do is at first to be able to have the signal pass through all the layers until the end. And how we can do that? By adapting the weights of the layers just only to pass the signals. So before trying to teach anything to the network, you have to verify, to justify that indeed the signal passes. So with this initialization, we built training algorithms that were able to self-adapt to this kind of noise and this auxiliary classification layers, trying to train extra layers that try to learn these parameters of the noise, use them to normalize the input, but also the output of several layers. And this noise-aware approach also has been used in an activation-agnostic way, so without coupling with specific activation functions. So the estimation of the variance of the noise was very critical on that direction, and if you have that, then you can back-propagate the gradients, taking care also about the noise and making the network, pushing the network to become more robust during training. Then you hope that this, let's say, a noise-aware network will be able also to perform similarly when it comes to the actual application on the actual hardware. So during the initialization, as I said before, you actually don't train your algorithm to perform the task. You just train it to pass the signals from input to output and from output to input. Then, when you have your initialization set, then you can start to train your networks. We have applied this idea also for specific applications. I will skip that on financial time series and on optical fiber communication evaluation, also in the framework of the Plasmoniac project that we are participating. And we have seen indeed that the proposed approach gave significant improvements. And we have tried to use that also on a more relevant task, which is the optical fiber communication evaluation. Also have some talks today on the same problem, when we have a channel and we consider that a neural network actually can help as an encoder and decoder, so actually as a transmitter and receiver, when it can modulate efficiently a signal train, taking into account whatever comes actually in the channel, and then the receiver on the other part can be also a neural network that also compensates for the noise on the channel. And this entire pipeline can be trained end-to-end if you have if the channel is differentiable, or if you can pass gradients from the end to the start. And this approach led indeed in significant improvements, once again using the proposed optimizations. And we have tried to use also sigmoid and photonic sinusoidal activation functions, so activation functions that we already knew that we can implement in photonics. So improvements from the initialization were evident, and then we have also tried to use this approach to other datasets like image classification. These actually are more or less toy example, but even with deeper networks, 4 convolutional layers, 2 fully connected layers, so architectures that cannot be implemented in hardware, but we were able to simulate in our case and see if indeed these activation functions and the noise modeling can be handled at least in our simulations and approaches. And the evaluation results were indeed improved in many cases where the actual algorithms that we have available collapsed in terms of accuracy. When you perform actually informed training and initialization, you are able to compensate in a great extent for those features that come from the photonics. And results also on other datasets like Cypher10 also validated this idea. Also in low precision photonic neural networks, as Miltos said in the presentation before lunch, we have also tried to compensate with for the low precision, because we also in the electronic domain, we are dealing with low precision and quantization error, but in that case, these are quantization errors come because we want to have lighter networks, we want to use smaller precision, But in that case, it was not the same because in photonics you cannot have actually the precision you want in the in the electronic domain. And but you can see if you can train appropriately networks that will take into account these quantization errors in the case of neuromorphic photonics. So we took into account whatever was available on simple uniform quantization and applied these mechanisms of initialization, noise compensation, and estimation of these parameters in order to make our networks work better with the quantization error. So this was our contribution to propose a quantization-aware training framework, where actually we model everything as noise that comes with the quantization. So this actually is a model of the corresponding neuron with the photonic activation function, and estimating these values of the quantization errors, we were able to train our algorithms and compensate for, with a proposed model, compensate for the errors that come with quantization. And the results, as you can see in these tables, were that in many cases where, as you see, for 4 bits or 2 bits, actually the post-quantization collapses. Actually, the network is not able to train anything at all. The proposed approach in the last column proves that you are able to more or less keep the performance closer to the original baseline when you have 8 bits quantization, both for photonic sinusoidal and for the photonic sigmoid case. And we did these experiments we have repeated for the CIFAR 10 and for the FI1 2010. And in all cases, we found similar results that indeed, whenever you take into account the quantization, you are able to significantly improve the performance of the trained algorithms. Now, coming to the last contribution that we are working and we have worked in the last 1 or 2 years is the non-negativity constraints. So from the beginning of our collaboration with Photonics Lab, we had always the problem of what about negative weights and negative values and what we can do about that. And you have already had several solutions that can be followed. But in our case, from our perspective on machine learning, we said, can we train non-negative training networks? Do we actually need negative values, both on weights or also on the activations? So we have proposed, and we thought several methodologies to come around that. And actually, what we have proposed at the end was we found a transformation that is able to transform any given network that has negative weights and to transform it in a network that has only positive weights, with a constraint that you need biases. So we were able to propose fully non-negative photonic neural networks. It's a paper that's under consideration now. And we have performed several experiments on different data sets to see, you can see here that the regular and the non-negative one, that we can obtain exactly the same performance using negative weights and non-negative weights. And this, of course, to our view, opens up a new direction, not only for the application of photonics, but also another issue that is very relevant in our research area, but also in the community, which is the explainability of these models. Because when you have non-negative weights, non-negative activations, many things become clearer. You add positive or non-negative values, then the explainability, interpretability of these models is easier to obtain. Also, you have other important features like monotonicity of these networks, which is also another feature that we want for explainability. So, as I said before, we have In the framework of plasmoniac, we have performed several experiments. You can see in Cypher 10, 100, and in all cases, we have found that indeed the non-negative proposed approaches are similar to the negative one. So coming to the conclusions of this talk in neuromorphic photonics, as I said before, leading a group of machine learning, deep learning, computational intelligence, we have seen that indeed when you are trying to implement and to build networks that are physics informed, photonics informed, whatever informed, you have to have deep knowledge on whatever, but this is not possible. It's not possible for us to have deep knowledge on photonics. So, to my view, this is a very good opportunity for all groups to collaborate and advance the research and also the results on both communities. And I think both communities have to gain from that. And we are dealing with new problems, the difficulty to support conventional activation functions. You know, this is the activation function. You cannot have whatever you want. We will have noise. You have to deal with the noise. And also the low bit resolution, the challenges with non-negative weights. So interesting challenges and approaches that can be followed to solve and be beneficial for both communities. So concluding, I would like sincerely thank Nikos Pleros and his group for these last years that we have collaborated, and it was also for me and my group the opportunity to learn more than we knew before, of course, and also propose some solutions, hopefully useful also for you. Thank you very much.
Thanks a lot, Tasso, for this enlightening talk and for being our trainer, actually, for all the last years. So the talk now is open for questions.
Very nice talk. Just a question. You said that the activation function plays a significant role in the accuracy you can achieve for a specific problem. So is it, let's say, worth trying to find a solution in order to prepare any activation function you need for any problem with photonic tools? What is your opinion?
Once again, sorry, I didn't hear you.
Yes, for example, if we had a tool, a photonic tool, that could produce any activation function, this would be worth investigating or not?
To my view, this is something that is needed, for at least for the photonic researchers, to be able easily to test any photonic function they have in mind. For example, I know that this photonic function is something I can produce in my hardware. So let's try in the software now to see if this converges. If I apply any trick I know with this photonic function, can I have a network that will be able to solve even, let's say, simpler problems, like communication with fewer? And then, if we have these tools available, the entire community will benefit and will also progress the research. This is my view. These tools are needed. In our case, without these open tools, we will not be able to progress.
So it's not only a matter of how nodes you have, but it's also important to have, for a specific number of nodes, let's say, a reconfigurable activation function. Have I understood correctly or not?
You mean if we want to have the best performance available that we can achieve, then to select the appropriate function, the activation function, is something we call network optimization. This is something that you can search it if you have all the tools available, like these open tools. Will you gain what you expect? I think that to my view, if we find a simple function, activation function, like the ReLU, with small nonlinearity, will benefit the domain. I don't think that in large nonlinearities we can find a solution.
Okay, thanks.
A second question in the back.
Have you observed the difference, the statistical difference when you change from non-negative weights, from negative weights to non-negative weights? Have you observed any statistical difference in the weights? I mean, the range of the weights, the minimum and the maximum values, the mean value of the weights. I wonder how can we solve the same problem with the same number of weights when the weights are positive and negative and only negative with the same accuracy.
You mean if we also change the range of the weights?
Yeah, I mean...
yes, we change the range, of course, of the weights. It's a way, but this is something we have not discussed. In many cases, of course, from the photonics, you say that you know the range that I can support is that. So you can train whatever you want, but at the end, your weights should be from that value to that value. This is an extra constraint, but this can be handled in some cases by scaling the inputs, or we have some tricks that can handle this. But in general, I can say that when you're changing, when you transform from non-negative to negative, the scale changes, but this is not a major problem. We can handle with the scaling in some cases, and even we can retrain with these constraints to try to suppress the range of the weights.
Yes, Folk. Okay.
Just intuitively, if you remove the negative weights, you're removing like the inhibition, right, or the suppression. Did you use a negative bias, or how did you still get enhancement?
Yeah. Actually, what we did was that we moved every non-negativity to the bias, whatever is needed, but also from a geometrical point of view, let me just try to explain the symbol. When you are trying to solve a classification problem, you can actually rotate the space, whatever you want, and solve the same problem. So you can see, for example, that I have to solve a classification problem on the third quaternion when we need, for example, negative weights, but we can rotate everything and put it on the place, on the high-dimensional space, where it can be solved with non-negative weights. From a geometrical point of view, we can consider it that way.
Thanks.
No, because we calculate everything beforehand. I mean, we have now different approaches. First is that we can take whatever network is already trained with non-negative weights and make it with negative weights and make it non-negative. But on top of that, what we have proposed is to start from the beginning with non-negative weights and with multiplicative updates stay on the non-negative era, or to use hybrid learning. So you start with negative weights and positive weights to help boost the network training, and then you take the negative weights and switch them to non-negative.
Okay, so if you, another question. So if you train the system once, and let's say you train it n times, and you don't change any parameters, do you get, you showed 4 significant digits. Do you always get that same number, or does it fluctuate a little bit?
No, okay, you are right.
Like for anything, with or without?
What I have shown is only transformation from when you have a trained network that is non-negative, it has a specific accuracy, you transform it to non-negative without retraining, and you have the same accuracy, exactly. If you train it from scratch, of course you will obtain something different. What I have shown in these tables, is that the transformation from negative or from regular to non-negative does not affect the accuracy. So we don't lose any information on the weights by this transformation.
It just looks, if I be that blunt, it just looks too clean.
Yeah. But because actually it is redundant, because when you prove mathematically that it's actually the same, you don't have to do the experiments. This was something that we were discussing also with my student. But nevertheless, when you obtain also in experiment the same numbers, you say, okay, that works also in the experiments.
I mean, it would be great if that framework works. I mean, sure.
Yeah, the publication, we already have in the arXiv, I think, the papers, yeah.
Okay. So I would propose then to move to the next talk. Thanks again, Tasso.
Thank you very much.
The next talk will be given by Timoleon Moraitis on how to make neuromorphic computing the mainstream of AI.
Let's hear it.
Thank you, Nikos, for the introduction. Well, first of all, I'm really happy to be giving a talk in Greece. It's my home country, but I've been living for almost a decade now abroad, so it's actually an honor to be here. Thank you for the invitation. Indeed, my talk is about making neuromorphic computing mainstream. So let's see, what's the state of the art in neuromorphic computing? Actually, just a very brief mention of some examples. You know, there's a lot of progress in sensors, in processors, in material sciences, in circuit design, and all that is actually very impressive. Much of the focus of the field of neuromorphic computing has been in spiking neural networks, so much so that when I mentioned that we're working on neuromorphic computing, then the reaction is, oh, spiking neural networks. But there's a number of other neuromorphic properties that I'll keep for later, and we'll see why they're important. So in any case, despite all this impressive progress, the reaction from the conventional AI community is, well, Jan LeCun is one of the Turing Award winners for deep learning, and he's, why build chips for algorithms that don't work? And it sounds harsh, but it's also somewhat fair, right? If you want to solve a problem, then you're going to go for the best working solution. And we're far from proving that our solutions are the best in any sense. Even efficiency, in many cases, is kind of a hope. But even if we presume that efficiency is something that we can achieve, so far the paradigm has been a trade-off. Like fundamentally, we're trying to achieve efficiency by trading off performance in some other manner. My belief, our belief with my collaborators is that actually it doesn't have to be so, because the reason why we achieve efficiency is because we use some unique mechanisms that are inspired from biology. But these unique mechanisms, if they're applied in unique problems for which they're best suited, then they can also actually improve their performance, and even in terms of accuracy, in terms of new capabilities that are not possible otherwise. So in fact, our approach is paradigm is that we're trying to achieve performance through efficiency rather than looking at this as a trade-off. So I'll make that more specific with actual examples where we actually do improve performance. But so what are the type of things that we work on? I'll focus on four. I'll try to categorize it into 4 types of problems. One is how could we improve the theory of learning? We've heard in various talks that we should make learning that is more brain-like to imitate how animals learn and how our brain learns. Well, the practical implication of that is we would make learning on chips much more efficient than current learning on chips. Then how can we imitate how animals are able to sense the environment, the continuous streams of sensory information, which is completely dynamic. And then the implication of that would be, we would have chips that are able to process all kinds of sensory streams, that, vision, video, images, and so on. Then how can we make, how can we imitate or achieve some level of capabilities in interacting with environments, taking actions, and then the implication of that would be we would be able to build autonomous cars, robots that are moving flexibly despite unpredictable factors in their environment. And then lastly, how can we make these processing by neural networks faster, such that the reaction time is faster. So, this sounds so vague, but that's just because we're talking at a kind of high level of a number of disciplines that are involved. So the disciplines involved are essentially theoretical machine learning, applied deep learning to actually show these in real-world applications. It's actually, from a different perspective, all the things that I'll talk about could be described as computational neuroscience. There are also theories, and in cases, also experimentally testable predictions for how the brain works. Then there's material physics involved, chip design, and all that. So I won't talk in detail about all these, but I'll try to give some impression about things that are relatable to all of us in here. So first of all, in terms of learning theory, the core algorithm of deep learning is backpropagation, right? It's this idea that you propagate forward and then to actually update a synapse, a connection weight that's somewhere hidden in the network, you need to have knowledge of everything that's above the synapse, of all the full model, all the synapses, all the connections, so on, so that you can backpropagate the precise error that should be credited to that connection. Well, that makes it non-local and introduces all kinds of inefficiencies. You need to have backwards going ways, you need to have currents that are moving forward and backward through the chip in neuromorphic settings. It introduces, sort of time locking, that you cannot input another input before actually propagating forward and backward again and all that. So it's actually very different from what we know about how our connections in our brain are updated, which is simply by looking at information in the previous and the next neuron, this locality. So there has been a very broad, very large number of high-profile attempts to resolve this, like high-profile in the sense that from companies like DeepMind or groups like Geoffrey Hinton's. Another, by the way, his keynote speech at NeurIPS last year was about this topic and how significant it is to address, and so on. However, this type of approaches aim mostly to approximate backpropagation by somewhat getting around each of the individual limitations it has, with the additional, so they don't deal with all of the limitations, and on top of that, they actually decrease performance significantly. So here, this table is about CFAR 10, but because most of these are not applicable in more difficult problems, in fact. Right, so what we introduced in this paper that's referenced down there is actually a very different, radically different approach, which is not an approximation to backpropagation, but it's actually a sort of bottom-up approach where we say, okay, what if we have this Hebbian plasticity, where Hebbian just means the principle that neurons that fire together, wire together, plus some additional biologically constrained properties, could there be learning that emerges in a single layer, and then by stacking many layers, a deep learning? Right. So in fact, we proved mathematically that such a type of learning rule that does actually minimize cross entropy, which is one of the most common losses in deep learning, without even having access to labels, under certain assumptions, of course, and without any backpropagating signals or any feedback or targets. So that's for a single layer. In terms of that was a mostly theoretical paper. That's the sort of plasticity rule that's described there. I won't actually get into even that single equation I have there. But practically speaking, we also show this introduces a robustness to adversarial attacks, which is a notorious limitation of deep learning-based neural networks. I'll show something about that later, but before that, so this was about a single individual layer that's learned with that. In a subsequent paper, we actually showed that by stacking such layers, where, again, there's nothing propagated backwards throughout the layers, we actually managed to train such a network and achieve good performance in a completely unsupervised manner. There's no target again, or error propagated. And it actually outperforms these other approaches, which are, in fact, approximations to backpropagation, while this is a very different type of approach. And so this table is about CIFAR-10, but we've also shown it in in ImageNet or STL-10, which are much larger data sets, and previously were completely out of touch for this kind of approaches. Even though those approaches that are actual approximations to backprop were not applicable in many cases on ImageNet and so on. And in fact, it solves all this number of problems precisely because it completely gets around backpropagating signals. Right. It should be, well, I'll mention about the caveats on that a bit later, but in any case, this actually achieves already some degree of efficiency even in GPUs, right? So actually, in a single epoch of training, a single presentation of the data set, we were able to achieve this result, while the other approaches need tens or, in cases, hundreds of epochs. And it also reduces the number of flops and so on. But, of course, the full efficiency would be achieved in analog, for example, crossbar arrays, right? So it's very suitable for neuromorphic learning chips. Now, going back to the issue of adversarial robustness or sensitivity, I'll show it with a kind of practical demonstration. In the paper, we actually have analytical results and systematic results and so on. But in any case, so this is an example. You know, CLIP is one of these big models from OpenAI where you can show it an image, upload this image, and then it gives you a very precise description of the image. It's impressive, really. It says it's a cat wearing a suit and all that. Then, however, if you just show it this number 4 with some added Gaussian noise on top, it then says it's a picture of a person doing a yoga pose. So it's really, you know, this is and this is Gaussian noise. There are even stronger attacks than this. However, this type of very simple approach of learning, which is biologically plausible, which we call soft Hebb, by the way, because of Hebbian learning and this so-called soft winner-take-all circuitry that is biologically plausible as well, it does not have this issue. It also labels it as a 4. And it also shows this kind of robustness in this white box, very strong adversarial attacks that actually assume full access to all the weights. Therefore, they can, you know, the approach there is they perturb the image in the most perturbing possible way for the specific network, but still our approach shows advantages in that case. But this was only in this single layer network. In the deep network, we have not studied yet adversarial robustness. Right, so just to mention that these things, we have been studying them in theory and then in simulations. So all these ImageNet results and so on, they are on GPUs. But as I mentioned, this is very suitable for neuromorphic application or neuromorphic implementations. And we do, in the past, with similar but not entirely the same algorithm, we have demonstrated these things in phase change devices, which are a type of memristor, which represents the weights. And then, well, we were able to show essentially a very similar type of learning, on the devices. With the new approach, this should work much better and possibly be able to stack such layers on top of each other to achieve deep learning. So, therefore, you know, one would think we should go and just implement that on chips to have this sort of not just in-memory computing, but in-memory learning. But it should be mentioned that there are important unresolved obstacles. So this is not a generic algorithm like backpropagation. We showed it for a very specific type of architecture on a limited set of vision problems. So it's very unclear if something like, and even how something like that would work on more advanced architectures than it's a type of convolutional network that we had there, but it's not a ResNet. It has some particular limitations. Then on top of that, despite outperforming these approximations to backprop, compared to backpropping itself, it actually performs much worse, right? So we would also have a comment by someone like Jan LeCun, like, why build that, right? And then the networks we had are multi-layer and deep in the context of that, these types of algorithms, but still they're relatively shallow. We went up to 6 layers. Right, so on a separate note, these, what about, you know, processing the dynamics of the environment? So this work is something we did actually while I was at IBM before Huawei, where much of the other work is currently taking place. So it started from the observation that much of the dynamics that is happening in natural environments has this property that things are, the present form of an object is associated with its future form. So it's a type of associative relationship. And then on top of that, many things that are observed now, the probability of being observed in the future decays with time. So just taking that kind of concept, modeling it mathematically, we actually were able to show that the optimal solution to modeling the probability distribution of such an environment is achieved by a mechanism that exists in biological synapses, which are this short-term Hebbian plasticity, which has the Hebbian aspect, this fire together, wire together type of association with a decay that makes it short-term. And then by using that with spiking networks that only use this type of plasticity that is completely unsupervised and local and simple and spiking and all that, we were able to outperform much more conventional networks under a similar number of parameters and so on a task that we designed specifically for such a simple network to target. But then to take that, so it actually is a demonstration of an actual advantage in this case, where we outperformed in terms of accuracy the non-neuromorphic things, right? Just as a note. But this is, you know, it's a sort of toy problem, even though it's much more, it is a kind of video where images are occluded and that there's noise on top. So it is much more difficult than MNIST itself, but it's still, you know, type of small problem. So to actually go in much more advanced problems and apply it in real-world settings, we thought that this would be suitable, especially for things where you need to interact with the environment. And so, in any case, just to make it more advanced and much better working, we took this concept of short-term plasticity, we formulated it as a new type of recurrent model to represent this decaying and this memory that is needed in each connection, in each synapse, and then we trained the plasticity parameters, so the parameters of the plasticity rule. So this makes it actually, if plasticity is a type of learning, then training the plasticity is a type of meta-learning and learning to learn. So this then relates to how do you adapt to completely new environments on the fly that you have never seen. So you need to learn how to learn, right? So this is the idea. And by taking this approach, we were able to tackle advanced machine learning problems that were, again, completely out of the field of neuromorphic computing until recently anyway, such as, well, this is a toy problem of, let's say, kind of language processing, but we also targeted this type of maze exploration where the maze itself is actually changing, and so you need to learn again, and then with Atari games, this sort of simulated robotics. And in all these settings, we were able to outperform the models that are essentially what the state of the art is using. So LSTMs, RNNs, in fact, even other models with plastic weights and so on that were designed for each of these individual tasks. So this single type of model that we call STPN, short-term plasticity neurons, was able to outperform all of them, all of these models in all of these tasks. And so this makes it, well, by the way, the approach we took for training the plasticity was reinforcement learning. So the same setup can be applied in settings like this. This is not our work, but in any case, just to explain, learning in 20 minutes how to walk in an environment that is completely noisy and so on can be solved by this type of approaches, and presumably by an approach that outperforms the state of the art in these other problems, would also outperform it in this more like true robotics case. But something that is, so we showed an advantage in terms of accuracy, and then there is an advantage, there would be an advantage in terms of efficiency, energy efficiency, if you implemented it in hardware just by the means of, you have some device that's suited for that. But on top of that, this actually is a new method for increasing energy efficiency in neuromorphic hardware, because the reason why it outperforms these other models is that it has this decaying, this kind of forgetting aspect. So this forgetting aspect, if you interpret it in analog hardware terms, it would mean that the synapse decreases, individual synapses turn on and off at different times, so therefore the currents turn on and off. So only the useful currents are necessary, and therefore the other ones, they don't consume any power for forward propagation. Well, in light settings, it would mean you can make similar analogies in photonics and so on. So in simulations, we calculated, we estimated the energy consumption that such a model would consume compared to a number of other models. And in all cases, indeed, our intuition proved correct, that this STPN would actually have the lowest energy consumption compared to all the other models in all these other tasks. Just to speak a bit about hardware implementations of that, in fact, we currently are working together with Alexandros Emboras from ETH in Zurich, who is going to talk about the specific implementation of this exact approach. So I won't include this here, but some other related approaches are that we actually showed in this paper, that you can use PCM devices and have some parts of the weights in software, some parts in hardware, then we demonstrated some actual useful applications of short-term plasticity in such hardware. In addition to that, some devices that actually are phase changed, but they also respond to field effects. And by using the field effect, you can actually emulate this sort of dynamics. And we, again, demonstrated the implementation of short-term plasticity in nano devices, memory-restive nano devices. Right. And then an additional related thing is that in this collaboration with Oxford and IBM previously, we demonstrated this type of reinforcement learning that was necessary for these kind of tasks within individual optomemory-restive devices, where optomemory-restive because they do respond to light, in fact. And the approach we took there was that light, you have light and the possibility to apply light or electricity, where light can act as the Hebbian update term, whereas light can act as a reward term, for example, or vice versa. And by doing that, you can implement reinforcement learning on these types of devices. And we demonstrated a sort of maze task that was learned by reinforcement learning on these devices. Similarly, somewhat to the mazes that we solved in simulations, right, with some differences. Anyway, moving on. Still in this topic of interacting with the environment, just very briefly to mention this work of ours that was published in Europe's, well, by the way, the previous work, the theoretical work and the model and the simulations were published at ICML, another one of these high-impact conferences in machine learning. This one was published at Europe's last year, where the idea we had was, well, actually, one concept that exists is very well established in neuroscience is, have you ever wondered why you cannot tickle yourself? It is because your brain sends a copy, it sends a command to the muscles to tickle yourself, but it also sends a copy of that command, so then it cancels the actual sensation. It can predict it and cancel it out. But then this copy that goes back, which is called an inference copy, is a copy of the actual command for the action. We thought here, well, it could act as a sort of label, a sort of training signal, so that if you use it during learning and training a deep network, it can act as a self-supervising signal. So in fact, we modeled that mathematically. We showed that it actually is it can capture a number of previously existing approaches to self-supervised learning that were previously kind of scattered, it unified them. In addition, it extended them by showing possibilities of changing the loss that's applied. And in practice, it actually improved approaches of deep learning with ResNets and so on in self-supervised settings, so without actual labels on ImageNet and other settings. So this is just a single slide of that, even though there's a lot that you can look at in the paper itself. The last thing I wanted to talk about is this idea of spiking neural networks that I started by saying there are all these other mechanisms, but spiking is important. However, a lot of the approaches in our field have been, let's do it spiking, we will have some efficiency advantage, but it doesn't, it's not as simple as that. So, in fact, it's been very hard to prove that that you can achieve the same result with the same efficiency, with higher efficiency, even if you do it spiking. So here, instead, we focused on something that we isolated an element of the spiking aspect that is compatible even with conventional neural networks that are not fully spiking. And we thought that a concrete advantage could be that it could actually increase decrease the inference time. So the idea here is essentially to combine the benefits of conventional artificial neural networks, which is ease of deployment, ease of training, and high performance, with some advantage that should come from the spiking aspect. So that would also outperform the spiking networks in terms of accuracy, while also outperforming ANNs in terms of something else, in this case, latency. And actual consumption by actually doing shorter computations. So, I mean, long story short, what we did is we targeted problems where your input is a sequence, such as a spoken keyword in this case, in this example. That's a waveform of a voice recording that is input in a recurrent neural network. It could be instead the transformer, for example. That is processing a sequence. And then what we do is we take the output and we make that spiking. So only the output layer is spiking. And then the first spike that is produced during training, that is when we backpropagate. So we don't wait for the end of the sequence to apply the label and the backpropagation. We apply before the input sequence ends. So that decreases computation during training because you can forget about everything that happens after that. But it also turns out that merely by applying the standard laws of, for example, cross entropy here, it not only decreases, it increases the accuracy, but it also decreases inference time throughout training. So that first spike becomes earlier and earlier during training, even though it maintains the high accuracy. So in fact, if you go too early, it starts decreasing accuracy, but until some point, it actually loses no accuracy in a number of tasks that we tried. And even the trade-off, if you want really to go much faster while losing some accuracy, you can tune it by adding a term of that is actually entropy weighted here in the loss function. So in the end, in a number of kind of toy problems as well as problems that are standard in the spiking neural network community, we showed that we can actually reduce reaction times while actually outperforming the state-of-the-art in spiking networks in terms of accuracy. Then we also achieve the same accuracy in spoken keyword spotting as the state-of-the-art in conventional neural networks, while showing speed-ups, which even in the conventional neural networks. And it could also be applied in fully spiking networks, but then you do have the standard issues with spiking networks that you start losing some performance. Right. So this method, we call it rank coding because for historical reasons, it is inspired from some previous approaches. But the idea is you rank the output spikes, and you take the spike of rank 1 to encode the output label, and you use that one to also backpropagate. And it's a very simple method. You just threshold the output, and then you backpropagate. It sort of circumvents the disadvantages of SNNs while achieving some of their advantages. And it brings essentially, it is not fully spiking, but spike-based approach that is actually achieving state-of-the-art performance. All right, so as a kind of conclusion, again, spikes can be important if you are targeted in how you use them and in which settings and in which way. But it's not only about spikes. There are all these other mechanisms like local plasticity, short-term plasticity, this mechanism of inference copies that you can use as a self-supervisory signal. In fact, the results from that is not just energy efficiency, but it's also data efficiency. I mentioned, for example, just one epoch of training. Then there are many other aspects that I didn't mention. There's speed for training and speed for inference. You can do well-performing learning without labels. That's unsupervised. You can have networks that adapt in real time throughout their life to the environment. We showed generalization and robustness to actual attacks and so on. So this actually goes beyond the problems that are usually targeted in the neuromorphic niche. It actually improves state-of-the-art in AI, both in efficiency and proficiency. Just because performance could mean efficiency, we kind of try to separate efficiency from performance by saying proficiency instead. Sorry about that. And yeah, again, we went to real-world applications beyond MNIST. And so, in fact, biological efficiency does not imply performance constraints necessarily. It can actually bring performance advantage. Actually, you know, we publish these things in venues that are not usually what neuromorphic papers target. So we try to go in this mainstream AI community and show that you should perhaps look into this neuromorphic field. In fact, by showing real-world applications, and indeed now we're working in putting them in actual products within the company, neuromorphic could maybe become the mainstream of AI because it improves efficiency and performance in some cases. So yeah, with that, I'd like to acknowledge my team, my collaborators, current and previous ones. Yeah, thank you for listening, and I'm open to questions.
Thanks a lot for this very interesting talk. So now, any questions? Yes, please, Antonio.
Hi, thank you very much for your talk. Very interesting indeed. I guess I wanted to ask what is the role of the spikes actually in this late demonstration that you showed? It wasn't entirely clear to me. And also, it would be good to know whether are these spikes implemented in software, in some platform like Intel Loihi or something like that, or is this some hardware implementation? I didn't fully understand.
Right. The role of the spike is to encode the output label. So the first spike, the first neuron to spike at the output layer is the one that is taken as the inferred label. That's what happens during inference, and during training, that is at the time of the first spike, that is when you backpropagate through time in this recurrent network. So it has this role, which that's exactly how we implemented it, but then the implication of that, so the role of that is to actually bring that first spike as early as possible, and therefore decrease computation, because you can stop computing when that happens, and also decrease reaction time. Right, so that's the role of spikes in this case. The concept is, we've heard for a while that spikes actually are suitable for spatio-temporal tasks because you encode time and so on. So this is a demonstration of that in practice. And then Secondly, about your question about hardware, no, this was implemented in GPUs. But yeah, in principle, if you have any, it is a method that is applicable on any kind of training hardware you may have. But I presume you only have GPUs to train networks. Yeah. Right.
Thank you.
Yeah.
Thanks for the nice talk. Do you think that photonic technology can can step in neuromorphic field? Actually, in your presentation, I see more generally the neuromorphic electronics, analog electronics with memoristic devices. Do you think that photonic technology can support this, can offer the performance and efficiency?
Right. Actually, I'm probably the least photonic guy in this room. So I actually tried to answer this question for myself by being here and listening to all the nice presentations. But yeah, so I won't be able to give you a good answer to that. But my impression from what I saw is that maybe, there's a large number of progress, good things happening, but there's also a large number of kind of obstacles in it. But potentially, by using this type of algorithms, you can just, instead of trying to see, okay, how do we best implement backpropagation on a chip using photonics, maybe we don't need to do backpropagation, for example. And maybe in that case, you won't have attenuation issues, for example, or because everything is happening locally. But again, the algorithms go hand in hand with hardware, so it's not just, even though there are all these nice things I mentioned, again, there are the caveats also to the algorithms, so it's, yeah, maybe if you go and put them in hardware, you'll see things that deteriorate in performance, and also, even in software, it's far from, for example, I'm talking about the soft-hub approach of learning on chip. It's far from state-of-the-art in broader deep learning terms. But yeah, very probably some things of those could be matching some of the photonic principles, yeah. It will have to be discussed for the given constraints of each individual hardware implementation, whether it matches the requirements of the specific neuromorphic algorithm. But another note is that, yeah, most of the things are electronics in terms of hardware that I demonstrate, that I showed. But we do have things that are, interacting with light. And more about that will be by Alex, who is going to give maybe the next, or I'm not sure, talk. Right. Yeah. He's bringing you the mic. Yeah.
I'm curious about the software design interface. So this is a conceptual framework, and you just happen to choose that particular, machine to GPU, for example, to implement it. How important or not important was the? I guess I don't know if you did you use NVIDIA. Was it like CUDA or?
Yeah.
So how important was having the CUDA interface to implement this? And let's say if you hadn't had CUDA, could you still have done it? And yes, but it would have taken, I don't know, like much longer. Like, can you comment on this ecosystem of software to implement this algorithm?
Right. Well, yeah, the approach we took here was to try and demonstrate real-world settings, actual things that could be impressive by some standards and so on. So for that reason, we went on to do deep learning. Before this type of works, we were doing neuromorphic things that were of equal kind of significance in my view, but not impressive for like deep learning standards, let's say. So if you want to achieve like this kind of high performance, big data sets and big networks and all that, it's much easier to just use CUDA and because there's a large ecosystem around it that is a big moat for NVIDIA, right? I mean, for example, you know, I've seen AMD has released some competitors to NVIDIA's GPUs, and some people were very excited about that because some specs of those are much better. But then you go, I've heard from others, you go and try them, and then you have issues with drivers and all that. So, exactly. Right. So in the end, you go with what works and achieves your target. So we had enough problems to solve. We didn't want to solve also these others.
Right? Is how, I mean, I personally think the importance of an plug-and-play SDK kit is extremely important. Right. And I guess you just like basically validated that. So, and that's something I think we need to discuss.
Yeah, I think maybe one alternative possibility would be that if you know, this is a sort of B2C case, right? Where we're the client and we need to solve that. So then, yeah, if we're sort of retail where you need to train their networks, then they're going to need all these libraries and all these drivers. But if your goal is a very specific application and it's say B2B scenario where your client just wants to sense some data and they don't, you know, they don't want to train themselves something, but it should be just a chip that is doing its job, and then you do all that in your own kind of backend.
Sure, yeah.
Then maybe that would not need all that. But indeed, otherwise, yeah, you're right. It's not just about solving the hardware problems that we've talked about here, but it's also solving all the whole stack on top. Right?
Because from an investor point of view into this entire field and growing it up and scaling it up, I mean, you know, Wim, are you still here? I think he was in the meeting earlier, but I mean, he mentioned this whole fan out, right? We need to fill the pipeline. We need to do 10x more of chips and stuff, right? For that, it needs probably software first before we even do the hardware, because I mean, I'm seeing this as well. I mean, in fact, I caught with NVIDIA just a few days ago, and it was like, yeah, they really need big volume and big markets. So and it starts with the SDK. It starts with the software. If you don't have this, they need to train thousands of people again on some new hardware, which, you know, there's no standards. Like, it's not going to happen. So we have to think very much about a software approach as well, like a co-design between hardware and software. But then, question which standard should we use? You know, it's good at like the known-only, or is there a different one? Or should we develop our own, and should we sync up amongst our community on doing so? So we need some sort of bit of a focused approach around, I think, software as well. That's at least my comment.
Yeah, I agree. Yeah.
Okay, let's take one last question from Harris, if that's still valid. The intention, I mean.
Fascinating work. Thank you for the presentation. A quick question from my side. You demonstrated this short-term depotentiation of the weights in order to make your neuron forget a little bit. Right. Does this apply only in sequential learning, or you can do it every time? And how is there a rule of thumb about how you choose the rate that you reduce the weights?
Right. So yeah. So the conceptual framing that I gave is that dynamics in the environment is similar to this dynamics in the synapse. So it presumes some dynamics in the input in the environment. So yeah, you need some kind of concept of time in your input, and therefore it needs to be sequential to have some advantage from the that decaying mechanism. Right. Now, how do we choose the time constant of the decay needs to match the time constant of your environment. But that was, well, in the first demonstration, basically, yeah, we hand-tuned, let me go back to that. We hand-tuned the time constant to match the time constant of this data, which was sequential time frames coming in. But the next step was exactly answering your question, essentially, and it was training that parameter of a time constant. So not just hand-tuning it, but training it, and not just training one parameter for the whole network, but training it for each individual synapse. This came with a large host of problems that we had to resolve to actually be able to do that. But the result of that was that we were able to target much more advanced problems. So indeed, yeah, being able to tune and choose in a good enough way these constants is important. Yeah.
I assume possibly that there is it depends on the correlation of data and the sequential data that you receive. The level of correlation also regulates in a way the rate that you have to increase or decrease the weights, probably.
Yeah, that's one part of it. The other part is also that, like, how persistent are these? Should these memories be? Like, is there something that actually changes very frequently in time, and therefore it should be forgotten to learn something else? Yeah, the title of the paper is "Learning to Learn and Short-term plasticity neurons learning to learn and forget." So it's about learning to learn, which is a previously known concept. This is all about learning also to forget, and how much to forget, and whether to forget even, because, so it has to do with this. It's also a bit difficult to actually describe these things in a very concrete way, because this happens in a hidden layer of a neural network at its individual synapse and so on. So it's very hard to say that this specific synapse's rate of decay is like that because it matches that X feature in the input. So, but in general terms, it is somewhat like you said. Yeah.
Okay, thank you.
Okay, let's then thank the Timo Leon again. And I think that I will manage now to be the first session chair to start a talk on time. So now it's Alexandros Emboras, the one who is going to give now a talk on bio-inspired learning rules on photonic electronic neuromorphic hardware.
So, thank you for this kind invitation. So today I'm going to talk about bio-inspired learning rules on, on photonic electronic hardware. My name is Alexandros Emboras. I'm coordinating the Center for Single Atom Electronics and Photonics at ETH Zurich. So here you can see where I come from ETH Zurich. On the one side of the lake, we have our labs and offices, and on the other side of the lake, we have our nanotech center between IBM and ETH Zurich. And in this nanotechnology center, we are fabricating our state-of-the-art devices with a feature size of nanometer, few nanometers, I would say. So, as I said, I'm coordinating also the Center for Single Atom Electronics and Photonics, and this was funded by Werner Siemens with 12 million, started on January 2018, and will last most probably forever. And in this center, we would like to perform research on new class of optoelectronic devices and circuits where atoms rather than electrons are used for the operation, and with that we would like to make a functional shift and move more towards neuromorphic applications. This is the outline of my presentation. In the first part, I will give a motivation for optoelectronic neuromorphic computing. I will proceed to part 2 and describe memristors, which I believe could be a good candidate for neuromorphic hardware. In part 3, I will describe our own toolbox for optoelectronic neuromorphic computing. I will describe 2 or 3 devices, and then I will conclude. So let's start with the motivation. So it's really very well known that we're living in a society that is driven by the data, and this basically can be understood also by this graph here, where the computing performance is plotted as a function of the year, and the clear message here is that we need more and more computing power as a function of the time in order to support AI applications. And for that, also, we need efficient computing systems for data processing. And what is the computing challenge behind that? The computing challenge can be understood when we think about a game and the AlphaGo, where the computer beats human world champion in 2016. But in order to do that, they consume 12,760 human brains running continuously for 3 days without sleep. So where does this huge inefficiency comes from? This is coming from the von Neumann computing architecture, where the memory and the CPU are separated. So if we would like to perform an operation in the ALU unit, we need basically to bring the data from the memory, bring it to the ALU, perform the computation, get the result, bring it back, and this movement of information back and forth, this is what is causing the huge energy consumption. One more point, which arithmetic operation is consuming the most of the power, and we have some results from IBM research block and across 3 main AI applications: speech, language, and vision with different neural networks, RNN, DNN, and CNN. They demonstrate that the matrix vector multiplication consumes the 70 to 90% of the total operation, which is the most energy-consuming operation in the current computing architectures. So what are the ways now to overcome this computing challenge? One way, there are a lot of different approaches. One is the electrical neuromorphic computing. And here what you can see is a neurosynaptic array, a crossbar organized in a dense crossbar configuration. And each cross point that you see here in the inset can store and process information at the same time, so you don't need to bring data back and forth from CPU to memory. And how they did that with memristors. You're going to hear this word, memristor, several times in my talk. What is memristor? Memristor is a 2-terminal device with a tunable non-volatile resistance and is able to emulate biophysical processes in synapses and neurons. So what's the problem with this specific example that I show? So when we try to scale it up and let's say integrate several neurosynaptic arrays, then we need to communicate with, we need to have intra-chip routing through, for example, dense copper interconnects, and this is basically a huge drawback. And at that point is rising also the interest for integrated photonics within neurosynaptic arrays. So, photonics is also giving us some solution as an all-optical, especially if we use it in all-optical domain. And here you can see an example of a demonstration where you can see a silicon waveguide integrated in with a ring resonator, and in this ring resonator we have a piece of PCM material, and this PCM material, which is acting as a memristor, can store and process information at the same place in all optical domain, and this could give us the advantage of really high bandwidth. But if you see the scale bar there, the demonstration, the device is huge, which means that, of course, photonics is giving the advantage of bandwidth, but is generally bulky compared to electronics. And our solution is an electro-optical solution with memristors, and we would like to take the advantage of electronic circuits and the high bandwidth of their photonics counterparts. This is, of course, not something new, But what is new here is that we would like to build this platform based on memristors. And as you will see in the few slides later, those memristors have the advantage of being volatile, which can be used for communication, but also being non-volatile that can be used for computation. And computation also in electronic, but also in the photonic domain. So just I will mention our demonstrations based on memristors. We already demonstrate in my group and in the center that I'm coordinating, we already demonstrated 2-terminal memristive switch. We already demonstrate 3-terminal memristive switch, like a transistor, and we demonstrate modulators, photodetectors, and laser source based on memristors. Good. Now, what is memristor and why is suggested as a key element? So this brings me to the part 2 of my presentation. So memristor is basically a resistor with a memory characteristic. And instead of tuning the electronics property by gating, we tune them by relocating atoms. We have basically 3 main technologies. One is the conductive breaching memory, where we have 2 metal electrodes, the top electrode and the bottom electrode. And what we are moving some atoms between these 2 electrodes, and this is what is modifying the state of the memristor. We have the valence change memory, where it's more or less the similar technology, but what we are moving back and forth is the oxygen ions. And of course, we have the phase change memristor, where different atomic ordering, this causing the modification in the state of the memristor. In this presentation, I will talk about the first 2 technologies, the conductive breaching and the valence change, where also the physics is very similar. How does we operate, what's the principle of operation of a memristor? And this can be understood by this graph here, where I plotted the current as a function of the voltage. And the investigated example here is silver, germanium, selenide, platinum stack. We start from the state, basically D at the beginning. We start increasing the voltage, and at some point there is a sharp increase in the current, where the VES set it is, and this sharp increase in the current is an indication that we have a short circuit between the platinum and the silver. When we reduce the voltage, for small negative voltage, we can dissolve the filament and open the circuit, and we can switch really reversible several thousands of times between the low resistance state C and the high resistance state B through voltage-induced filament formation and dissolution. What is telling us that indeed we have a short circuit between these 2 metal electrodes it is an in situ demo observation, where they did see that during the operation there is a formation of several filaments, but there is one filament that is completed, and this is what is switching the device. This device is very rich of different physical processes and dynamics, redox, ion, atom transport, and electronic transport. And it is already used extensively to do some binary non-volatile operations 0 and 1. But if we carefully choose now the programming signal, this programming signal can induce also intermediate atomic rearrangement, and we have at the end not only a binary operation 0 and 1, we have also a multi-bit storage in a single device, which means that essentially we have an analog device like how the synapse works. And this analog operation is very important when we try to train an AI algorithm. So the second important behavior of those memory stores is that they are able to emulate an integrate and fire functionality, which means they are able to emulate neurons. Now, if we correctly choose again the programming signals, we can induce intermediate atomic rearrangements in this filament, and the device is dramatically change its state when a threshold it's achieved, and then this is the signal that we generate a spike. And this is exactly how the neuron basically works. So to summarize, with memory stores basically can exhibit non-volatile and analog operation, and this is how we think synapse works. Memory store also can exhibit integrate and fire functionality, and this is how neurons works. But maybe the most important part, memory stores can emulate biophysical processes in neurons and synapses, and we can take advantage of these different physical processes to perform some computation in an AI domain. So this brings me to the part 3, and I will describe some of our devices. And I will start with the memoristic electronic switch, and then I will describe the effect of light when we train a deep neural network to recognize images. So as I showed before, an atomic scale memoristic devices, when it's formed, it can create several filaments, and this is a big challenge because the filament formation is a stochastic process, and it is the key limiting factor for reliability and repeatability. And what we developed an atomic scale memoristic electronic switch, and this is based on an ultra-sharp 3D tip technology that I will describe now. And with that 3D tip technology, we are able to enable basically performance improvement, more reliable, less power consumption, and faster operation. So the device looks like that. It consists of a top electrode, which is the silver, which it has a tip-like configuration, and bottom electrode, which is a platinum, and in between we have a silicon dioxide. And when we apply the positive voltage on top electrode, we start oxidizing silver, and silver is diffusing inside the insulating material, and we are able to form a filament at the level of the tip. And what I will show you is that this sharp tip improves the field confinement and thus promotes the formation of a single nanofilament, and this is what at the end gives us the better reliability. The motivation is coming from also, can be understood from these very simple calculations where we calculate the electric field induced in a tip-like configuration, the top image, and the more planar configuration, the bottom image, and the tip-like configuration. It uses better, basically, field confinement, which means lower switching volume, better control of filament growth, and at the end we see higher speed and lower switching voltage. How we fabricate this tip? We fabricate this tip with a technology that was invented by IBM Zurich and then becomes a startup. What we have a heatable tip, basically an AFM tip that is used to direct pattern and simultaneously imaging. And here you can see a movie, how does it work. So when the tip is moving on the right, is heated and is writing in the resist. When it's moving on the left, is reading what is already written. And this is very reliable, fast, CMOS compatible. And the most important aspect is 3D patterning in atomic scale, which for us it was really very beneficial in order to locate the formation of the nanofilament in a very single place. So, and we fabricate this device using this fabrication technique, and here you can see on the right side an SEM image, and in this SEM image you can see the silver, the platinum, and in the center there is a dot, and in this dot here is the sharp tip that we form with this AFM, with this fabrication technique that I just showed you. So, and what we did also a cross-section at the level of this hole there, and we estimate the radius that we form, that we transfer into our silicon dioxide, and it was roughly 10 nanometers, which is, and this was very reproducible, and this was really a nice achievement. The technology is also scalable. We pattern 2x4 pattern array with a minimum pitch of 30 nanometers with this technology. Of course, compared to the state-of-the-art or industrial standards, maybe this is not good enough, but for academia, I think this is quite remarkable, I would say. And then we compare the tip and the non-tip structure, and what we show, and here you can see the current is a function of the applied voltage. We show that the tip structure gives lower switching voltage and better cycle-to-cycle variance, and this is exactly because of this tip, the promotion of the single, the creation of the single nanofilament because of this sharp tip. We have a binary switching operation, non-volatile 50,000 cycles, 100% switching rate, and we send a pulse of 20 nanoseconds, and we see switching time of 7.5 nanoseconds, which sets an energy of 17.8 nanojoules, femtojoules, which is, it's not the best in the literature nowadays, especially at the time that we demonstrated that it was one of the best. But I think still it's really suitable for low power neuromorphic applications. But the important part, this device is not only, we're not performing only binary operation. We can also, by choosing the correct pulses, we can also induce, as I said, intermediate states, and the programming voltage can form intermediate states and thus continuously tune their own resistance. So we don't have only binary operation. We have also on this device a multi-bit storage in a single device, and how now we can use that to perform neuromorphic operation. I will show you two examples. One is we're currently working on that, is the vector matrix multiplication. You probably know all here that this is the formula that is giving the vector matrix multiplication. Y is the output, A is the matrix, X is the input. Now, in the standard computer, if we would like to perform this vector matrix multiplication, we call all the data from the memory, we bring it to the ALU, we use the circuits with a lot of transistors, adders and multiplicators, and then we generate the result, and then we save it back to the memory. This is, as I said also before, consumes a lot of power. So instead of doing that, we organize our memristors into crossbar arrays. And here I show you a 2x2 array for simplicity. So, and in each basically cross here, the Ohm's law is valid, which means that the current 21, I21 is equal to the G21 multiplied by the voltage 2. And similarly, the I11 is equal to the G11 multiplied by V1. This is the Ohm's law, but also the Kirchhoff's law is valid in this configuration. We have resistive elements here. So the I1, it will be equal to I21 plus I11. And then if I use the Ohm's law from the previous calculation and rewrite a little bit this equation, I have in a matrix, I have this form that you can see here. And then if I rewrite it a little bit more, I have very similar equation as the vector matrix multiplication. And to do now in this scheme, to do the vector matrix multiplication, What I need to do is to map input to voltages, map the matrix to conductances, and read the result by measuring the current. So what I have to do is just come and go and read the current in each column, and this will be the result of the vector matrix multiplication. No need to bring data back and forth, and this is important in energy efficient neural networks. Of course, as I said again, this is an academic demonstration, 2x2 device for the moment, and the process of publishing those results is, we're going to publish it soon. So, as I said, this, and here what you can see a normalized conductance of a similar device as a function of the pulse number, and what we can get some quasi-lean analog behavior as a function of the pulse number, and then we use these conductance states to train a machine learning algorithm to recognize images, and when we did that, the accuracy, it was really bad. It was really about 65%. There are a lot of other devices in the state of the art that they can do much better. But what is the innovation here? We integrate then our memory store with a silicon waveguide, as you can see in the top left image. And then we perform exactly the same experiment, but now the light was on. And what we achieve with that, we achieve to basically linearize and make more analog the behavior of the conductance changes. And then when we insert now those data into the same machine learning algorithm, we end up with accuracy of roughly 95%. My message here is more analog means more states, and this is what improves at the end the accuracy of training an algorithm to recognize images. What is the physics behind that? Basically, a few things. Light can induce heating. The main mechanism is heating. That enhances the redox processes and thus broadening the filaments that were formed. And this broadening of the filament, this is what is giving more analog operation, and this is what is improving at the end the recognition accuracy of the classification. And as an outlook, we didn't make that yet, but we didn't make the experiment, but we fabricate the devices. We fabricate silicon waveguides, and on top of that, we integrate crossbar arrays. Here you can see a 4x4 crossbar array with plasmonic heaters. And yeah, we would like to perform the classification experiment exactly on this kind of what we called more scalable level. Good. I will skip the device, the memoristic photodetector, because I don't have time to talk about that. I didn't plan it, but I leave the slides, and I will go to the last demonstration, which is the bio-inspired computation, and in particular the computation using the conductance dynamics. So until now, I talk about conductance states, steady states. So now I would like to show you how we can use basically the conductance dynamics of a memory store and use some networks that originally basically invented by Timo Leon here and to do some energy efficient computations. So the network, it looks like that. I will not get on details to describe the theoretical background of this network. What I would like to say here, in this network we have two important parameters. One is a non-volatile component W, and the other is the decay, and the other parameter is the decay dynamics, which should be somehow controllable. So the second thing that I would like to tell you is that if we compute this parameter, the weight decay, we end up with the conclusion that the computation of weight decay is responsible for the 25% of the memory GPU, of the GPU memory traffic, which means that a specialized hardware is probably needed to run such models more efficiently. And of course, someone could use a digital circuit to emulate, to calculate this decay dynamics, but as you probably know better than me, this needs to be updated at every time. So again, we need to store information, compute, add, and then take the result and bring it back. So it's not very energy efficient. There is the analog circuit approach, but we need huge capacitors, especially if we are targeting time scales of the orders of seconds. So we need huge capacitors to charge and discharge. This is not an space efficient, I would say, solution. And what we suggest here is a single device, our memristor, and our memristor can really very naturally reproduce this decay dynamics at that time scale. So to conclude, memristor is the solution that we are presenting here is a very scalable solution for the implementation of biorealistic synapses, especially to implement these decay dynamics. So this is how our memristor looks like. It shortly consists of platinum and chromium on one side. On the other side, we have platinum titanium. We form a titanium oxide because we heat a little bit our device to generate oxygen vacancies. In between, we have the STO material. And here you can see the protocol that we apply to reproduce these decay dynamics. On top, you can see the applied voltage for different read. The different colors means different read voltages. And below, you can see the conductance as a function of the time. And what we can see is that at the beginning, the device, it is in a specific state. When a volatile pulse sets in, there is a peak in the conductance, and then there is a decay of the conductance, which can be controlled by the read voltage. So the conductance, the non-volatile components of this device is shown here, and the decay component is shown after the volatile pulse sets in. So, we have also more results on that aspect. And here we set our device in a conductance value of W1. And then we did that by sending a non-volatile right pulse. And then after the non-volatile right pulse, a volatile right pulse is coming in, and this is what is creating this spike in the conductance. And then there is a decay, which, as I said, is very useful for the STP neuron. And then we send a different volatile pulse. We change the conductance W2. We get now the non-volatile conductance 2. And again, if a volatile pulse sets in, the decay dynamics can be retrieved. So, and then we can continue, and we create basically multiple conductance, non-volatile conductance states, W1, W2, W3, along with its dynamics. To be honest, this is really very new results. Now we are at the level of implementing now these non-volatile and volatile components into the algorithm that Timo Leon suggest. So the next step is to implement really the non-volatile and non-volatile memristor dynamics in the algorithm. And just before starting this presentation, I text one of my PhD students and I asked him if, because he's very close, he mentioned that he already implemented this into the software, and he see an improvement in energy consumption of 2 orders of magnitude. So it's much, much more efficient to have these dynamics in hardware rather than computing that in software. So to conclude, I will not mention everything. I will mention that we have I think this is really interesting, the hardware implementation of non-volatile and volatile component in memristor dynamics can be really very useful and energy efficient when we train an algorithm. Of course, there is the technology with the integration of memristive technology with plasmonics and photonics. And probably a more visionary conclusion, we have atoms rather than electrons that are used to interact with photons and efficiently operate the device. And with that, we envision, as in the brain, a shift towards more bio-inspired applications. And thank you for your attention.
Thanks a lot, Alexandre. Any questions? Please, Toli.
Thank you for the nice talk. How stable over time are the memories?
Those memories?
Yes.
So stability and repeatability is one of the major issues. There are several ways that we can improve that. I believe one reason that is not commercialized, that is not commercial nowadays is because of this. So, yeah. Clearly, the stability and repeatability of this device, it is an issue, but you know, to demonstrate in an academic level new concepts, I think it's really enough.
Yeah, of course. Yeah, it's an interesting approach in any case. Okay, thank you.
To Antonio, yeah.
Hi, thank you very much for your talk. Fascinating, really loved it. I have one question. Maybe I missed it. How much power, how much optical power do you need to switch the device, and what wavelengths of light are you using to do the both volatile or non-volatile switching?
To switch the device on and off in a non-volatile way, one application, for example, the photodetector, we need, I think, 10 nanowatts. Since, at least for those demonstrations, we are working also with other concepts that the wavelength could be important. Since the principle of operation behind that is heating, so what we're working at 1550 for the moment. So because, yeah, we are integrating that with a silicon waveguide, so it's, for the moment, it's easier. Yeah. So, but heating is the main mechanism.
Harry.
Thank you for the nice talk. 2 quick questions. The first is that you mentioned that the filament creation is a stochastic process.
Yes.
So when you use such a system as a neuromorphic computing system, I assume that you have some limitations regarding the bit accuracy that you can achieve when you're setting up the weights.
Sorry?
The accuracy that you can set up the weights.
Yes.
Does this significantly impact performance in the tasks that you have to take?
Yes, I don't have numbers to tell you here, but it is well known that this stochasticity can significantly also improve reduce the performance in the training.
And a quick question from Adonis as well. I'm the spokesman. is what time this switching between the on and off state, at what is the time scale that you can achieve?
So I show you here switching times of nanoseconds, 7.5 nanoseconds. In a group of York Lloyd Hall at ETH, there is a postdoc there. He recently showed picosecond switching times. Yes. Okay. In a non-volatile fashion, not a volatile. So
for the non-volatile.
he sent a picosecond and pulse, and then he got a non-volatile state.
Interesting. Thank you.
Any more questions? Okay. And let's thank then Alexandros again. And now we're going to the coffee break. I would say let's make it until 5:15, so 25 minutes from now. And at 5:15 then we start with the final ramp-up session.
I think we are all here, the persons who managed to stay till the end. So I think it was a very nice workshop. And we have already 3 candidates for next year. Miguel is one of them for Palma de Mallorca. We also had yesterday the intention of Jose to be also the host if there is no other candidate. And also I think Volker today said that he would like to also to organize this in Florida. Although Florida is a little bit far away for the Europeans, but okay, also Greece is also far away for the people from US, so we have to think about it. So
we should perhaps vote.
Yeah,
in the end, isn't it?
That's a good idea. Or we can discuss with the 3 volunteers offline and see who is going finally to do it. So I think it was a very nice workshop. Thank you all for being here, and it was very nice. Not only because all of you are excellent researchers, but also because we had a very nice view and the whole image of different activities in this area. We saw things that are closer to what we say photonic neural networks and how photonics can serve AI applications, but also we saw nice presentations, very inspiring ones, about neuromorphic and bio-inspired techniques, which are less conventional, let's say, but also very useful. And in my opinion, they should be also examined in depth in order to see what is the way we should follow, or the ways we should follow, because there might be more than one. And for this reason, I would like to, all of us, Nikos and Haris, we had discussed before organizing this meeting that it would be nice to have a final discussion and see what is the perception of each of us about the future of this area, not only in the scientific domain, because scientifically it can progress and can provide very nice results, and sometimes science does not have to follow the market, but it has to produce results, and you never know when they will be useful, but also to see what is the prospect of photonics to compete to other technologies, more established ones, especially in the field of artificial intelligence. So, what is the way to go? Should we follow the conventional way of trying to compete, for example, in MVM functions, the GPUs and the TPUs, or we should think of out of the box and try to follow brain-inspired techniques? So I think here it's an open discussion, so we want volunteers to start this discussion, to initiate this discussion, to say their opinion. Probably people who are already doing things close to the market first. I don't know if any of you wants to start this discussion. I was sure about that.
So I think at least at a high level, we should be doing what light is naturally good at. And I think that would be a very low-hanging fruit. So if you can define or even find even algorithmic approaches that where whatever light gives us is a natural good fit for it, I think that would be a very low-hanging fruit to target. I have several collaborators, these very big grants that we have, the $50 million vehicles and so on. Some of them, we have really hardcore IC people, like electronics people, and they are very, we need to really convince them strongly that we have something to offer. And I think they have a good point as well, because, okay, like for example, let's say with like TOPS per watt, right? So currently there's a DARPA program that has regular SRAM, 22 nanometer, not even 14 nanometer advanced SRAM, no heterogeneous integration, just standard old plain stuff, CMOS as almost as vanilla as it gets, as they say. And their challenge of DARPA is 70 TOPS per watt. That's what they're aiming for. And then they do even the whole SIM and PIM, the programming in memory and all that other stuff, right? That whole TSMC and the whole really memoristic stuff. So that then, I mean, TSMC basically said we can go to 400 TOPS per watt. So, I mean, that's why we looked into our performance. We said, okay, if we can we really at least get to 100 plus, or maybe a few hundred TOPS per watt. If your technology basically says, oh, we can get to 5 TOPS per watt, congratulations, but forget it. Don't even try, I would say, from this technology point of view, because it's just too expensive. So if there's, I mean, that's why we started looking into this Fourier stuff. So at least there's one order of magnitude better, simpler complexity. Is there something we can really leverage there? And there may be like a whole bunch of other things. I mean, maybe there might be maybe different optimization algorithms, maybe even in the cryptography space, maybe for hashing or so. Now, this of course goes away from neuromorphic necessarily, but now on the other hand, if we're very open, I mean, Light Matter raised recently $150 million for, well, not even compute, but sort of, I mean, they basically still say on their website they're doing a matrix vector, but they also do basic interconnect. I guess everybody knows this now, basic routing and so on. But on the other hand, JetGPT shows us we have so many components to train, so that's why I really realized in the last 12 months, the community flipped a little bit. Before then, photonics was really very esoteric and sure, I mean, yeah, we always look at you, but really not really serious. Now it had changed a little bit. They're really now saying, okay, so really what do you have now there? Let us really sit down and watch. I had meetings the last few weeks with everything all the way to the top, like TSMCs and GFs and so on. They're really listening. Several meetings, and they want to know more about what we as a community we are doing, right? So I think, so it's not maybe a very satisfying answer, but if you can really identify true, and we need to be very honest, and the other comment might be we need to do a system analysis. A device is good, and we all work on those to some degree, and that's great, but we need to do a system analysis, and a very, very honest one. And better, honestly, I don't even do this analysis myself. We work with, again, IBM folks that have done this for many, many years and so on, and really good people who do this for their daily bread and butter. So maybe I'll leave this as a kickoff.
So, in my point of view, I think that photonics should not, the primary target at least, not to subvert conventional approaches or to replace GPUs for MVM, but should focus on applications that are unreachable to conventional approaches or are not sufficient to perform such kind of application. Or, for example, latency critical applications. Or solving nonlinear equations that takes months, I don't know, to train in a conventional approach. So I think this is, from my point of view, should be our target, at least the next 5 years. Yeah, more or less. I don't know if you agree with me.
Yeah, as far as what photonics will do for AI, I would say that photonics is already instrumental to AI. So if you look at things like the Google TPU data center, that thing, it looks like a woolly mammoth of optical cables. And I think that there are two things that we should be looking out for. One is, where is that going to go? Are we going to see a mass migration from these pluggable transceivers to co-packaged optics where every chip that you have that does compute also has optics coming out of it? And then if that happens, what does that do to the marketplace in terms of how many fab months of photonics needs to be produced? And at the larger economies of scale, do we see prices go down? And then I guess when that happens, what other opportunities does that open up for photonics to do actual computing and not just communication?
Sorry, here. Just a quick remark because I need to go off the airport.
But in my experience here, working at the Chimera Research Center with photonic integrated circuits over the past 2 years and in neuromorphic photonics, we have identified that at the end of the day, photonics is like a wrench. It's just a tool, and as he said previously, you need to really focus on the application and to create something with, let's say, 10 or 100 times more impact in comparison with what is currently on the market, particularly electronics in the case of neuromorphic photonics. Otherwise, I think photonics, I'm not going to say that it's going to be doomed, but there's a long way ahead. I think we are way back, long way back from the electronic side of history. And I think at this now, we need to be really focused on the applications and to create something which would be exponential in terms of technology performance. Otherwise, I don't see it very clear. But I think as well we have to be the right to fail, but fail as quick as possible. Thank you very much for inviting me for this, and I need to really to get off the airport. And again, Adonis, for the invitation, and it's been a pleasure to meet you all. And it will be really nice to see you again next year. It will be that this is getting bigger and bigger. And again, thank you very much.
If I can intervene, I agree that photonics will take their place in specific applications, and we will find niche application that fits really well to the physics of photonics and what they can provide. But one thing that to consider is after Wim's presentation that in order to get things going, you have to fund them and you have to gain the volume and the market in order to do so. So maybe an interesting question is which are the applications that we should focus, these niche applications, that they are big enough and they have the volume in order to, if we stick to them, to gain traction and then get things going with neuromorphic photonics. So this is, I think, another point that maybe we should consider.
I think you're 100% correct. So, okay, I pitched my story yesterday from the point of view of programmable photonics. But if you really think from the applications point of view, these niche applications, like you call them, they are out there. We just don't see them because we're usually approaching the things from a technology push from our field, from photonics. Like, okay, we have this nice technology, we want to play with it. So the challenge is to basically, how do we get into contact with the people who really could use this technology? And they will probably have a problem that they can't solve, and they will totally not be thinking about photonics as a way to solve it. So bridging that gap or making that innovation, like by linking the two together, is a challenge. And I don't really know how we should solve them, but in any case, for any researcher or student in the field, I would say, like, try to keep your gaze as wide as possible and try to learn about other fields so that at least you get an idea of, oh, there might be people out there, there might be problems in other fields, and I might have something that can help them to solve it. And okay, those applications might suddenly appear out of the blue because one person talked to another person at a totally unrelated conference. And so we need to find that. And it's not going to be one niche application. There's probably many of those. We just don't see them yet.
Yeah, I fully agree with basically all of you. I think the main point is that everybody's trying to look for the killer application, but not only us here in photonics. For neuromorphic computing, generally in electronics, everywhere I go, everybody says, what's the killer application for neuromorphic computing? Will neuromorphic computing stick? So it's a thing for the whole of the community beyond this workshop. And I think I think that's a great point. We need to look for the applications rather than look at the technology. So here is a comment. We are focusing on doing, obviously, things with photonics. We're always looking at ultra-low power, very, very high speed. We can do more with less and faster. And this is one way of looking at this. Can we do more? And I start to think that perhaps we should look at, can we do less? So can we look at things that are very, very simple, and we can do it with low latency? Perhaps there is a lot of opportunity there. So, for example, when Ryan was talking about the edge, things that will require things that photonics might bring. So perhaps not everything is in, can we do more? Can we do more? Can we do more? Perhaps it's, can we do less, but do it very simple?
I am also going to repeat what the previous speaker said about opening the technology to the community. I'm one of the people here who is less familiar with photonics, but I know that once computers became readily available to students, we had more programmers. And then once microcontrollers became readily available to young people and start having lessons at school, robotics was a technology that was very quick developing. So maybe it's time to make something simple and not very complicated and give it to the community, to people like me who can solve problems with it, but I'm not a researcher to do research on it, and start solving problems that maybe none of us have thought of yet, and making this popular. I mean, it's creating a hype, which is, it is there, but not to everybody. I mean, if we go to a computer science department and we ask about photonics processor, no one knows about them. I hope in our department, many people know about them.
Yeah, I think you are right. And this is also in line with the black box perspective that Fim mentioned yesterday, or with the analog VNN software suite from Nathan and the suite from Tassos about combining PyTorch and VPI. These are indeed towards this direction. So sometime making it open to the public. And I think it's good that we make this type of discussions about possible applications, because I think now it's the time to start looking into that while we're developing the tools, because the tools are not ready yet. All the thing as the way it started, so 5-6 years ago, it started with a big boom about neuromorphic photonics. And at the same time, the boom was happening also in the AI community. So more or less they were growing at the same time, with the drawback of photonics that it was drawing towards a direction, the mainstream direction. So let's make a GPU, which was probably the first thing to think of, but probably not the right thing to think of. But during these 5-6 years, at least now all this hype has settled down. Now we know what we can do and what we can't, and we still have a gap to fill with the people coming from the AI community. So I think that all the approaches that we are working on are now useful and will be for the next 5 to 7 years in the form of developing the proper tools, while AI settles down as well to some point where we know what can be all the capabilities that they can offer, so that the two fields can be re-examined again, whether we can converge and finally bring something useful with photonics to the AI community or not, but probably not now, in 5 or 7 years from now.
If I may add to what Nico said, I took inspiration from Tassos' work about the different nonlinear functions and how you can tune them and change them, and maybe you have to train them. And a discussion that we have with a lot of people from the community is that in many cases, we generate the tools, but another question is which tools are we generating? So a main effort is we know how the AI is progressing, we know the tools that they generate, the tensors, the way that they compute, the way they make the matrix multiplications, and so on. But the key question is, should we develop the same tools? Because, for example, in the optics, we have 2 degrees of freedom. We have amplitude and we have phase. And we say that you make a nonlinear function like a sigmoid, because sigmoid or ReLU is a typical nonlinear function that people from the AI are using. But they use real value systems, not complex values. In the complex domain, when you have phase and interference, maybe this complex function is not the optimum one. Maybe the tool that we try to generate is not the best tool in order to solve the task. So maybe we should re-examine this as well. Which tools we should produce and compare them with the typical tools that AI already uses.
So it seems like this sub-community of the neuromorphic community, it has, of course, this additional constraint that it doesn't need to only be neuromorphic, it also needs to be photonic, right? So this limits even more, it makes the problem even more difficult. So, however, maybe there are some things that can be learned from also what, maybe some people in the electronic neuromorphic community or whatever actually. I'm about to talk my own book, essentially, which is, so the approach we took is say, okay, let's see, what can we demonstrate that would work today and be able to show something of a state-of-the-art type of improvement in what already works today, right? So we added neuromorphic mechanisms to deep learning networks that already work on GPUs, and we showed some advantages. So now, in a similar way of thinking, maybe the photonic subfield should focus on things that are already working for useful photonics, and then apply some neuromorphic principle to those. And from what I understand, maybe some working photonic applications are actually interconnects, and so not photonic processors, but maybe photonic interconnects. And then maybe that interconnect can be made more neuromorphic by somehow, I don't know, deciding, I'll now make up things, but maybe you can make that signal transmission to be more dynamic or more intelligent or whatever, but then it would be already in the photonic domain in an application that is actually proven to be useful and already has a market and perhaps even growing prospects or whatever, with the addition of neuromorphic elements that improve it. So maybe that could be a kind of a ready path to improve. But yeah, I'm a bit of an outsider in the field, so feel free to drop these ideas.
I guess I'll make another comment more on the software side of what needs to be done for neuromorphic systems to be useful, which is that both for photonic neuromorphic and other kind of neuromorphic systems, people aren't used to training their neural networks in that way. And it's sort of like the answer to the question, why does so much software work on x86? It's not because x86 is the best instruction set architecture, it's because that's just what took off at the time. And like a snowball, that's what everybody adopted. So I think a good question to ask is, if somebody is used to training neural networks with conventional techniques like TensorFlow, PyTorch, how much extra effort does it cost them to retrain their model on photonic hardware or neuromorphic hardware? And if that extra cost is a factor of 2, they're going to be put off. But if it's, let's say, 10% more and they can get a 2x performance boost, maybe they'll consider it.
So another question would be, I mean, we always say now, the community, right? Well, who's the community? I mean, I guess it's the community of neuromorphic photonics people. Well, that's literally us, and maybe plus double the ones that are right now here in the room, right? I mean, literally, that's about it. And what's our intent? So we are, I mean, I don't know, are we engineers? Are we researchers? Are we entrepreneurs? Like, how do we define success? Nature papers, is this success? Well, it's success, but is it enough success or not? I mean, maybe I'd like to ask the question back, so what do you think should be our success? I mean, I think each of us have our own version of success, right? Because let's say, the point is to innovate new parts, then we should be measuring, again, papers and IP. Okay, we can do this. And maybe we are very successful already as it is. Maybe we are amazingly successful compared to other ones. I don't know. But if the success, now if the question is, oh, no, what the success is, we want to have the next, I don't know, Apple and whatever, NVIDIA, and that's the success measure. Well, then we have way to go, right? Then we need to think, I mean, Wim and I were brainstorming a lot here about how, like, what does it take to get to those levels, right? So that's a different question. And the other one about like this whole democratization of winning buy-in and fanning out sort of our ecosystem to, you know, everyone can work with us, right? Other data scientists and so on. This is just, in my mind, a marketing problem. I mean, it's in the end, one needs to really seriously just like change the marketing approach and just make a target approach to certain people and win them into our ecosystem. But again, my question is like, what are we after? I mean, are we after the market? Are we going after, we're not producing much, like enough papers and IP, or we really would like to have another photonic NVIDIA? And I would say there are companies that are pretty successful already as it is. I mean, so I don't know, like, we're doing, so to some degree we're also doing well, right? But,
I think I can answer that. I'm joking. But since here we represent Pythagoras, Plato, and Aristotle, we have to tune, you know, the weights of the three philosophers and see in which direction we want to go. For example, if we want to go to the scientific part of this story, we will give a higher weight to Plato and a lower weight to Aristotle and Pythagoras. But if we want to go to the direction of something useful for the society and not only for the scientific community, we have to put a higher weight here to Aristotle and to Pythagoras. In my opinion, I think that, okay, science is a very beautiful thing. This is why we all want to do these things, because we love science. But if we want to see something beyond that, in my opinion, is that we should start step by step and see how photonics can really enter this, not market, I wouldn't say market, I would say this specific domain, the domain of computing. And I think that the things have been already spoken here and have been, the opinions have already shown that, in my opinion, the direction is that to start with some applications which are closer to photonics, and I think you need to have the initial signal in the optical format, and this is, for example, communications, or even LiDAR. LiDAR, for example, is a quite, you know, an exploding area, and we do not have any proposition in order to process things in the optical domain. We just rely on digital processing for LiDAR, while the information is intrinsically in the optical domain. This is the first. And the second, in my opinion, is to use these nice new training techniques, like the ones presented by Timo Leon and some discussions from Tassos here, and other things. We see new tricks, for example, this direct feedback alignment and other things, which can really reduce the effort in order to online train a photonic chip. And I think, in my opinion, we should try to work towards this direction. How we can use information in the optical format and process it optically, and second, how we can easily train online photonic processors using even photonic techniques to do that. This is my perception, at least.
Yeah, I also don't know how to define success, but at least the dream of all the people who were in the optical computing community, even from the 70s, 80s, was to make them becoming real, as was also the telecom industries. This was their dream, and their dream that failed several times till now. So probably this should be the dream from them even now. And I don't think that they care about success or not, just to see them being on the same level with the telecom applicability of optics would be okay. I think that's challenging to achieve still. But seems to be closer than it used to be 20 or 30 years ago, where there was, again, a big hype. So now I think it has come closer to the nature of light, which is analog. So seems to be closer. So I don't know how it will proceed.
Yeah, so another thing that I was thinking about is that you should have a greater collaboration between the photonics, the people who work on photonics with the people who work on neuroscience. Because there are many concepts from neuroscience that can be used in photonics in order to help them be more reliable and more efficient in what they do. For example, the reservoir computing sim, which is not used very much in the AI that we are hearing in our everyday. It is a concept that has worked very good in photonics because it uses their high bandwidth in order to produce many nodes and have a good result. So, and also there are other concepts like the direct feedback alignment and the Hebbian learning that can be used in photonics in order to accelerate and aim their and help their results. So I think that there are many other concepts from the neuroscience that can be uncovered and be used in order to further improve the efficiency of our photonic sim. So I think that it is needed a more good collaboration between these two fields. The reservoir computing concept, yeah.
So probably the conclusions are there, so we'll know what to do right now.
Do this is we could also flip it around. We could say, okay, so what can we absolutely not do in electronics right now that we possibly, eventually, hopefully, there's a roadmap to do in photonics, right? That would be another option. So, and then we call this a grand challenge, and then we give, I don't know, some funding money. You know, like 1,000 by 1,000 matrix at 1 nanosecond, right?
Or teleportation.
Yeah, that's something we're realistic. I mean, or just, I don't know, just, you know, we can define some certain targets that clearly, and yeah, so that would be also interesting, right? To say, but now this is again a push as opposed to be a pull, right? We just push certain technology if we have it, but that may be another way to, again, dissect the field, right?
So I think we have already discussed a lot on this. We would like once more to thank you for being here. I think it was very interesting, at least for us. I think for you as well. And we will definitely repeat it next year. So we will discuss with the candidates, unless you want us to vote for now.
No, a proposal could be the following, since we have 3 candidates. So to arrange the sequence so as to have it carried out for the next 3 years.
Yeah, that's correct. Actually. Yeah, that's a good idea. Yeah, of course.
And okay, being now in Greece and having 2 candidates from Spain, 1 from Florida, could be starting gradually to go to the Western coast. Next year to Spain, 2 years from now in Florida, and then back through Spain again.
Yeah, that's correct. Okay. So thanks again, and
yeah, thanks a lot to all of you.
We will meet each other in other conferences, in other events. And of course, next year in the 3rd workshop in Neuromorphic Photonics. Thanks a lot.
Thanks a lot. Thank you.
And especially thanks to Adonis, because he was the local host here, so he undertook most of the things. So many thanks, Adonis.